Good morning again, everybody. It's 8 o'clock. We're going to give people another 120 seconds and then we'll start. In case people are having difficulty logging in. Our participant list is going up quickly, so people still joining.
I've got eyes on this and I've got my Teams open and I've got text open. If you guys notice any trouble with IT stuff as we're going here, I'm trying to keep my eyes going 4 different directions, but
yeah, thanks for that, Elliot. Hey there, David. Let me see. I think it's called Prompt Smart. Let me see. Prompt Smart Pro.
All right, well, I've got 8:02, so we are going to get started here today. And it looks like, yeah, we've got a lot of people on the phone. So good morning. I'm Greg McCowan. I'm a biologist with the California Department of Fish and Wildlife, Office of Spill Prevention and Response. I'm the chief of our response technology and support branch and have been working in oil spill response myself for 28 years. Thank you all for joining us today. Who are you? Well, when I checked last, we had approximately 200 registered attendees representing approximately 70 entities. There are 4 non-US sovereign nations represented: Canada, Cherokee, Wyatt, and Yurok nations. And my apologies if I pronounced any of those incorrectly. Representatives from multiple states and provinces are on, numerous industry representatives, oil production, refining, distribution, service providers, consultants, Class 1 railroad, a lot of local, state, and federal government agencies, and a number of NGOs as well. So thank you all for being here and for the work that all of you do to prevent, prepare for, and respond to oil spills. Personally, I'm speaking to you from my home office on the historic lands of the Chenault. I want to start this morning by thanking the people who made this workshop happen. First and foremost, our workshop coordinator, who also leads OSPR's Best Achievable Technology Program and our Fisheries Closure Program, and that's Annie Nelson. Big thanks to you, Annie, for all your work to review the technologies, coordinate with the presenters, and host today's session. So thank you very much. I also want to thank Ellen Farrow-Daniels, our Applied Response Technologies Coordinator, for her work, and Elliot Frodel for providing the IT leadership throughout and today. So thank you guys as well. And thank you to my boss, Deputy Administrator Julie Yamamoto, for her support in facilitating today's workshop. A little bit of an introduction. Last October, as probably most of you are aware, there was a release of approximately 25,000 gallons of crude oil from a damaged pipeline in the Pacific Ocean off Huntington Beach, California. That prompted a large-scale response with approximately 2,000 responders, cleaning the shorelines, the water, and caring for oiled wildlife. The release occurred around 2 in the morning, is my recollection, or was first detected, and response vessels were mobilized immediately. However, as is often the case, there were some aspects of the initial response that were waiting for a situation report at first light to get a better sense of what we were dealing with, waiting for overflights and that sort of thing. That prompted some questions about why we can't do our work just as well at night as during the daylight. And the administrator of OSPR, Tom Cohen, who will be speaking to you next, committed immediately to conduct a special workshop to assess the status of technology that could be used to detect and recover oil at night and in other low visibility situations. Today, you're going to hear about a variety of technologies that advance our ability to conduct our work when we can't directly see the oil with visible light, from Spaceborne and Airborne technology to on-water and underwater remote sensing, and even to the abilities of our canine colleagues. We've got a great slate of presenters leading us into the future of spill response. Before we start, I do want to address one key topic that directly influences our ability to conduct effective operations at night, and that's the safety of response workers. Even if we know where the oil is and how thick it is and what tools will most effectively facilitate its recovery from the environment, we're still at a place where many of those activities require human involvement. The number one priority for the spill response community at every spill is ensuring the safety of response workers and other people potentially at risk. Even if we're able to effectively map an oil slick on water at night, we still may wait till light to deploy recovery assets if they require people to operate them. Working through night increases the occurrence of impaired motor skills, reduced cognitive function, and slowed reflexes. Work-related injuries are more frequent. I was looking at a 2001 study that found the risk of accidents for offshore shift workers was substantially higher, that is double-digit percentages higher between 6 p.m. and 6 a.m. compared to a daylight shift from 6 a.m. to 6 p.m. So I just wanted to include that as a reminder. Detection of oil at night and in low visibility conditions is a key step in the advancement of spill response efficiency and effectiveness. But implementation requires full integration of the recovery assets and the people who operate and manage those assets. Safety will always be our highest priority. So to kick things off today, it is my pleasure to introduce to you the Administrator of the Office of Spill Prevention and Response, Mr. Tom Cullen. Administrator Cullen is a retired captain of the U.S. Coast Guard, having served for 27 years. He has senior responsibility for the protection of California's 3,400 miles of tidal shoreline, 30,000 miles of rivers and streams, and 4,800 lakes from the impacts of oil spills. Administrator Cullen is an ardent advocate for new technology, and his personal commitment to ensuring that OSPR maintains awareness of and fully embraces the best possible tools for safe, efficient, and effective spill response is invaluable in protecting the natural resources and public interests that depend on us. So with that, please join me in welcoming Mr. Cullen. Tom, take it away.
Hey, thanks, Greg, and welcome to all of you. And Greg, we should have coordinated our opening remarks a little bit because I'm going to give a little bit of a rehash. But sure enough, in the morning, late evening hours of Friday, October 1st, reports started trickling in from fishermen who were preparing to set their lobster pots about 8 miles off the coast of Huntington Beach, and they smelled a heavy petroleum odor in the air. And one of our California Department of Fish and Wildlife Patrol boats happened to be in the area to monitor the lobster fishery that had just opened, and they began to investigate these reports. But their, as we say, Mark 1 Mod 0 eyeballs and nostrils didn't detect anything. Of course, this is an area that's known for significant natural seeps from the seabed, as evidenced in the past couple of weeks' reports of many such tar balls washing up on southern Los Angeles and Orange County shorelines. There's also a resignation and an acceptance that not much can currently be done during darkness, and that first light would reveal the potential source of that particular odor back in October. Of course, that was not a natural seep, but the first indication of a significant release of more than 20,000 gallons of crude oil from a damaged pipeline on the seabed that transports crude from 3 offshore pipelines to a receiving facility by the Queen Mary in Long Beach. The next day revealed a harrowing sight, not just long swaths of dark oil in the water, but there were hundreds of pleasure craft queued up, lining up to witness Blue Angel's air show. The next morning, I joined a handful of other federal and state executives to embark on a Coast Guard aircraft and overfly the scene. And it was a foreboding sight with miles of sheen and interspersed with dark patches of crude oil. And as Greg said, during subsequent hearings in the California legislature, I described our office's mandate to evaluate and mandate the use of best achievable technologies in the protection of California's natural resources from the effects of oil spills. And one such measure that we use to meet that goal is to co-host an oil spill technology workshop every 2 years. We co-host that with Chevron Shipping. And the most recent one of those was this past February, where we had several hundred panelists that joined us virtually. And Greg, you can correct me, I think it was from about 70 countries. And I promised the members of the Senate and the Assembly during those hearings that we would hold another one of these more focused off-season events to better discuss and evaluate the current state of the market technologies for detecting oil at night and in low, i.e. fog, visibility conditions. Time is precious, of course, in the initial hours following the release of oil to our precious waters, and many measures could have been accomplished much earlier had we better known the location and extent of this most recent spill. As someone who spent many years in his early Coast Guard career flying over oil spills using 1950s detection technologies, and as a current licensed drone pilot, I'm really excited to learn about what is out there to help us better perform our response mission. And as I look through today's agenda and scan the participant list, I'm very encouraged and excited about what we will hear today. I thank all of you who will present, as well as the rest of you who are joining us, taking time out of your busy schedules to collaborate and learn more about this important topic. Many of you are return presenters to our past technology workshops, and I hope those of you that are newcomers will find today's sessions both informative and invigorating, and join us next February for our 10th biennial session. I'll add my thanks to Greg, Annie, Elliot, Ellen, and the rest of my incredible OSPR team that helped put this together. I look forward to reading your evaluations, how we did, and I hope that today meets your expectations. Thanks so much.
Thanks, Tom. Annie, take it away.
Good morning, everyone. I'm Annie Nelson. I am OSPR's Best Achievable Technology Coordinator, and I welcome all of you here today. I just want to go over a couple quick things before I introduce our first speaker. Hopefully all of you saw the agenda, which is posted on the OSPR website under our science page. I added recently a second page to that agenda with all of our speaker bios and contact information. So if you're interested in following up with a speaker later on, you have that information. And for that reason, I'm going to keep my introductions pretty brief today and let them introduce themselves. In addition, we're going to keep the chat open today. I just ask that everybody remain professional and respectful in the chat. No advertising, please. Just use it for general comments and kudos during the workshop. If you have a question for any of our speakers as they're presenting, we ask you to use the Q&A feature of Zoom, so that way we can track the questions better, and we can ask them for you when the speaker's finished with their talk. In addition, if something comes up during that question and answer period and you'd like to put your hand up, we'll be watching for that too. So you can ask a live question if it comes up at the last minute, but try to use the Q&A. That's easiest for us to track. And with that, we're a little bit ahead of schedule, but I see that our first speaker is online. So I'm going to go ahead and introduce Gordon Staples. He is a senior radar application scientist and project manager at MDA, and I'll let him give you some more information himself. I'm going to stop sharing now. Gordon, if you're ready, go ahead and take it away.
Hi, Annie. Sorry, I just stepped out for 1 minute. Did you want me to start?
Yeah, please. I guess we're running about 15 minutes early for our startup. So if you're ready, yeah, please go ahead.
Yeah, no problem. I'll share my screen. Okay, I assume everybody can see my screen and hear me. Good morning, everybody, and thank you to the organizers of this event for the invitation to present. I'm really excited about doing this, and I echo the comments that the people speaking today, I think, bring a wealth of information and a wealth of background in terms of oil spill response. So I think it should be Very interesting for the participants and also very interesting for me to learn a little bit more. So today I'm going to talk about Spaceborne SAR for oil spill detection and response. And I just introduced myself again, Gordon Staples. I'm with MDA from Richmond, British Columbia, Canada. So brief outline, start with a quick introduction. I'll then look at slick detection. This is just a summary of the capability in terms of target parameters. So those are the oil characteristics, environmental, and the radar component. Look at a couple of capabilities, and that's area and relative thickness. And Ben Holt, the next speaker, will be talking in detail about relative thickness. So my comments on relative thickness are just a very quick overview and to a degree kind of an appetizer for what Ben will talk about. Look at data access. So this is data processing and delivery, and finally operational considerations. So I'm sure people have seen examples of this many times before, but for those who haven't, the photo on the left is just, well, exactly what it is, a photograph of an oil slick off the coast of Louisiana. And this is the corresponding image from RadarSat-2, and they were taken about 2 hours apart. So from a visual point of view, the oil appears to be a slightly lighter hue than the background ocean. But when you go to a radar image, for the most part, oil, various slicks in a radar image appear dark. So the question is, why is that? So the viscosity of a slick plays a really important role in dampening the capillary waves. So these capillary waves are these very small, short wavelengths on the order of a few centimeters that are on the top of the ocean. And the dampening of these waves, the capillary waves, play a key role in what's called Bragg scattering. And the Bragg scattering is really what causes the radar return from the ocean surface. So the rate of dissipation of these capillary waves is related to the kinematic viscosity, the ocean wavelength lambda, and the boundary layer thickness. So as you can appreciate, as that oil becomes more viscous, you're going to have more dampening. And in general, an oil slick is particularly effective at damping out these short capillary waves. That in turn causes reduced radar backscatter, and that in turn will generate that dark tone in the image. But as usual, there's always a few caveats in there. So anybody who has looked at oil spill knows that there are many other parameters, many other constraints, situations that will cause false positives, oil lookalikes. A relatively common one are rain cells. So in this scenario here, and you have a couple of examples. One is when you have, moderate to, moderately heavy rainfall, that will dampen the ocean surface in the same way that an oil slick does. So that area will appear dark. And there are some occasions that with very intense rainfall, there's enough density of rainfall that the radar signal will actually be attenuated and you don't get a response from the ocean surface. Excuse me. Low wind speed will also cause a reduced radar response. So sometimes that can be misinterpreted as an oil spill. And similarly, the presence of oil seeps, which fundamentally are oil. But if you're looking at pollution, for example, that can be a sort of a false positive. Internal waves and other oceanographic features can also cause area of reduced backscatter. And finally, when you're going from mineral oil, mineral oil to biogenetic surfactants, they also have a similar appearance on the ocean surface. So transitioning now to just an overview of the various parameters. And as I mentioned, I broke this down to oil characteristics, environmental, and radar. So if we look at the oil thickness, in general, a radar can detect thickness that's more or less consistent with the bond agreement thickness range. So this is from, say, the mid-range of sheen through metallic and through emulsion. I talked about the viscosity. And so as the viscosity increases, you have increased ocean surface damping, and that in turn improves the slick water discrimination. In terms of area, I have a few more comments on this to follow, but in terms of the area, we can detect areas less than half a square kilometer, but from an operational point of view, based on some work that we have done, something on the order of about half a square kilometer can be readily detected. And this was based on 50-meter resolution SAR data. If you go on now and look at the environmental, from the wind speed perspective, in order to generate these small-scale capillary waves on the ocean surface for C-band radar, the wind speed is roughly from about 2 meters per second as more or less the minimum. In the absence of any wind, the ocean surface appears smooth to the radar, so it's difficult to discern the slick. And on the order of maybe 10 to 12 meters per second, the oil is mixed in the upper layer of the ocean surface, so you see that detection. The presence of rain. So for very light rain, there is a negligible impact in terms of detecting the slick. But if that rain increases significantly, then that in turn disrupts that surface film and there's degraded detection. Clouds and fog, negligible, so a non-issue there. And day-night is also negligible. But I should add the caveat that most polar orbiting satellites image at about dawn and dusk. So in the case of RADARSAT-2, we image, roughly speaking, at 6 a.m. plus or minus an hour and 6 p.m. plus or minus an hour local time. So for example, the Huntington Beach oil spill, we imaged that 6 a.m. and 6 p.m. So as much as we could image at 3 o'clock in the morning, no problem with the radar, we're simply not in a position to image. So that's a consideration. Looking now at the radar side of things, so there's the polarization. For the most part, vertical polarization provides a little bit better discrimination than horizontal polarization, but they're relatively similar. But they are both much better than what's called the cross pol. And in general, the cross pol response provides a very weak radar return. So it's usually not, if ever, used for oil spill response. The resolution, generally not a limiting factor for detection. I mentioned about this half a square kilometer minimum area in that range. There is some interest sometimes to go for high resolution data. So high resolution data could be 5-meter data, 10-meter, 3-meter, as the case may be. And what that will provide is sort of interslick variability. And that could be very applicable, say, in a case when you're looking at relative oil thickness and when you're responding to an oil spill. If you can get more detailed information about the relative oil thickness within a spill, that in turn will allow the responders to target their efforts. Continuing on with the radar side, there's what's called the incident angle. And very briefly, the incident angle is measured from the vertical to the incoming radar wave. So at about 25-degree incident angle means the radar is looking more directly down on the ocean surface and more obliquely at 45 degrees. For the most parts, at larger incident angle, a slick is visible, but that's very close to what's called the radar noise floor. Carrying on to the next one, the noise floor. So the noise floor of a radar is really the sensitivity to discriminate low return features. So for example, if you were detecting a building, there's no issue there, or a ship, but an oil slick has a relatively weak radar return. And so that can introduce problems. So the noise floor increases with increasing incident angle. So at a larger incident angle, when you're at 35, 40 degrees and beyond, that can impact quantitative analysis of the data because of that influence of the noise floor. But from a visual perspective, there's usually very limited impact. And for example, we've seen oil slicks at 45, 50 degrees, even out to 55 degrees. So you can visually see them. But as I mentioned, there may be some impact quantitatively. And finally, in terms of the radar wavelength, the dampening of the Bragg resonant waves is more effective at shorter wavelengths. So that means that X and C band do a little bit better job of detecting an oil slick than the longer wavelengths, the L and the P wavelengths. The differences are, relatively minor, really and truly. So going on now to look at capabilities, look at the minimum slick area and the relative oil thickness. So we completed an analysis what, a year or so ago, 6 months ago, and we looked at about 215 RadarSat 1 and 2 ScanSAR narrow images. So ScanSAR narrow is characterized by about a 50-meter resolution. And we had gone through and we had done a classification, a visual classification of the various slicks. And we broke them down to pollution slicks and from oil seeps. That encompassed about 1,200 slicks in total. So we used a kilometer as a square kilometer as kind of a break point. And for those pollution and oil slicks that were less than about a square kilometer, the average detected area was about half a square kilometer. And again, as I mentioned before, that was based on 50-meter resolution data. So what does a half a square kilometer translate into something perhaps a little bit more meaningful? If I look at the area and volume, so this is the bond scale going from sheen, rainbow, metallic. And if you look at the thickness, I did an estimate here of the liters per square kilometer and then converted that to barrels based on approximately 158 liters per barrel. So in the mid-range of these different categories of oil or categories of sheen, metallic, etc., the number of barrels of oil for that half a square kilometer, is really quite small. Through here, you're 1, 8, 80. Even when you're out to, on the order of 600 barrels for relatively thick oil, for the most part, half a square kilometer is relatively small. It's a very small area. So from a radar, a SAR point of view, usually that area is so small and very likely a short duration that it precludes the use of SAR. Now, of course, as that area gets larger and as the spill duration increases, that's where radar, especially spaceborne radar, plays a very strong role. So if we go on now and look at the estimation of relative thickness, and again, as I mentioned, Ben Holt will talk about this in more detail. But this is just a quick look at 3 techniques for doing this. There may be other ones as well. So I started with quad polarized data. And very briefly, quad polarized data provides as much polarimetric information from a radar as you can possibly get. And so with the RadarSat 2, what's called the fine quad polarized mode, it's a 10-meter resolution. And what's done here is to exploit typically the horizontal and the vertical data channels. There's also look at the phase difference, which is the difference between the copolarized data channels. And there are a variety of polarimetric discriminators that can be effectively used for relative oil thickness. You go on now and look at single polarized data. So we can get this from ScanSAR narrow from RadarSat 2, from the Sentinel-1 imaging mode, relatively large swath widths here on the order of 300 kilometers. And in this particular case, you are looking at what's called the damping ratio. And usually you use the horizontal or the vertical polarization. And essentially the damping ratio is just the ratio of the oil compared to a slick-free area. And finally, there's the compact polarimetry. And this is an imaging mode that is currently available on the RadarSat Constellation mission, which is the Canadian government SAR satellite that was launched about two years ago. And much like the quad polarized data, there are compact pole discriminators that can be used to estimate relative oil thickness. So as attractive as, for example, quad polarized data is, and the quad pol mode on RadarSat 2 has an extremely low noise floor. so suitable for oil. Where you get clobbered is the relatively small spatial coverage. So for a small spill, when you know where the spill is located, this is pretty good. But if you look at other modes, the ScanSAR narrow and the Sentinel-1 imaging mode, a much larger spatial coverage, so much more amenable if you're looking, this would be a really big spill, but if you're looking at spills, you're looking at the spill drift, or if you're searching for the location of the spill, these larger imaging modes are very attractive. And that makes the use of the damping ratio equally as attractive. Just an example here. What I did is an oil slick off the coast of Louisiana. And this is the RadarSat 2 quad polarized image with one of the polarimetric parameters called the entropy. This is the RadarSat 2 damping ratio. And this is an RCM simulation. I couldn't get data simultaneous with RadarSat 2. An RCM simulation using a compact polarimetry discriminator called the degree of polarization. And as you can see, for the most part, they're very similar in terms of the ability to discriminate the sort of a relative oil thickness. This area here is, for the most part, oil-free. As you move into this area, you get into oil sheen. And then this reddish color here, it varies, but the center part here and through here is an area of thicker oil. And we had in situ data that was acquired during the acquisition, and also use optical data to do an oil slick classification. So we had a very good idea where the thicker oil was. And so the point here is that each one of these techniques can be used to estimate relative oil thickness. And there's also considerations for operational constraints, such as the image size and a few other parameters. So going on now and looking at data access, there are two broad categories for that. One mode is what's called a standard acquisition plan. And the standard acquisition plan means that the data are acquired on a regular basis. There's no option to cast the satellite for user-defined needs. There are typically variable acquisition modes for terrestrial and maritime. A very attractive feature of this data is that they're available at no cost. The processing time is variable, but usually 1 to 3 hours after data acquisition, which for oil spill response is pretty good. An example of that is data from the RadarSat Constellation mission and also Sentinel-1. The other model is a commercial or user-defined mode. And in this particular case, the data are acquired based on user needs, or in the case of for RadarSat and what we do, it's called a background mission. So independent of a user need, we may acquire data at certain parts of the world. An advantage of this is that there are user-defined imaging modes, user-defined processing time, and user-defined delivery time. Great, but again, never really a free lunch. So unlike the previous standard acquisition plan, the commercial data does come with commercial pricing. So examples of that are RadarSat 2, and then a bit of a plug for what we call it's our Chorus satellite. And we are in the process of building what we consider the next generation radar satellite. So if we look in the case of a little bit of bias here, of course, but if you look in the case of data acquisition, processing, and delivery timelines, from a, from a programming perspective, the satellite can be programmed as little as 12 hours. And so if we receive a request, say there's an oil spill, if we receive a request, we can take that request, turn that into the appropriate parameters that are needed, upload that to the satellite, do that within 12 hours. We can do that in 4 hours, but this is a very special case. And it depends what's considered an emergency based as defined by the RadarSat 2 Mission Management Office. In terms of data downlink, there's a couple of options there. If we are within a ground station mast, so we have ground stations around the world, and a station mast typically has a radius of about 2,000 kilometers or thereabouts. So this is an example here. This is off the south coast of Florida. This is the station mast here from one of our ground stations in Gatineau, Quebec. So if we were imaging an oil spill out here, for example, the satellite is flying this way, flying northward. We acquire the data, but we record it on the satellite. And as soon as we're within ground station receptor, or within the ground station mast, we immediately start downloading. If, on the other hand, we are over an area where we are within the ground station mast, we acquire the data and it's simultaneous downlink to a ground station. In terms of recording, it depends on the proximity to a ground station mast, but worst case scenario, you're looking at about 4 to 6 hours from acquisition to recording to downlink. In terms of data processing and information extraction, once the data have been processed, have been downlinked, we can process that data typically less than 10 minutes. The information extraction, so that depends on the scene complexity, but usually, well under 2 hours. If we're looking at an oil spill, we can take that image, process it. We can do a very quick digitization of an oil spill, probably within 20 minutes. And then following that is just electronic delivery of the information product. That's typically very quick, but to a degree, it does depend on the communication bandwidth. So one example here that was pretty good. We didn't have to do a lot to this. We do have the capability, but we were looking at a oil spill study off the coast of Louisiana. And we had an acquisition that was acquired at 0700 Central Time. We were within the ground station mast from our station in Gatineau, Quebec. So we downlinked. So we downlinked the data, processed it, we extracted, delineated the oil spill, we compressed the image to 2 megabytes, we bundled that up, and we delivered that within 42 minutes of the acquisition to a ship that was out sampling in this area. So in this particular case, it wasn't that the stars were aligned and it took a lot of effort on our part. It's something that we can do on a fairly regular basis. So going on now to look at the operational component and oil spill response and the role of STAR. So I broke this into 3 categories. One is short term. So these are typically very short duration events, perhaps less than 24 hours, small spills in marinas, lakes, on the order of tens of barrels in that range. Realistically, the time frame is generally too short for SAR to respond. You look at a moderate spill, so Huntington Beach comes to mind, bilge dumping, maybe hundreds to thousands of barrels. The duration is days to weeks. And it depends on the spatial extent on the duration, but a larger spill, Huntington Beach, it was probably there, I don't know the exact days offhand, 4 or 5 days or thereabouts. And that's long enough to get the SAR data. So in that range, that's a good role for SAR. And when you get into larger spills of national significance, classic is Deepwater Horizon. This is on the order of weeks to months, and this is a very strong role for SAR. So just an example here of what can be done when you're combining data to respond to a spill. I picked the date, December the 10th, largely because in mid-December, Sentinel-1B failed and is currently not operational. So I backtracked a little bit. So sort of a spill, this is the Huntington Beach area. And I said, okay, for example, I picked the date, December the 10th, what can you possibly get? So, and this varies, and this was not necessarily picked to be a perfect example. It does vary, but I would say that it's a typical example. So in this case, there was an oil spill reported December the 10th. On December the 12th, there was a RadarSat 2 acquisition, so up here. And certain times of a RadarSat 2 orbit, we can get 2 acquisitions that are 12 hours apart. Normally that doesn't happen, but in this particular case it did. So we had it December the 12th, the 13th, we had a Sentinel-1B. Similar idea, we had 2 acquisitions 12 hours apart. Then we had a Sentinel 1A, again, 2 acquisitions 12 hours apart. And then finally on the 22nd, a RadarSat 2, there was a single acquisition. And this really speaks to when you have multiple SAR satellites in place and the fact that they're imaging on a fairly frequent basis. The orbits aren't exactly the same, so you get variability in terms of the days when they image. But collectively, they're able to image an oil spill. And again, if you have a reasonable duration and a large enough area, you can start tasking satellites to meet needs. So finally, SAR provides all-weather day-night imaging and is very applicable in terms of responding to oil spill detection and response. There is a very good understanding of slick detection performance as a function of the oil characteristics, viscosity, etc. Environmental conditions, the real enemy here, so to speak, is the wind speed and radar parameters. There are data access models that provide predefined and user-defined data, SAR data, usually within hours, that can be downloaded, usually within hours from a ground station downlink. The satellite orbits are deterministic, so the time to the first image and the subsequent imaging opportunities are known. So they're known tomorrow, and they're known next year, and they're known 5 years from now. So once the oil slick has been located, and then you look at that and say, okay, when's the next satellite orbit? And we can do that very, very quickly. Finally, in terms of looking ahead, we are just embarking on a project to implement deep learning algorithms for slick detection and classification. And as I mentioned, we're in the process of building a new C-band SAR that will eventually, it will be launched when RadarSat 2 is in orbit and eventually replace RadarSat 2. And what this satellite does, it's the best of RadarSat 2 and the RadarSat Constellation mission. And one of the sort of innovations or the significant changes is that it's an inclined orbit versus a polar orbit. And that inclined orbit means that we image roughly as far north as about 65 degrees and 65 degrees south. So we're not necessarily imaging the poles, but the advantage of that is that we have increased revisit even with a single satellite. So that's what I had to say. And thank you very much for listening. There's a few minutes for questions. I can answer those.
Thank you, Gordon. I know we had at least one question from Oscar. Oscar, did you want to?
Yeah, thank you. Hello, Gordon. Good morning. Just want to ask you if you could expand on the characteristics of the new generation of RadarSat. I wonder if there is going to be same type of beam mode characteristics like quad polarization capabilities or things like that compared to RadarSat 2?
That is the current plan. It will have the quad polarized mode. It will also have what's called the compact polarimetry mode. So it kind of brings what we learned from, well, fundamentally, really and truly, it's what we learned from RadarSat 1, RadarSat 2, and the RadarSat Constellation mission. And we took all of those and we said, what's the best that can be used to meet a variety of operational needs. So some of the modes aren't there, but we picked the best. But the quad pole, compact pole, the wide swath modes, etc., are all there.
Thank you.
Great. I also saw just a one-word question that says costs. Do you have any general information on that, Gordon?
Cost for RadarSat 2?
I'm assuming.
Yeah, so we have our posted commercial costs, but much like a hotel, when there's the rack rate and then there's the Expedia discounted rate, we tend to do a similar thing. If you're buying a single image, it's probably going to be whatever the posted cost is. But if there's multiple images, the price per image drops a little bit. Well, drops quite a bit, to be honest.
Okay, let's see. I have a question in the Q&A from Matt Bissell. It says, how were you activated? Were you contacted and activated by PRC, state, the feds? And by the way, great presentation.
So the activation, this is something that we have a two-pronged approach. We do a lot with OSRL and other oil spill response companies. So we have an agreement with them that they can call us, and then we will immediately respond to their needs. But in general, for anybody else, we have a 24-hour-a-day, 7-day-a-week hotline, to use that term. So there's somebody available, and not necessarily for oil spills, but this is for any type of emergency. So it could be an oil spill, it could be an earthquake, it could be a flood. And what we try to do is to tell people, part of our, our sales people and our business development people, to let people know this is the number. So it's almost like you need, like FedEx, for example, it just comes to mind. They've done a really good job of, the 1-800-GO FedEx or something like that. And they've marketed that, and people know that's what I have to do. So in effect, I don't know if we've done that, but we need to let people know, and we do try to let people know as much as possible. There is this single number. You can call it, anytime, and there's somebody there who will take the information, and they will find out, what are your data needs? Where's the area of interest? They will in turn convert that to what is needed to upload the information to the satellite and arrange for the next acquisition.
Thank you. And I have one more question in the Q&A. Says, are these satellites owned by your company?
RADARSAT 2, yes. RADARSAT Constellation mission is owned by the Government of Canada. And the one we are building, which we call Chorus, will be owned by MDA.
Okay, and let's see, another question. Can you define SAR for those who aren't familiar?
Well, interestingly enough, yes. The problem is there's so much stuff on the screen I can't see. I had added this slide and then I took it out. But so basically what SAR is that when you have a radar, it's called a real aperture radar. So with a real aperture radar, the radar resolution degrades with increasing altitude. So for low flight aircraft or low altitude platforms aircraft, it's typically not an issue. But it's a huge problem if you've got a satellite 800 kilometers in space. So the way that you can increase the resolution is to fundamentally increase the length of the antenna. But if you have a satellite 800 kilometers in space, and in order to get resolutions on the order of tens of centimeters to meter scale, you would need an antenna with a physical size of 3 to 4 kilometers. So that is just not practical. In the 1950s, a person at Goodyear Aerospace came up with the idea of what's called a synthetic aperture radar. And essentially what a synthetic aperture radar does is that it synthesizes the benefit of higher radar resolution by multiple, it synthesizes that by using a relatively small antenna. So it creates the resolution capability as if you had an antenna on the order of, a few kilometers long, but you're actually getting that higher resolution from an antenna in the case of RADARSAT 2, for example, that's on the order of about 10 to 15 kilometers in length. So that's where this notion of a synthetic aperture radar comes from, because fundamentally you're synthesizing this longer radar antenna to give you this much improved resolution that you wouldn't otherwise get.
That's a great explanation.
Just if I can quickly add, the very same approach is done for astronomy, where they will synthesize like a telescope, and rather than having the aperture of a telescope as a massive dish, you'll have multiple telescopes or whatever is used, and they're in an array. And it's the same idea that you synthesize the benefit of that big antenna without actually having a physically large antenna.
Very cool. Another question in the Q&A, can you touch on SAR's ability to detect moderate to large diesel spills?
I don't know the characteristics of diesel, but if diesel has the same ocean surface damping as oil, then there's no reason why it couldn't be detected. But I don't know offhand if it has those characteristics, if it has that same ability to dampen these small scale or capillary waves. And maybe someone in the audience knows that, but I don't know that offhand. If it does, if it has similar damping capability to an oil slick, then it would have pretty much the same performance as, say, a mineral oil slick. And so your minimum area, is on the order of, half a square kilometer, and with thicknesses to use, going back to the bond scale, thicknesses down to, sheen in those type of thicknesses.
Makes sense. We have a question from our next speaker for you. What is the local time of acquisition for porous?
That I don't know that offhand. It's because of the inclined orbit, it will be variable. So with most polar orbiting satellites, the local time of acquisition doesn't vary that much. When you go to an inclined orbit, you do introduce variability of the local time. So that has some consequences. But in terms of that particular, in terms of the variability of the acquisition times, I don't have that information right now.
Let's see, I think there's one more here. What is SAR's lifetime?
So RadarSat 2 was a 7-year design life, and it's been in space. It was launched in 2007. So that is, if I could do my math quickly, 15 years. So, it could fail tomorrow or could last obviously much longer. The information, what we go on is the metric with RadarSat 1, that was a 5-year design life. It lasted 17 years. So projecting ahead with RadarSat 2, if you're looking at about a 3-time multiplier, you're on the order of 20 to 21 years. And to use the term that was often used for RadarSat 1, RadarSat 2 is aging gracefully, to put it that way. And there are multiple redundancy that is built into the satellite. We are at a point now where I don't think we're down to a single point failure, because sometimes there's 2 to 3 layers of redundancy. So we are good for that point of view. The satellite is performing extremely well. And sometimes the consideration for a satellite is the onboard fuel, but there's plenty of fuel on board the satellite, because every 50 days or so, there's an orbit burn to boost the satellite up to its appropriate orbit. But there's lots of fuel on board. So really and truly, it's probably good for, 20, 22, 23 years, something like that.
Thanks, Gordon. Does anybody else have a question for Gordon? I can't see if there's hands up, Ellen or Elliot. If there's any hands up, can you let me know?
I guess I can stop the share here if that helps.
There are a few Q&As if they haven't already been answered, and looks like they have. I think I heard a couple of these get answered.
Yep.
Yeah.
Looks like no hands up.
Okay, thanks, Elliot. Thank you, Gordon. That was an excellent presentation. And just to remind everyone, this webinar is being recorded. So if you missed part of it or want to go back and watch it again, we'll have it posted to our YouTube once we get all the kinks out and get it polished up. So thank you again, Gordon. That was
Good.
excellent.
Thank you to everybody, and thank you for the questions. And we'll look forward to listening to all the other speakers.
Me too. All right. And just a reminder to attendees, it's easier for me to monitor questions if you use the Q&A rather than the chat, but I am trying to watch both. So just try to, if you pop a question in the Q&A, it's easier for us to make sure we don't miss it. Okay, so let's move on to our next speaker. We're just a couple minutes ahead of schedule now, so that's good, back on track. I'd like to introduce Ben Holt. Gordon kind of gave you a little pre-intro to Ben. He is a NASA research scientist, and he is going to talk about airborne SAR. So take it away, Ben. Looks
how's
good.
that looking and sounding okay?
Perfect.
The weather's sort of messing with my sinuses, so I hope I speak clearly without coughing too much. So thanks, Gordon. That was a good talk, good overview, and hopefully it answers lots of the things that I wasn't going to touch on exactly. And thanks for inviting me to this to be a presenter today. So as the title says, that we're going to discuss our airborne SAR imaging experiences that we've had this last year, actually. And this is work being done by many authors. And for this talk in particular, or co-researchers, my colleagues will be are Kathleen Jones and Karen Ann and Annie Peacock from JPL, Frank Monaldo at University of Maryland and NOAA, Oscar, who's coming up soon, and Ellen Ramirez from NOAA response group. So the focus on half my talk will be about our field campaigns that we conducted last year off Santa Barbara in May and October. And then what was a unique thing for us for the UAV SAR program was a response to the Huntington Beach campaign spill. So the focus will be mostly on our airborne SAR sensor called, unfortunately, with the world's worst acronym, UAV SAR, which would be flying on a drone, but actually flies on Gulfstream aircraft, one of which is based in Palmdale and one in Houston. So this is an L-band system with a 23 centimeter wavelength. So you can imagine what that is. It's about, well, I don't know, a foot, 12 inches or so, something like that. It has a pretty good resolution. We usually use data that's about 5 meters resolution. It has the forward polarizations that Gordon has mentioned. We can fly the same track very accurately, which is not necessarily needed for looking at oil seeps, oil slicks, but it is very useful for one of its primary design features, which is for looking at surface deformation or earthquakes, for example. So all our data, as all NASA data is openly available for the public, is at no charge. And in this case, the data is distributed from the Alaska Satellite Facility in Fairbanks. Okay, so we have a 4-year study supported by NASA. With this title, we're basically trying to move an algorithm, SAR algorithm, into the NOAA response group to assess oil, to try to understand an oil thickness parameter that they can implement. And here's the team. Our actual PI is Frank Monaldo. We have Kathleen and myself, Sean, Lisa, and George, and Ellen from NOAA, Oscar, and Gordon is on one of our partners. We have a partner in Norway, and Dana Toulis from the Coast Guard is also a partner. For our field campaigns that we had, COVID prevented the inclusion of Lisa and George Grettinger in our campaigns, but so most of the effort was conducted by myself, Kathleen, Frank, and Oscar, with Kathleen being our primary person flying on the aircraft during our campaigns. So what we're trying to do is develop a quantifiable approach for measuring the thicker components of oil using SAR imagery. And this will be translated from our L-band system to this rotating the orbiting satellites, as Gordon talked about, which are usually C-band. NASA has an upcoming program for its first satellite-borne SAR mission since 1978 called NISAR, which is a joint project with the Indian Space Agency and NASA, and it will be an L-band system. So we're trying to generate an algorithm that NOAA can implement to looking at the thicker components of oil with SAR. So our system has a very low noise floor, which actually I forgot to mention, I think back here, down into we're very low, minus 47 dB, which doesn't mean too much normally, but it's much lower than any satellite SAR system. And as I will show, that has allowed us to examine the thicker components of oil slicks very effectively and quantitatively. So we had several field campaigns, and we've tried to effectively put together an in situ sampling of this heterogeneous material that we can, over a broad enough area, that we can use it for validating our airborne and satellite observations. So to do this, we have a tube sampler that Oscar has developed, and we're using also Oscar's drones to expand our local area extent. So we had 2 campaigns in Santa Barbara over the natural oil seep area. We were planning to have a 3rd campaign in Norway this coming June, but Norway's plans weren't conducive to our desired goals for campaigns. So basically they weren't leaving their oil out long enough during their controlled experiments. So we're going to conduct a 3rd campaign off Santa Barbara in June this year. And we'll make use of whatever we can put together for our high resolution satellite sensors, SAR plus optical, for effective comparisons and, translating what we see on the surface and from an airborne SAR to a satellite. So our algorithm is basically using the damping ratio that Gordon described, which is basically just the contrast ratio, the ratio of the backscatter from clean water without oil over just a ratio of oil backscatter using a single polarization, in this case vertical, because all SARs have at least one of these vertical or horizontal polarizations. And so we're trying to keep it simple as much as we can. If it's what's called a copolarization were available, then that could be used as well. So we flew, as everybody in the world did, our airborne SAR or satellite system over the Deepwater horizon. And unexpectedly, actually, or surprisingly, we found that we were getting a significant change in the backscatter over what we believe was thicker oil. And you can see that in the center diagrams, graphics, where these the red classified areas are thicker components, thicker oil put together by the underlying ocean wind forcing. And we have, some aircraft, actually photos taken from a helicopter that were quite coincident to our airborne acquisitions. And so this was quite surprising to us, actually, unexpected. And so you can see that result that basically the redder colors had a much lower backscatter than the ocean or the sheen areas. And you can see that in the scale in the center. So this led to a couple key publications. And so since then, we've been trying to understand how we can describe this thicker oil in terms of specific levels of thickness measurable from the surface, basically, how we can best put these together. And here's a map that what we'd like to be able to do with an algorithm from an experiment we did with NOAA in 2015, I think, or 2016, off of Louisiana over the Taylor Field. Okay, so here we have a sequence of 2 pairs of Sentinel-1 images. Sentinel-1 is a really wonderful system developed by the European Space Agency, whose data is also freely available. It has now 2 satellites that were operating until December, as Gordon mentioned, where 1A is still working, but sensor 1B has failed. And this is an extensive program that's supposed to last for 20 or 30 years, where they they replace aging satellites with another copy, so that they can keep these operations going, these acquisitions going from a whole series of satellites, actually, for many, many decades. So from this pair, these 2 pairs, you can see what's happening in terms of the diurnal response from the winds, basically, are very, very important for detecting the slicks. So the pair, let's see, how am I doing? The top pair, the first one's acquired at 6 p.m. local time for O2 Zulu. And in that case, the winds are pretty high in the afternoon, as we all know from local California experiences. And the following 12 hours later, which is 6 a.m., the winds are reduced and you have more spreading of the oil. The oil is, a spread. There's some low wind areas also down in the right-hand corner of the top image. And so you have a lot more oil present, but also it can be mixed with these false positive of low winds and potentially natural biogenic surfactants. So in this second pair on the bottom, you have a similar sequence taken 5-6 days later. And again, the local time of the winds is very important. See if I did, yeah, I did that right. Okay. And platform holly and coal old point are very distinctive in this pair. So the time of day is very important for what we see. So our basic plan for the Santa Barbara campaigns was to head out from the Santa Barbara Harbor, go out towards platform holly, and look for the thicker components of the oil seep areas. In both campaigns, the field measurements were conducted from the U.S. Coast Guard blackfin cutter. This was done with arrangements from Dana Toulis at the Coast Guard, and it turned out to be a really great platform. The Coast Guard were very, very supportive and did just as we asked them to look for oil. When we found it, we slowed down and approached the thicker parts and conducted our field measurements. Here's an example of Oscar's tube oil sampler, which is a pretty nifty little device that you can place in a thicker part of the oil. It has the tubes, the little stoppers are activated and close the oil within the tube. And then he takes these back to measure the thickness. And here you have a couple of great examples of how the oil appears and how it's accumulated into these sort of narrow patterns, narrow slicks within these. It becomes accumulated by the convergence zones of whatever the underlying ocean currents and winds are conducting or doing. So another key thing was using Oscar's drone, which he has a couple talks about later. This carries a multispectral sensor, which produces these local area maps as shown below. For an example, this is a true color image. Here, after returning back to his office, he generates classification maps, which are, one example is shown here, where red is the actionable or transitional dark oil. So, and examples of our airborne SAR acquisitions for May. This is one on one day. We had 2 days of flights. The first flight is at the top of our 1 day, and then 3.5 hours later, we fly repeat observations, repeat flights about every 20 minutes. We just circle around and fly the same track again. So we have this really nice time series over a few hours of the evolving seep appearance that we measure, as often as we can from the surface. In this case, the winds were just 2 to 3 meters. This is another day. I think it's the second day, May 12th, where the winds are even lower, and you have this large expanse of dark seep area, which are probably combined with low winds as well. So it's very challenging under these situations. We have in the lower right corner, we have the expression of a submesoscale eddy, ocean eddy, which is known to pull together especially the biogenic oil, the natural oil that's present from biology into these narrow convergence zones. So in this case, the biogenic oil is acting as a tracer of the underlying currents. So this is the first flight of the second day of our campaign. And then at the end of the day, well, toward the middle, this is the fifth of 12 flights for that day. You can see that the winds have picked up, which mixes the oil into the ocean, especially the lighter components. And in this case, what we think we are seeing is the expression of these multiple bands, dark bands, which are likely what's called internal waves. So these are subsurface waves that are formed from tides. They form along the thermocline, or the temperature and salinity thermocline, just slightly below the surface. And they reach the surface and are able to collect the oil in these progressive bands as the oil moves, the internal waves move closer to the coast. So I guess my cursor works. So over here on the right-hand side, you can see these expressions of the internal waves with not, that are probably containing, again, this natural biological oil, the oil seeps, not the oil seeps, but this surfactants. And in this area off Coal Point and to the west will be the accumulation of the seep area of the natural mineral oil seep into these bands as well. So here's finally one result of our oil thickness classification. This is a blow up on the left with a relative thickness classification map in the center, and a photograph from the ship of how the oil is appearing on the surface. And again, in these bands, these accumulated bands of quite thick oil. In a larger view, we have another classification where, in this case, Kathleen took basically a histogram of the backscatter of the damping ratio and separated these classes by percentages. And so you come down to the thickest oil has a fixed percentage in terms of the histogram. And on the right is an enlargement that also has Oscar's drone map superimposed on it. And I think the next slide there, you can see how his classification, this is a true color version, and his classification of actionable oil works out pretty well and seems to match up quite nicely with the UAV SAR. Okay. Now, a similar algorithm was run with the Sentinel-1 that was not quite on the same day. I guess it was actually of this campaign, and you can see some preliminary results in this case of the thickest oil, which is colored blue. Here's an enlargement of that. So that seems to match up pretty well. It was slightly different time of this acquisition from space with our field campaign. Okay, so we're basically, this is a summary of our Santa Barbara work. We're trying to figure out the thresholds where we can separate cleanly the sheen from the sheen and thin oil from the thicker oil. We have to, in terms of backscatter and range of wind speed. So this is what we're continuing to strive for. We're making good progress with our field measurements. And what we're planning to do next is for our third campaign is to look at higher winds. So we're going to start our programs a little later in the morning, more towards noon than before when we were starting off about 9 a.m. local time. So we're hoping to get a little bit higher winds and try to understand our, how we're doing when the winds pick up and we have actually the less presence of oil, but hopefully more comprehensive results. So sorry, I'm a little bit slow today. Anyway, I'll briefly say that for our Huntington Beach experience, we collected, this is our aircraft plan. We sort of, the gods came together for us. The airplane was available. People were available to help plan everything and to fly. So as the spill progressed, we put together a acquisition plan based on the observations that were being provided by NOAA. And this is our plan. We flew the aircraft on October 6th. Actually, it was right around midnight local time, so it, or UTC time. So it sort of translates into the next day. It was in the afternoon, or actually, but UTC wise, it spilled over to October 7th. And our plane is not operational. So we put together a workflow that's so that we could try to provide this data to NOAA to put into its oil response products. So a lot of extra work was required to do that, and to which I'll talk about briefly too. So this is one example of our collection. You can see Catalina on the lower right with a large wind shadow, and then closer to shore, you can see some expression of the oil spill, the oil slick signatures closer to the coast. Here's an example, a blow up of that same area. We had this plan put together to provide these products as quickly as possible. Again, in a non-operational workflow to NOAA. So that requires not only looking at the data on board our aircraft, which is possible, to sort of prioritize the acquisitions, and the data has to be driven from Palmdale after landing to JPL, and you start the download process from disk to computer. And close to midnight, the jobs were submitted for processing. Early in the morning, some other colleagues came in to start generating the geotiff images, and these were uploaded and sent pretty quickly actually to NOAA. And NOAA was able to use two parts of our acquisitions and generated these products, which they posted on their response website, which is pretty neat. We thought that was quite an accomplishment. And we also posted the data onto the IRMA, the response page, the oil spill response page, which hosts all the data collected during these campaigns during a response. And the blue arrows show the first two observations provided by NOAA of the earliest detection of the spill on October 2nd and 3rd. The red arrows point to our two airborne SAR acquisitions, so they were closer to the coast. And then offshore, is where most of the oil was present. But we did manage to provide detection of oil from the spill in areas that were not observed by other sensors. And again, the time of day seems to be very important, as we actually know, for optimum detection of oil. Okay, so sorry that was a little quite a disjointed talk. But we managed to respond for the first time ever to a spill response and provided the data to NOAA. And significant acknowledgements to Dana Toulis for providing the Coast Guard cutter for our Santa Barbara campaign, and to the support of the flights by NASA to be used for the spill response and for our field measurements, and the UAV SAR team for responding so well to generating these unique products. And we hope to have a couple of nice publications coming out soon, and the implementation of this actionable oil product using satellite SAR at NOAA. Okay, sorry. It was a little bit rough for this morning. I'll be happy to entertain questions.
No apologies necessary. That was a great presentation, Ben. Thank you. I do have a few questions popping up here. So the first one says, can airborne SAR be used at night? What are the requirements and limitations? Unless they missed it.
Yes, it can. We've actually operated, we flew, we fly our plane to Alaska. Actually, we had some unrelated SAR campaigns to Alaska, and that flew over sea ice in December. So we know there's no no problem with that. So yes, functionally, it can operate without any issues at night.
Great. Okay. The second question says, how do the numerous kelp beds present in the inner offshore areas register on these types of imagery? Do they just show a dampening of wave roughness, or do they actually show up?
That's a really good question. Actually, we've obtained some kelp maps from colleagues at UCLA and Santa Barbara that have been derived specifically for kelp. So we plan to overlay those to our within our airborne SAR acquisitions to isolate the kelp beds from the oil seeps. But in general, we think that the kelp beds also produce a dark signature, but that may be not always the case. Similar to a signature, similar to a seep, the seep areas, that may not always be the case depending on the wind, where it's possible, we think that actually there might be an enhanced backscatter over the kelp, as is seen actually with sargassum in the Caribbean, which because the material actually extends above the surface of the ocean a little bit, the kelp leaves and the sargassum, and it actually provides an enhanced return. So it can be, we expect it to be actually both brighter than the surrounding ocean, and also darker than the surrounding ocean, similar to a seep.
Well, thank you. Another question, can you tell us a little more about the L-band system?
So L-band has been flown, let's see, I'm not sure if I'm starting off in the right direction. Perhaps utilizing the L-band system. Maybe that's the more pertinent question. So this is it's a NASA system that can be requested to be used for science, which is and it actually is also used on occasion for disaster response. There are costs associated with it, which are usually can be supported by NASA. Let's say, you know, it doesn't cost. There is a cost to operating it, it can be, I guess technically it can be hired, but the costs go up. Let's say by a non-NASA agency could request the acquisitions, but generally it's used to support funded NASA studies, and the costs are built into the grants, generally speaking. I don't know if that's what the person had in mind.
We'll have them ask a little more specific if there was something else they wanted to know. The next question says, is the aircraft dedicated to SAR, and how long to get airborne for unplanned missions? These two platforms are generally dedicated to flying our UAV SAR programs. However, it turns out that the one in Houston is actually used by astronauts on occasion. So, but no other sensor is flown. No other sensor is flown on these aircraft, and that's because there's the navigation system and the radar system itself are such that they takes up most of the space and design of the SAR system itself. So so it is a really it's a dedicated platform for the airborne, for this airborne SAR. Okay, and finally, how long does it take for data processing to estimate slick thickness?
Well, that's a good question. Again, we're not operational per se. I think this was probably the quickest we've ever processed data from our aircraft in a way, because we were flying local, the processors at JPL. The algorithm, once it's working, we think it will be, you know, quite fast. So, you know, once it gets going and an acquisition comes in, we should be able to generate the classifications in, you know, 15, 20 minutes, similar to what NOAA generates it generates a wind speed product from airborne, from the satellite SARs. And I think that happens fairly quickly once you get the data in hand and in proper format. Hope that answered the question as well.
I think so. That's all the questions we have. So thank you so much, Ben.
Okay, sorry I was a little disjointed today.
No, I thought it was great.
Thanks for having me.
Thank you so much for being a part today. And we have one more speaker before our first break. And, you know, if we go we're about 4 minutes behind, we can cut into the break a little bit because they gave us 20 minutes. So I'd like to introduce our next speaker, Dr. David Chenault. David, you can go ahead and share your screen. He is president of Polaris Sensor Technologies, and he's going to be talking to us about Pyxis.
All right, can you see me and hear me? All right, here's a little view, I think. I may be on.
I see you on camera.
Yeah, there we go. All right, I'm going to turn that off because nobody wants to see me. Yeah, thank you. So I think that you, I'm going to give you full credit, Annie, for planning these talks in this order, because we started with Gordon and at satellites, and then we went with Ben to airplanes. And so I think that what we're going to do is we're going to go down a little bit lower with the latest in Pyxis, and it may address a slightly different aspect of monitoring and spill response. So here's what I'm going to talk about. I'll just jump right into it. So for those of you that haven't heard me talk about this before, what we're exploiting is we are exploiting polarization. Of course, you've heard that a lot this morning. In the case of what you've heard from Gordon and Ben, it's a radar system where you are actively emitting radiation, and the antenna produces, it makes that radiation polarized. What we're looking at here,
Hey,
shorter
David?
wavelengths. Sorry?
Sorry, we're not seeing your presentation. Were you?
Oh, no. Okay. Did
There you
that do
go.
it?
Yep, thank you.
Okay. All right, very good. So what we're doing is we're looking at passively emitted polarization. So we're looking at polarization that is in the thermal infrared part of the EM spectrum. And the thing that we're taking advantage of course, is the fact that anything that is at room temperature is emitting radiation. So in the case of oil and water, what we're doing is we're looking at actually refractive index material differences in between the oil and the water, rather than temperature differences. And so it's that phenomenon that we're exploiting. And you can think of it, again, it's in polarization that's in the environment, not emitted from an antenna. And so you can think of it like you're putting polarized glasses on your infrared camera. The advantage is that we can also get the thermal information, and I'll show some examples of that. But because it is passive and because we are using optics here, it's probably best suited for closer ranges on class 1 UAVs, for example, or for fixed or even handheld applications. But it does give area coverage, so it's not a point detector. It does give area coverage. And the physics works out that it provides optimal detection when you're looking obliquely to the area, as you can see here. And the output is real-time video. So the algorithms that we've developed that exploit these material differences enable us to look at the oil directly. All right, and I'm kind of confused. Which screen am I sharing? Am I sharing my the PowerPoint or the?
It looks like you're sharing your PowerPoint. Yeah.
Okay. All right. Good.
I see
All right. So yep. So we'll move on. All right. So the demo and testing opportunities that we've had to address the kind of the low visibility or the difficult conditions have been, we haven't had a lot of them, but we have had some opportunities at OMSET, and we have had a few that I'll talk about. These are the main test opportunities that we've had several years at OMSET, sponsored in part by ExxonMobil. We've been to Mississippi Canyon 20 to look at the Taylor Seep. We've been to the Santa Barbara Seeps, and we had an opportunity about a year and a half ago to look at a spill in Delaware. I'll show some examples of that. And we've recently deployed a fixed site version of this onto a transfer vessel in the Gulf of Mexico. And I'll show some example data from all of these. Testing in fog has been difficult for us. We have really only had one opportunity to do that. but I'll show that. But the overall capability is that we are able to detect these phenomenologies in the daytime and at night, and it's independent of sun position. So we're not subject to any kind of glare or any kind of sun angle dependence. And it's actually also wave position independent as well. We have looked at a handful of different hydrocarbon materials. So crude oil, refined oil, diesel, and kerosene are all detectable with the sensor. And it is effective in both calm water and waves, as you'll see here in just a minute. And we actually have also looked at emulsified fresh oil, emulsified oil, and oil subject to the action of dispersants. So there's a very real potential application for this during a spill response during the application of dispersants to kind of monitor the application of dispersants in real time. And it does reject false positives. Somebody mentioned kelp a few minutes ago. We actually have seen that we do not detect kelp. So that's really just kind of the hardware and the overall capability. I'll dive into some of the results. So some of the testing that we did several years ago at OMSET was an overnight test, and the activity here was to look at two bins of oil in a fast tank next to the tank. The action of wind, of course, blowing oil around the tank overnight was just not very doable in terms of a long-term test. And so we put it in a fast tank on the side of the OMSET tank and looked at two bins that contained one very thick oil, 5 millimeters, and a 0.5 millimeter on the right hand tank, and collected imagery about every 10 minutes from mid-afternoon to mid-morning. And this shows the time-lapse version of this. What you see in the upper left is the visible image. The thermal image that comes from the thermal capability of the camera is shown in the middle, and the polarization piece is shown on the right. And so you can see what we're sensing. In this particular case, the oil is represented as a very dark signature in the water background. Along about now, you'll see that the sun is going down and we lose the visible feed completely. And yet both the thermal and the polarization are essentially unchanged. What you will notice, though, is that the thermal imagery, the thermal samples are actually looking an awful lot like the background. And that's what's represented by the red curves on the bottom. It's just kind of a simplistic metric to show the contrast is really kind of goes away in a couple of places. And the polarization continues to maintain its very strong contrast with the water background. You will see reflections of clouds in the polarization image that crop up occasionally. This is actually something that that I'll address a little bit later on, and is an issue for us when we get into sensing in fog. Sun's back up now, and again, the thermal is just shows very low contrast. Now, in this particular case, you kind of know where to look. In this particular scene, in these several frames right here, you'll see the moon reflected and the oil heating up in the thermal image. But again, the polarization remains pretty constant throughout, and that's what we really want to take advantage of. Again, here's just a couple of snapshots. The thermal is essentially zero contrast in several of these areas at 1527 and 757 for the thinner oil. So that's what we're trying to overcome. Here's another example. This is what we call a baby pool demo off our parking deck in the back of our office. This was done somewhere around 11 o'clock or midnight local time here in Huntsville. You'll see the guy there is about to inject oil into the pan in the middle. Obviously, the visible image on the left is we turned out the lights in order to inject it. And this shows our detection software finding the oil slick in the little container there in the middle. it turns out that we grabbed some freshwater river reeds, and that's what these objects actually are here in the pond. You can see them here now that we've turned the light back on, the external light. So you can see that our algorithm is rejecting the oil detection. This is a plastic bottle showing up very well in the thermal image, which is the gray levels that you see here, but is not being detected by or highlighted by the detection algorithm. So nighttime, we've got that covered, but there's other low visibility conditions that I think that many of you are probably more familiar with than I am. In the case of waves and in situ, when you don't actually have nice blue swimming pool color to compare or to look for the oil, I think the visibility goes away pretty significantly, even in the visible. Certainly in the thermal, under the action of waves, the oil is kind of mixed and tumbled about, so that the thermal signatures, although a little bit visible here, I would argue that the polarization is significantly better, makes it significantly more visible. And then what I'm showing here now is what we call our E-therm image, enhanced thermal image. So basically what we've done is we have fused the polarization image with the polarization, because we are in fact getting both at the same time. And the thermal does in fact offer some situational awareness, some context for this image. So it's useful to use that in many cases. And the E-therm images enable us to capture the detection by the polarization and put it in the thermal context. So these are actually breaking waves, which I think are probably make it pretty hard to detect the oil. This was from an underwater release at OMSET, and I think this is probably more indicative of color of the of a real world example. Again, you'll see that the visibility in the visible part of the spectrum is not very good at all. The thermal, you can see it, but the mixing action of the waves does tend to make it a little harder to see. And again, the polarization helps all of that. And then one last example here in OMSET. This is emulsified oil. So this is oil that was prepared over the course of several days. And while it's very visible in the visible image in the IR, of course, it's actually quite difficult to see. And again, in all of these cases, this type of detection is effective at night as well. This is an example of the Taylor Seep. So that's the visible image. And while we don't detect thickness differences, once we reach our threshold, we do that identification, do that detection. And you can see the sheen visually here. And you can see that our detection is pretty much in the middle of that area. And so we are detecting the thickest part of the spill. So in fog, again, we don't do as well in fog, but any optical technique is really going to suffer in fog. And so the thicker the fog gets, the more we lose sensitivity until ultimately we don't have sensitivity. But the key thing that's going on here is that we're actually get a reflection of the fog off of the scene that is in direct view. So we don't need a thermal difference in the scene, but we do need a thermal difference between the part of the environment that is shadowed into the scene in order to detect these material differences. And so the fog is essentially at the same temperature as the scene that we are measuring. And so that's why we have reduced sensitivity. We haven't really had a good opportunity to measure that. We've only had one opportunity to measure that. But through modeling, we believe that we can see down to maybe about what the aviation folks call Cat 3 conditions, where the visual visibility is about 300 meters. The IR window remains high through Cat 3. And so we should be able to do that. But again, we really just haven't had the opportunities to test that. With the one exception of the leak at Delaware Beach in October of 2020. We had the opportunity to respond. We got there a little bit late on the response, but the third day of the response, it was still foggy. And you can see that the visibility is actually much less than 300 meters that I just showed. And so we were pretty much grounded for that day. But the following day, it cleared up nicely. And this was the kind of detection that we were able to do along the beach. The visual scene, of course, is on the right. The Pyxis output is on the left. And what you can see is the tar balls that we're picking up that are in the visual are essentially indistinguishable from some of the other debris on the beach. This is incidentally the lower left shows the PDF of the output from this, which can be disseminated pretty quickly after the flight. And in fact, this, speaking of deployment opportunities here, or deployment options, the unfortunate name of Oscar, or fortunate name maybe, depending on how you look at it, for oil spill cleanup and response system is the system where American Aerospace has integrated the Pyxis onto their drones for spill cleanup and response. And in this particular case, we have real-time streaming from the data of data from the camera, and it's actually displayed on the pilot's display that you can see right there. It is configured so that he can capture the PDF data that we just showed and disseminate it further. There's also a few controls over the algorithm so that he can adjust the sensitivity depending on the situation. Some of the reporting capabilities are the drone identity, the heading, the timestamp, the GPS of the aircraft, not of the spilled area, but of where the aircraft is. That's an upgrade that's coming, and the altitude. And it's pretty easily deployable. It's a couple of cases, and one pilot is all that's required for the Oscar. Again, here's the kind of information, and we elected to do this as a PDF that can be easily emailed or even texted around. We also have a handheld version that can be deployed, and in fact, this scene is a different scene of Santa Barbara, the Santa Barbara Seeps, that was acquired with this device in this configuration, flown from a helicopter. So this was one of the first in situ measurements that we made, and it was done by basically hanging out the window of a helicopter. We also have fixed site capability as well. So so basically you take the camera that's shown here, and you either put it into an environmental enclosure or place it on the top of a mast. We have taken some of these same detection algorithms and incorporated into what we call pods, the Polaris Oil Detection System. And it's really intended for long-term monitoring, and is set up for sensing recoverable oil in sensitive areas or areas of concern, such as when transfer operations may be going on, or along pipelines. There is the ability to define user detection zones, and then a user-defined track for a pan tilt unit deployment of it, and then of course do the alarming. And we have a couple of different housings right now. With the picture here on the bottom right shows the explosion-proof housing for explosive environments, but we also have just a more slightly less rugged version for deployment along waterways and things like that. So here it has been deployed on a transfer vessel out in the Gulf of Mexico. Here's the picture of that. The pipe here is transfers oil for about 20 to 24 hours to fill up this tanker vessel, and the pod system is able to autonomously monitor that through the night, which basically frees up a man at this point. The Annunciation is remoted to the control cabin, and in the current Annunciation is basically just red flashing lights and an audible alarm, but it's also possible to do texts or emails. And then there's a kind of a black box capability of recording a minute or so prior to an event, and then throughout the event, and then post event for several minutes. And again, we're looking at detection of recoverable oil around 50 to 100 microns. And the user display looks something like this. It is possible to have multiple sensors lined up over here. In this case, we are only showing the offload video. When there is an event, the video will switch to the sensor that is detecting a spill. The video display is there. Pan tilt information is there. This is the full extent of the pan tilt unit, and the gray area shows the actual sensed area. And then there is manual control of the pan tilt unit, which can be used to set up some tour stops so that you can you can basically outline what this gray area is, and if there are any keep out zones that you don't want to do any detecting in. And so the operation is that the camera moves throughout this field of regard. This is the field of view that's displayed by the camera, and then the field of regard is the gray area. And if there's a detection event, then the user interface turns yellow, and then does a handful of false alarm rejection routines to make sure that you don't shut down an operation for a false alarm. And then after some investigation, it does an alarm, as shown here. So those are the ways that we can deploy this thing. There's always the question that comes up about where do we put this? How far can it see, and how much oil can it see? So we've developed a tool in Excel that is readily shareable that allows us to basically lay out how this thing will be deployed, either primarily for fixed sites, but could also be for handheld use as well. So again, we use the parameters of our threshold detection between 50 to 100 microns. It turns out this is the thick end of rainbow. And we use that in order to establish how far we can see a given volume or area of oil. And of course, it depends, like any other optical system, it depends on where you are, how high you are above the water, and what optics you have on it. And so this kind of gives an example of some of the standard parameters. I'm going to take up just one moment, if I can, and turn on the video, and I'll show you. Actually, I'll wait till the end to do that. So anyway, we have several different focal length lenses here, 40 and 20 millimeters. I'll show examples of those. This shows the field of view. You select the downlook angle based on how high you are above the water. And these show the ranges of these the footprint of the image on the water. The orange shows the 20 millimeter lens with the 30-degree downlook. The blue footprint shows the other one. And given those parameters, you can see that the range from the camera to the field of view in the center, this red dot right here, is about 157 meters. For the blue, I'm sorry, I got that backwards, is about 60 meters to the orange one, 157 meters out here. We're looking all the way out here at about 300 meters. The area that we can resolve based on the thickness and the pixel spacing is given here. So this is about 11 square meters here at the top of the field of view at the longest range. Near the bottom of the field of view, it's about 1/3 of a meter, and at our minimum threshold, that corresponds to less than 1/20th of a liter of oil. So it's really quite sensitive. So some of the planned upgrades, I'm getting a little long here, I guess, and I don't want to be the reason we can't go and break. But some of the planned upgrades we're working with American Aerospace, and we are enclosing the camera and adding a zoom lens to this gimbal right here. It's intended to be modular and platform independent. So we're planning on putting this on both Class 1, Class 2 UAS, and they also have an Air Ranger UAS that's a fixed wing for much longer flight times and ranges. Some of the upgrades for the pods that we're planning, we're going to add just some generic information such as georeferencing. We're going to add the type of area and volume estimation that I just showed in our installation guide into the direct readout for the pods. Adding tracking, it turns out that oil moves around, something that we really should have known and should have taken into account in our original deployment. But we're actually just going to go ahead and add the tracking to it so that we can see where it goes once it's detected. We are going to also develop a portable deployable system. You can get basically a 30 to 40 foot mast and a backpack, and couple that with a laptop and a environmentally ruggedized housing. You would be able to have a man-portable version of the Pyxis system to work in a response. Well, and actually, one of the biggest problems that we've come into is how do we confirm the operation, because it's difficult in a situation like you see here to actually deploy oil. You don't want to dump oil in the environment. So we're looking for materials that mimic the action of oil or are lubricants that are biodegradable. But it's actually been because of the real robust false alarm rejection, it's actually been quite difficult to come up with a good solution for that. So I think I've hit all these points, but basically for, again, I think for the closer ranges for somewhere below satellite and high flying aircraft, we offer another way to do oil detection. The polarimetric thermal together, I think, provide a different sensing modality that is complementary to the radar. And may be more accessible in response or perhaps in situations where you have sensitive areas or places that are prone to a spill or a leak, maybe over short periods of time. Then deployment of the Pyxis is a little more doable. And I think that's it. So there is a paper coming out at the American Petroleum Institute Pipeline Conference in about another 2 or 3 weeks, and so I'll be presenting some more of the offshore deployment and the autonomous monitoring at that conference as well.
Great, thank you, David. I just realized, I know you've spoken at our broader workshops in the past, but I've been redeployed during those workshops. So this is the first time I've heard your presentation on Pyxis. It sounds awesome.
Good.
I do have some questions in the Q&A for you. That hopefully we can get through these real quick. How quickly, you kind of addressed this already, but if you have anything more to add, how quickly can this technology be mobilized and deployed if called out to a spill in California? And is there post-acquisition processing time? Like how long would it take for Unified Command to have something useful in their hands?
Right. Yeah. So basically it's, well, let's see if I can do this. Turn on the video. So this is the camera. And so the handheld version basically screws in right here. So basically, and this is with a slightly different lens. This is the 40mm lens that sees at a longer range. So basically it's however long it takes me to get across the country with this thing. We have a tablet that is can be held in your hand, and so it's really quite small for the handheld version, for some kind of a mobile deployment like that. The mass version is something that I think that is intriguing and is really just relatively new for our thinking. It might take a little bit longer, but it could still probably fit into checked luggage on an aircraft, for example. Once on location, it's really just a matter of about 15 or 20 minutes. The UAV version might take just a little bit longer, but it's still quite rapid. In terms of getting the information out, the drone version of the sensor, we actually have this PDF that has key information, location, look direction in both the visible and the polarization, the E-therm image. And it's a PDF, and if you have a hotspot on your phone and self-service, then that can be disseminated immediately.
Cool. So the next question is, broadly speaking, can this polarization and E-therm imagery technology be applied to still images, such as those collected by camera traps used by hunters and researchers?
Yes, absolutely. In fact, we actually have two video versions, one at 30 hertz and one at 7.5 hertz. The lower frame rate is advantageous because it's less data to deal with, and it's also more readily exportable to foreign countries as well. The camera operates in video mode, but there's no reason that the collected data or the reported or disseminated data can't be treated as snapshots. So yes, that's not a problem at all.
Awesome. And the next one says, can the handheld option be used by a person on a boat at night looking for a slick?
Absolutely. Yes. I mean, the handheld version is really well suited for that. It is an optical system, and so the higher up you are, the better. But other than that constraint, if you can get up as high as you can, then it would work just fine.
Awesome. How about its ability to be used for detecting oil on wildlife?
We have asked that question ourselves. We don't really know. I think the answer is yes, but I'm not sure if it would be distinguishing enough from the thermal image. The short answer is I don't know. We would love to get an opportunity to try, but I'm not exactly sure how you go about do that testing. But if I'm happy to look into it if somebody has some ideas.
Okay. Next question says, there's a little confusion about one of your statements in your presentation about whether the sun angle matters. Is the polarization's greatest effect at an angle of 90 degrees to the moon or sun? And does the camera automatically adjust the polarizing filter orientation to maximize its effect?
Yeah, that's a good question. So the sun glint that we see and can filter out with our polarizing glasses is in the visible part of the spectrum. We are operating the thermal part of the spectrum, so we are only looking at the emitted light. and there's a nuance here that I won't go into, but generally speaking, we're only looking at emitted light. And so we only see polarization that is emitted from the water and the oil. And so the sun angle truly doesn't matter. And the angle of the polarization is only dependent on the relative angle between the camera and the horizontal surface of the water. So, so we actually effectively don't see the polarization from the sun or from sky shine or from the moon. And I can if I guess that came from Mike Donnell, and Mike, reach out to me if you'd like to go into that some more, because it's a subtle point for sure.
Great. Any plans for potential underwater use?
So this, because it's thermal, it's only a surface phenomenon on the water. So there is absolutely, we cannot see anything with this camera into the water or underwater.
Awesome. Thank you, David. I think there might be a couple more questions in the chat if you have a chance to go in there and look, but I'd like to give us a little break and not get too far behind. So thank you for your great presentation. And I'm going to give us 10 minutes instead of 20, and we'll come back at 10:20.
Very good. Thank you. Thank you, everybody. I appreciate it.
Thank you so much.
Hey, Annie, this is Lisa. Can you hear me?
Yeah.
Can I just do a quick screen share just to make sure we won't have any? Yeah, let me just real quick.
Trying to throw a timer up and I'm struggling.
No problem. Let me see what I can do here. Can you see? Can you see my presentation now?
Yes, I can.
In the regular way you're supposed to see it?
Yeah, it looks perfect.
Okay, cool. All right, I'll take it back. I'll stop sharing. Thank you.
No problem.
I've had a last minute, like, oh crap moment. What if it doesn't work?
Yeah,
Okay.
I know. I've had a few of those this morning. Okay, let me see if I can figure out how to share this. So you got a cup of coffee or took a little jog? I'd like to introduce our next speaker, and that is Lisa DiPinto. She is a senior scientist at NOAA's Office of Response and Restoration. I'm going to stop sharing so she can share. And whenever you're ready, Lisa, go ahead and take it away.
Okay, I'm going to share now. Can you all hear me?
Yep.
Okay, so let me just pull this up and get us going. Can you see my presentation?
Looks good.
Okay, great. Well, thanks everybody, and thank you, Annie and Greg and everyone for inviting me to this workshop. We'd love to reach out and communicate the exciting science we're working on. And I'm going to focus on some of our remote sensing work. We've done a little bit of work in not overnight work, so I'll talk about that a little bit. I'm going to be queuing up a lot of stuff for Oscar Garcia, who's the expert working on that project. And I'm just also going to talk more generally about some of the remote sensing work we've been up to lately, including some work that we've done in ice environments. So thank you for inviting me. I know there's some people on here who aren't as familiar with our office, but I'm working with NOAA's Office of Response and Restoration, and I'm the senior scientist there. And my role is to conduct coordinate and communicate about emerging tools and technologies that helps our office do a better job to support our mission, which is oil and chemical spill response, natural resource damage assessments and restoration. We have a marine debris division, and we also do disaster preparedness. So we don't have a research budget or any research staff except me. So we do our best to try to coordinate and collaborate to advance our ability to do these things more faster, better, more accurately, et cetera. The broad research areas I'm involved with, generally I work a lot to characterize the environment, especially using remote platforms, sensor packages, remote samplers that can attach to things like ROVs or to UAS, for example. We also do a lot of work to enhance oil spill modeling tools, fate and transport modeling. More recently, we're working in ice environments, and I focus a lot on the shallow surface mixing layer. I was the senior scientist and then natural resource damage assessment case team lead for the Deepwater Horizon incident. And one thing we really learned during that incident was the importance of the surface and being able to characterize surface oil and what lives beneath the surface and how things that are hanging around near the surface get exposed to oil. It's a very biologically active layer, and it coincides with where oil often persists during a spill. And all of our projects have a component that focuses on developing rapid workflows for data processing and making mapping products and other data products to ideally support response efforts and also, longer term products for assessments. So we got our start, or at least I got my start in this kind of area during Deepwater Horizon. Thank you, Jay Cho and Bessie, for funding a project years ago, maybe back in 2017-ish, 16-ish. And it was intended to help us expand the use of remote sensing to meet response and assessment objectives. So again, this was done in the wake of Deepwater Horizon, and we did a series of controlled experiments, including at the Omset test tank. We did some field testing at the MC20 or Taylor Energy oil spill site. You can see this is the Bird's Foot Delta. That was a very actively leaking site, about 1,000 gallons a day coming out of there for years. So we used that to study surface oil. And then we, developed ways to, I mentioned the rapid workflow and mapping products, et cetera. So the thing about this study that kind of we really like, and everyone that hears my talks will hear me say that synoptic sampling is my jam, where we like to do some on the ground or on water validation of remote sensing tools and technologies. So we would be out in a slick in a boat collecting physical samples and close to the on water samples at the same time that a satellite was passing overhead. And at the same time, we would send aircraft up into the air, whether it be a drone or whether it be a helicopter or a fixed wing. So we would have synoptic sampling and be able to compare data from really far away from satellites, to being actually on water. So it all started with this project in the wake of Deepwater Horizon. So we've had several years to continue this work, and we do a lot of calibration experiments. We've done some experiments at indoor aquaria. This is a Bessie funded project funding water mapping. Oscar Garcia, who is on the phone, to do some small scale calibration experiments in small, little 10-gallon aquaria indoors. We did some outdoor tote experiments, in collaboration with multiple partners. And I can't emphasize enough the importance of being able to collaborate, get in-kind contributions, and also be able to fund other entities through, resource allocations from some of these proposals that we got funded. So all of our research is super collaborative. And I can't stress how important that is. But we spent a lot of time doing calibration experiments. This is just kind of an extension of that same project. We did some work on a beach where, this is in St. Pete. And we like this selection because of, the various ground targets there, including grass, highly reflective beach, submerged seagrass, which, you know, has low reflectance like crude oil. And so here we're just calibrating with these panels with known reflectance. And this project was another one of Oscar's project that he was nice enough to invite us to participate in on. And the project report can be found here. We've done a lot of calibration and validation experiments at OMSET. I can't even remember which experiment this is from, but we've been out there multiple times. A lot of times we get a lot of in-kind contributions, as I've mentioned, from our partners. But this is a typical setup where we put out roughly 1 by 1 meter squares with different nominal oil thicknesses. And, you know, here we put some sargassum in there, trying to help us develop algorithms that can differentiate and eliminate false positives, for example, fresh oil, emulsified oil, etc. And this was, we're not allowed to fly drones, so the poor drone had to be suspended overhead with multispectral sensor package. And this is just, you know, an example of some of the different types of output you get, you know, looking, you know, here's the experimental setup in the squares. You know, you can just sort of see what, you know, true color looks like, or, you know, we can make estimates of oil thickness based on emissivity contrast or false color. Just some examples of the kind of things we've done. We've also taken it out into the field. This is these are images of the Taylor Energy oil spill site back several years ago, where we went out and did some synoptic sampling there. Here we've got a WorldView 2 satellite image acquired. You can see it was around 11:45. We're also out there in a very fancy, very tiny boat, collecting surface slick samples. At this point, we were using Oscar Garcia's water mapping tube sampler. So it was like a kind of a cookie cutter device that would, you know, break the surface, and then you could measure the oil slick thickness that way. And then we were also flying a drone over the same slick from this vessel around the same time, 20 minutes, you know, 23 minutes, you know, within the time of the satellite. And this is an orthomosaic of the drone flight over that slick. And each of these dots represent a place where we collected a physical sample. And then that data and information all gets put together into an orthomosaic oil thickness classification map. So it's been taken to the field too in real live applications. This is some work that we did at a spill in off the shore, off the coast of Louisiana. And we sent out a UAS with multispectral into a very shallow, very fragile, broken marsh habitat. So a lot of SCAT teams couldn't, you know, no SCAT teams could get out to some of these areas without causing damage to this super sensitive, fragile marsh area. But we could get a boat in there and fly around with a multispectral system mounted on a drone and create orthomosaic maps within about 15 to 20 minutes of landing the drone that could be sent back to the command post. And then these oil classification maps might take a little additional time, but, you know, literally within hours of landing the UAS, we could produce these oil thickness classification maps on an actual incident in near real time and definitely in operational response timeframes. We've also employed these systems, you know, on other incidents that I won't talk about. I know that Huntington Beach, it was used there, and we've, you know, we've deployed it on other situations. But I just wanted to give an example and make the point that we are not only doing experiments and calibration testing, but we've got these systems nailed down, and they can operate, be deployed rapidly, and produce data in response operational timeframe. And our calibration work isn't over. We continue with, we've got a multi-year experiment funded by the Canadian Multi-Partner Research Initiative. And that project is being administered by CRRC, or the Coastal Response Research Center. Many of you know Nancy Kinner, and then in partnership with other entities. But we started this project way back in 2019. We've had a bajillion COVID delays, and we've really had to morph the project. But we've done some we've developed a method to create a very uniform surface oil slick in a controlled environment at UNH with some students there and with Nancy Kinner's leadership. And so we plan on publishing these protocols so that others can use these techniques to make a super uniform oil slick to do some testing about accuracy and precision of various estimating and measurement surface slick tools. And then we've got some outdoor tests planned for the onset facility scheduled for this May. So thank you to Canada for the funding for that. And that slide was just intended to show our work to calibrate and continue to refine these tools is never done. And so we're going to keep that up. We've developed some internal documents. George Grettinger, who works with me at NOAA's Office of Response and Restoration, developed this UAS specification document. And basically, he's defined some end user scenarios, either for emergency response, for natural resource damage assessments, or for marine debris, marine debris surveys following, disaster events. But there are these user scenarios and specifications for end users like our scientists at ORNR, who are going to be advising and supporting things like spill responses and assessments. We know about the remote sensing tools and technologies, and this user specification guide helps guide us when we're seeking to procure those services in support of various scenarios. So we are definitely transitioning these tools into operation. We've recently worked with folks at RPI, Jackie Michelle and Jennifer Horsman, have worked with some of our ORNR scientists to develop remote sensing job aids. And I put the links to these job aids here and here. I don't know if you could see my pointer, hopefully, yes. But we have uncrewed aircraft systems for hurricane response and uncrewed aircraft systems for oil spill job aids. And they're really intended to help us guide us and develop standard methods for using these small off-the-shelf quadcopters. These are typically come with built-in cameras in support of, the spill and hurricane missions. And, they're intended to augment your traditional low altitude overflights and, do things like aid and oil spill recon, supplement SCAT surveys, and help you detect and identify marine debris and vessels and things like that, and useful for monitoring before, during, after, hurricane responses. So those are now publicly available, and feel free to download those from the interwebs. And now I want to talk a little bit about some research we're transitioning to, thanks to the Coast Guard Research and Development Center, working with ice environments. So what I've talked about so far and what we've done most of our work on are, temperate waters, but things get a little crazier when you start working in a cold water environment, and especially when you've got ice on the surface mixing with the oil. So we've got a multi-year project funded by Coast Guard RDC, and this project is gonna help us develop algorithms for remote sensing, specifically for UAS mounted sensor packages that can be used to characterize oil on water mixed in a mixed ice environment. And what's glorious about this project, speaking of collaboration, we were able to leverage additional in-kind contributions from Paul Panetta at ARA, who's, I understand, has moved on to a new space-based job. But Paul worked with us and brought his acoustic sensors, that were mounted on an ROV. So we were able to fly Paul's ROV underwater with upward-facing acoustic sensors, looking at oil slicks with broken ice at the same time that we were flying downward-facing UAS-based sensors to look at oil and water and broken ice environment. So there's a little more of my synoptic sampling. And then our third and final was a secondary objective. We kind of added this on at the end. Again, another collaboration with Dr. Brian Gillette at EPA, who developed an air monitoring a sensor system for measuring smoke plume particulates and gases during an in situ burn. So I'll talk, just very briefly about this. At the end of our experiments at CREL, we did a series of 9 in situ burns, and we tested EPA's Calibri sensor and a newly developed miniaturized proof of concept sensor developed by Oscar at water mapping. And so we've got some data and some experiments where we were basically flying drones through smoke plumes. So here's the base test plan. And I'm going to cue this up for Oscar to probably talk a little bit about in more detail. But we grew a sheet of ice at the Krell ice facility. You know, excellent support there from their technicians and scientists and staff there. And then we cut out a series of these 1 by 1 meter squares, and we put varying amounts of oil pieces in there at different percent covers. So we had one square with no ice, and then we had one square, oh, I'm pointing on the wrong screen. We have one square with no ice, and then, you know, we had, you know, sequentially more ice, 5%, 25, 50, and up to 80% ice. And we did emulsified ANS oil on one row, and we had fresh ANS on the other row. And then we had some totes with no ice for calibration here. And then we would sequentially add oil to each of these squares to achieve 9 different oil thickness categories, ranging from no oil up to 5 centimeters thick oil. So we would start with no oil. We would fly the drone with the multispectral sensor and thermal sensor packages overhead, collect 1 round of data. Then we would add oil to each of the squares up to a nominal concentrations of 10 microns, fly around, collect another round of data. Then we would add more oil, and so on and so forth. And, you know, and so we would have 9 discrete oil thickness classifications while the percent ice cover remained constant. So that's the concept of the experimental design. Here's just a real quick, you know, here's what the Krell ice sheet looked like without oil added, and then, or ice added. And then here's, you know, a square with 50% ice cover. And then here's a square with 100 microns nominal of ice, of oil in there. And then here's just a couple of pictures of the UAS system. I put this in because I want to point out that it's the first time that Krell has allowed UAS to be flying in their airspace to conduct research. And to accommodate that, we, meaning water mapping, who was our primary investigator, Oscar Garcia was our primary investigator here, was lucky enough to have to buy an all-American parts-made drone. So he bought the quadcopter Free Fly Alta X with, I believe it's a 7-foot wingspan to use in this project. And it had no problem hosting these downward facing sensors, multispectral, et cetera, polarized high definition video. So it's just, you get a sense of what they look like. And then here's an example of a data set collected with 100 microns of oil. And you can just sort of see the different channels and what they're showing us. And these are high resolution orthomosaics produced for each of the independent channels. And then our job, meaning Oscar's job, was to determine the best combination of channels that would allow us to differentiate between oil and ice and oily ice, et cetera. So we did determine that there's the optimal channels are near infrared, red edge, and red, being the best combination for differentiating fresh from emulsified oil from ice. But Oscar can talk in more detail about his algorithm development there. So that's our downward facing estimation. We also, as I mentioned, this is Paul Panetta's work here. He integrated 6 sonar sensors onto an ROV, the blue ROV2, and he flew these beneath the squares with mixed oil and ice at the same time that Oscar was flying the drone overhead. So we had upward facing sensors. You can see, you know, here's just a comparison. I just pulled this from our report for 2000 microns and 5% ice. You know, we can do some comparisons about what the thermal is estimating versus what the ROV is estimating. And, you know, we note the patchiness of the oil, and we also note that the acoustics work much better on thick oil. And so, you know, we learned about some of the limitations for the acoustic sensors from these experiments. I also mentioned that at the end we did some in situ burns, and we used the acoustics to measure the slick thickness beneath an in situ burn, which I would say is a pretty bold move when you see how much fire comes off of these squares. But this is just an approximate thickness estimation. It's a unitless figure here, but you can see at the beginning of the burn, it's at its thickest, and as the oil burned, your burn time here on the lower axis, you can see the slick thickness decreases as the oil burns off. So it's just another use of sonar measurements for oil slick thickness during an in situ burn. Then we did, and Oscar's, I'm hoping we'll go into much more detail, but we did some time-lapse remote sensing experiments. So we set these up and ran them overnight. And the purpose of the experiment was to collect multispectral and thermal imagery every few minutes over a 24-hour time frame. And you can see we're setting up the experiments here and collecting the data. And, you know, we wanted to study and understand the variability of things like temperature and illumination conditions on these instruments so that you can normalize those ambient variables when you're developing the algorithm. So, you know, we captured the effects of the sun crossing overhead, the sun setting, the darkness, the dawn, et cetera. And the sun, and, you know, all of this is discernible in the temperature pattern over the 24-hour time period. Oh, and you can see here we are, we're looking at kind of an overnight image where there's no light, but we did notice thermal differences overnight, and that the emulsions have higher thermal radiation overnight, so they're easier to detect than the fresh unemulsified oil using the thermal sensors overnight. So we did learn about nighttime abilities to detect and sense oil that Oscar's going to get into more details. And I won't show the whole video, but trust me, just like in life, the sun does come up on this video eventually. And then just quickly, I wanted to mention the in situ burn smoke plume stuff, slightly off topic, but since it was part of the experiments, I just wanted to mention it. This is Brian Gillette's Colibri sensor. It's about a shoebox size sensor. You can see what some of the parameters are here and what the instruments are. And then we put it aboard the larger free fly ultra drone and then flew it through the smoke plume. And this sensor package was one of two sensors carried by the UAS. I'll talk about Oscar's water mapping sensor in the next slide. But as I mentioned, we did 9 in situ burns with fresh oil and emulsified oil. And, you know, Brian then uses these measured parameters to calculate things like combustion efficiency in situ burns. And he's done a lot of work with Karen Stone at Bessie in this department, but we were just taking advantage of an opportunity with our setup to have Brian come out and fly and do some smoke plume experiments. Here's, this is a video of Oscar's sensor. Hopefully it's working for you. But one of the things that this miniaturized sensor package does is it gives you reading in operational time frame and real time, not operational time frame. So this video just shows we're getting real time readings of these particle size emission measurements as the drone flies through the smoke plume. So these conclusions are outlined in a report that's going to be posted, I'm sure, any day on the RDC website. Things that we learned are, you know, that multispectral and thermal sensors mounted, in our case, on UAS, but likely on higher altitude platforms, are able to characterize different levels of oil thickness. We had a detection limit at the lower bound of about 50 to 100 microns. We could detect above 750 microns, obviously, but the ability to differentiate between different thickness classifications was kind of quenched above 750 microns. We were able to differentiate between emulsified and non-emulsified oil. I mentioned about emulsions having higher thermal radiation overnight. We use these systems to characterize ice cover, including our ability to see ice covered with oil. And the ice really complicates these algorithm developments. You know, we're used to working, as I mentioned, in temperate waters. So working in an ice environment, the ice has an effect on the oil temperature and the water temperature that we're going to be figuring out in some future research that I'm going to talk about in the next slide. But our best combination of channels to differentiate between fresh oil and emulsions from ice, as I mentioned, is near infrared, the red edge and red channel combination. We learned a lot about acoustic sensors. We were able to detect the patchiness, but we also noted they're better suited for operations in thicker slicks. So maybe more helpful for, you know, when you're driving cleanup operations. And then we're busily working on our operational workflow for data processing. We are definitely not in the response operational timeframe yet, because I feel like this work is some of the first of its kind, but we're going to be definitely working on that next. So our next steps are that we have year 2 funding from the Coast Guard RDC to bring this work out into a marine environment. We're going to be heading out to Alaska this summer to do some controlled experiments shoreside in those totes. And at the same time, we'll, in the same kind of field of view, we'll be flying the multispectral and thermal sensors over a broken ice water environment so that we can have some side-by-side captures. So we'll be doing that this summer up in Prudhoe Bay in collaboration with Sandia Labs. I'm happy to talk more about that if anyone's interested. And then we're also going to be getting on a Canadian icebreaker and doing some work offshore in a broken ice environment, not with oil in the water, but just to help us do understand more about the relationship between ice and water and the thermal changes associated with that, and to help us do a better job of mapping ice cover. And we also got funding for the National Centers of Expertise to do some similar types of experiments tearing off of these in the Great Lakes environment. So we've got a lot of plans coming up in the next couple of years, and we are, you know, hoping to understand if there's significant differences between freshwater and marine environments. We want to understand our uncertainties and the strengths and limitations under different environmental conditions. We want to advance our calibration methods and get those down and get those, you know, working more quickly. We're going to be working with different oil products. We work with ANS before, but we're going to incorporate diesel into our future work. And again, we're always looking to optimize the workflow to work in operational response timeframes. And then my last slide is just talking about some funding we have from, again, from the Coast Guard's National Centers of Expertise. They're giving us some money to start up. It'll be a very small program, but a little bit of startup funding to take these emerging tools and technology to spills of opportunity. So stay tuned for that. We're going to have a workshop to understand which of the emerging tools and technology we've made an investment in, and which ones we want to be geared up, ready with contracts in place and the proper training for the research teams to be able to jump out into the field in coordination with incident command and with the response to be able to apply some of these tools on actual incidents. So stay tuned for more on that. And with that, I'll take any questions if anybody has any. We still have a minute or so left.
Thank you so much, Lisa. We actually have had to try to tackle spills under ice and under snow here in California, although it's not super common. It is definitely a low visibility issue that comes around from time to time. So that was really interesting.
Cool.
The only question I see so far is regarding the multispectral sensor work that you showed in that picture, that wetland spill. Is that type of sensing able to be done at night? Or what, or I don't know if you've tried it at night or if you have any thoughts on what that would look like.
I think that, well, I'm going to let Oscar answer that, but I won't even, I'm going to let Oscar answer that. I have an answer, but I'll let the expert speak for his own technology. Go ahead, Oscar, if you're there.
That's perfect. Well,
sure. You know, unfortunately, the multispectral sensor, as passive as it is extremely dependent on illumination conditions. And we tested, and even though we have high hopes with thermal sensor, the multispectral is very limited for night imaging.
But thermal?
Yeah.
Yeah, but thermal is, yeah.
The thermal offers, it has a lot more potential for limited illumination conditions and also for very complicated scenarios like ice, presence of ice, and other things.
All right, let me just check real quick the chat, make sure we don't have any other questions. Oscar, since you're already on board, why don't you go ahead and load up your presentation for us. Oscar's our next speaker. He's the director and founder of Water Mapping, and we've already heard your name pop up a few times. So we're looking forward to hearing about.
Thank you, Annie. Do you see my screen?
I can.
Okay, thank you. And I want to say to the audience, when Annie invited me to this workshop, she asked me if I had any cool projects, and I say, yeah, I've been working a lot on ice. And she said, well, there is not a lot of ice here in California, but we have learned so much on these experiments that I feel like they are worth it to share, because actually some of the work we did was imaging these conditions at night. And I think I'm going to try to tie up the work that we did in the context of this workshop. So, and having said that, if we go back to the basic analysis or the basic tools that we use to identify oil spills, most of us are familiar with the techniques related to the aspect, looking at the aspect of the oil, the so-called Bond agreement, which was made more than 5 decades ago, and continues being the foundation of identification of floating oil. This sketch on the left is from the NOAA guide or NOAA Job 8 for oil identification from aerial observers. I think it's a great sketch. It shows the gradient of the increase of thicknesses and how the oil changes its aspect. On the right, there is this famous table from Bond, where it basically declares what will be the range of thicknesses for each of the categories that you can associate on the chart on your left. However, we have to recognize that as good as basic guidance this is, we have to identify the limitations of this. First, well, it's contrary to the purpose of this workshop, because it only works when optimal conditions for visibility are in place. But also, we have seen on the field, you know, we should not be confused by this chart. Sometimes we see dark oil, fresh and emulsified dark oil, to be much thicker than the 200 microns. So we have to recognize there is no limitations only on the way we interpret the aspect of the oil, but also on the way we apply the ranges that this understanding let us use. You know, if we see each of these ranges, the range fluctuates on one order of magnitude. For example, the rainbow goes from 0.3 to 5 microns. And even though 5 microns might sound super small, and what I've seen is that these units are hard to magnify in our minds, because first, well, they are related to liters per kilometer square. But simply think about, for example, think about dollars. So if we have to pay for something, if we go out for dinner to a very fancy restaurant and we ask for the check and we say, okay, how much is my bill? And they say, well, it's between $300 and $5,000. Well, that's not very satisfying for sure. So that alone lets you think, well, it's a $4,700 spread on this category. But if you jump to the next category, then the dollar bill spread is much higher. It goes from 5,000 to 50,000. And the problem here is that we are not even going away from this, from the hints yet. As we get into the darker or the thicker oils, then the spread is even bigger. And not only that, so this guidance for detection stops at a range where the aspect wouldn't change too much more, and you won't be able to judge more if this gets thicker and thicker. So that's why this guidance stops at 200 microns. So this is why, even though it's a good basic concept, it's extremely limited. So, and as I said, so this works only on optimal weather conditions. But something that we have seen, if we imagine this is the ocean and this black or dark stain represents the thickness of the oil, when we are using thermal sensors, we have seen that different from the optical range of reflectances, the thermal radiation has a relationship of how strong will be reflected in relation to its thickness. And well, there is a lot to talk about thermal reflectivity, thermodynamics, etc. But I'm going to try to keep this simple. So something that we have seen, of course, is that depending on the illumination conditions, well, so that reflectivity of thermal radiation will be diminished. So if you see, I'm trying to portray here that there are clouds. I'm going to go back and forth and just represent that. Obviously, the radiation will change depending on the illumination conditions. However, the pattern of reflectance of thermal radioactivity, it behaves the same or follows the pattern of reflecting more when there is thicker oil. And if we go at night, that maintains, even though we get very, very limited reflectances of thermal reflectivity, we still see the pattern of more radiation when we have thicker oils. The problem we have seen is that we can also complicate this more by adding the effect of having ice on the water. And this has been a really interesting learning experience for a lot of people, because well, most common ice conditions occur not on a very sunny days. So we can complicate this much further by adding cloudy conditions, and then the presence of broken ice in pieces that will conglomerate the oil in very different thicknesses. So studying the effect of thermal reflectivity with oil, it's a very complicated process, and that's what Lisa was trying to explain we're trying to do. So what are the factors driving the thermal reflectivity? Well, so the thermal radiation, in this case, we have it from the sun. The thermal advection, which is the heat transfer, has to be conducted by a fluid, in this case could be air or water. And the thermal conductivity as well, which is going to be dependent on the emissivity of the oil and the water. Okay, putting all that in plain English, what that means is that if we want to compare or somehow get a model where we can relate that reflectance independent of the conditions we have around, well, we just have to measure these conditions. We have to see how much sun we had, how much clouds we had, what was the temperature of the air, what was the temperature of the water. And if we can measure those factors, then we can probably understand, well, so based on these conditions, we can expect a higher or lesser reflectivity of the infrared wavelength. We can go a lot on detail on this, but I'm just going to move forward. So Lisa touched base on this point. So we used the grill facility. It was our very first attempt to start investigating this. So our idea was to, as Lisa explained, so to set these squares where we had different configurations of ice cover. At the same time, we've set these toads where we knew we wanted to avoid the reflectance caused by the white surface. So we chose those toads to be black, and then and we set on these toads the configuration of thicknesses as shown in this chart. We use a fresh and an emulsified version of the oil. Okay, I'm gonna move forward. So Lisa explained that we use this super big drone because that was one of the conditions that we could only fly drones that were acceptable for security reasons. But on the good side of things is that this drone had the capacity to have a payload of almost 45 pounds. So we could we use it as a Christmas tree. We mounted on this drone as many different sensors as we could, and with the idea of capture synoptically a lot of data. So this is an orthomosaic of the map that Lisa showed, and as she pointed out, we wanted to observe the reflectance variability on water that had no ice versus how that reflectance variability will be observed when we introduce a different percent of ice cover. And we always had this control where we didn't have ice. All right, moving on. So again, so the way we process the data was, well, we obtained the orthomosaics. The geo-registration is always a challenge, but we accomplished that. And then we proceeded to run known-established algorithms. All of these are algorithms that had been used for other purposes. We kind of expected what could we get from there, and we knew that we had to come up with our own methods to see what will be the optimal method of combining all these bands to get the best results. And this is kind of like the end of the movie. It's not the end of my presentation, but I'm telling you what we were very happy to find. When we were at onset, we found at onset, not at creel, when we were at onset before with no ice, we found that this combination of channels worked very well. So the near infrared, the red, and the green. If we take the same data set and we swap the green channel by the red edge, we get a much higher contrast of the emulsion and the ice and the water. So that was the newest thing we could find on this experiment. So here, if you compare these two, the emulsion versus the fresh oil, there is a high contrast. This is important because if we were in a situation where we have the availability of a multispectral sensor, then we know what will be the optimal selection of channels that will give me the highest contrast to identify or to discern between emulsions and fresh oil and other thicknesses. This goes back to the first chart that I showed, where we know that oil, depending on the thickness, it will affect the aspect. So this is the best combination of channels that will provide you the highest contrast between those categories. However, again, it's limited because it will give you the differentiation of the aspect, but it will be limited to tell you how thick it is. All right. So then we knew we had to look at the thermal data, and here on your left you see the RGB orthomosaic of the tank with all these totes. And if we look at this picture here on your left, it's really hard to see anything from the RGB inside those totes. You almost see that they are all equal, right? I mean, this you just can't see anything. You can see the white ice, even the chunks of ice floating on the squares. Now, if we look at the thermal data and we look at the linear thermal data, so those totes pop up, and certainly they are much warmer than anything else because the oil is doing what it does. It stores heat. Well, we can go into a high debate if it stores heat or just reflects the heat. But anyway, so the point is that we see the much warmer signature of the oil compared to anything. Is when we use a non-linear scale where we can actually, on the same data, we can see other things. So why is that? Because the oil that is not in contact with the water, even though the totes are sitting on top of the ice and this is very cold, this oil is much warmer than anything else. So if we use two scales or two color scales, one to look into the variability of the totes and one to look into the variability of the ice, then we can see two things. We can see the limits of the ice, we can mask off where is the ice, and we can also see some correlation of the thickness of totes. Okay, now if we start looking into more detail about the temperatures of the data on related to the oil, and I have to clarify, these are calibrated thermal sensors. However, we have to understand when we are using remote sensing to measure temperature, there is a huge offset that will be affected by many factors, including temperature, humidity, many other things. So but that's why we call these apparent temperatures, even though they are not precise, they are not accurate, because the only way we can actually measure the temperature is if we have something in contact to it, like a probe, a thermometer, or something that is in contact with the surface. So in this case, we actually saw that there is an offset of 8 degrees at some points, or even more. But anyway, so that's why we call them apparent temperatures. And however, this understanding that they are apparent, it works because at the end of the day, they are going to be relative to each other. So what we did is a very simple technique to mask off the pixels that corresponds to the oil inside the squares, and then we extracted the measurements of what's the highest pixel and the average of all the pixels, and what's the coldest piece of surface inside that square. We did all those measurements, and just to go through one specific example here. So this is an extract of this, probably not from the same flight, but what I'm trying to point this out is that these two squares on the top have no ice. The squares on the bottom have 5% of ice. They both have the exact same, they all four have the same volume of oil, but just the fact that we introduce 5% of ice, the factor of that we are cooling off the water, it makes an effect on how we read the temperature of this square. So even though we have the same amount of oil, if we do math arithmetics around the temperatures of each pixel, we can come up with some volume estimation. However, we have to take in consideration that a given percentage of ice is going to make the effect of cooling off the area where the oil is. So that's why it gets complicated. And then we forget about the ice for a second. Then if we look at the temperatures of the toads themselves, and this was expected. So we see the trend where there is a high gradient of temperatures between some toads and the other ones next to them. But there is a point where the thermal signature gets saturated, and then we just can't see much more differentiation among those thicknesses anymore. So what we did is, okay, well, we look at the variability of that thermal signature, and we look at images with different illumination or different radiation conditions from the sun. We compare early on the morning measurements with noon measurements, and then we see those behaviors on this curve. For example, here, for example, if we look at the thickness of 1,000 microns, the spread of the temperatures early in the morning is much limited than if we look at them at noon when we have the highest radiation. So we knew that, well, this is going to keep happening, right? If we have, are you looking at the oil at noon, on the morning, on a cloudy condition? So these situations are real, and we have to deal with them. So yeah, we did the time lapse, and Lisa showed the video. So we collected data for every minute, basically, over this area. So we were imaging toads with different configurations, and here's the chart of the different thicknesses. And we were just looking at how the temperatures were changing overnight on the square inside. So, well, we have to come up with some programs, develop programs to extract the data over hundreds or probably more pictures, thermal images, to extract data and to put this on this ugly graph here that I'm going to make more meaningful to you. So this just shows that it's all the data plotted there over the time lapse that we were measuring, but this is a much cleaner a graph of what's going on. And on this case, I'm just comparing the same oil as thicknesses go incrementally higher. So as we can see, the 5,000 micron toad, it remains on top of the thinner sheens or thinner oils all the way, even through the night. And here we see the effects of the sunset and the sunrise. And this is just a subset of all the data set, but I wanted to get examples where, yeah, we have cloudy conditions during the time lapse. Then we got snow. We get to get some snow, like half an hour snow at some point. And then we were doing the in situ burning, and that cloud of smoke came through the sensor as well, and that was captured. So anyway, so I'm just repeating myself, but just something that is interesting here is that, yeah, so what I was trying to show on the charts at the beginning of the presentation is that even at very dark night, super cold night, in the middle of the ice, we can still see variability on those thicknesses. But even more interesting, when we compare the thermal signature of same volumes of oil, but now we're going to compare 3 classes. In this case, it was this is the fresh and emulsified oil. This is the 50-50 emulsified oil, and then the 730. Look what happened here. So the blue line, it's the fresh emulsified oil, and when there is the sun present, it's on top. But then it gets inverted when the sun disappears, and the one that is the oil that has the more water content gets on top, and through the night shows a higher reflectance of thermal radiation than the crude oil, and then inverts again, and the oil, the fresh crude oil preserves and goes as a winner. But anyway, so the point is that, yeah, so we observe that emulsions are going to be easier to detect at night than during the day. And guess what? So if we have an oil spill on the Arctic, we can expect a heavy emulsification, because wave action combined with the presence of ice, I'm pretty sure that's going to favor the formation of these emulsions, and for sure it's not going to preserve the fresh unemulsified oil. Anyway, so okay, so going back to the problem of the ice. So okay, so what happens every time that we have more and more ice? Is there a way we can find a relationship between how much ice will affect the temperatures? And we did. So well, and that effect actually is the same, no matter if you're using emulsified versus non-emulsified oil. So what happens here is that, so your horizontal axis here is the ice percent cover of the square. So what that means is that as we are adding more ice into the squares, this is the effect that we have to take in consideration for cooling off the surface of the water or the surface of the oil. This was very interesting because this could help us to then use this relationship to normalize this effect, and then see how well we can calculate the volumes applying this relationship to get the same results, because all of these squares had the same amount of oil. So if somehow we compensate for the effect of the higher concentration of ice, then we should be able to get similar results. And yeah, so without getting more details on ice, I think this is very explanatory of my first slide. When we talk about the aspect of the oil, this is where we are looking at. So remember, so the bond agreement, the aspect of the oil gets limited by 200 microns. So we are right here. So this is all we can tell by looking at the RGB. So when we add the thermal, so then we can expand that limit and see way more. Other things that we found, I have to say, I'm gonna steal a little bit of Kevin Hoskins' thunder, because we did an experiment with MSRC last year in Lake Charles, and with MSRC sensor was very interesting. We did a very similar experiment, and we found that this curve is much higher, obviously, because we were on much warmer conditions. but it showed the exact same behavior. I'm not going to show it because I didn't ask Kevin if I could show it, but maybe he would show it. But anyway, so the effect it is persistent, and no matter if we're looking at oil on ice or oil on tempered waters. So we see that these increments of thicknesses reflect this kind of logarithmic relation of thermal radiation. So what that means is that if somehow we can measure the incoming radiation, the air temperature, and the water temperature, we can use thermal to measure the oil thickness in a more quantitative way, more than just in a qualitative way. Okay, so the conclusions, as Lisa pointed out, is that yes. So if you are on the Arctic and you have a multispectral sensor, this is a recommendation. Use these channels. That's going to give you the highest contrast among all the features that you will be observing, and then that's going to help you to classify more easily what is what. The saturation of infrared signal occurs around 750 microns. Well, obviously, this is going to be depending on which conditions are we looking at, but this refers to the ice conditions. Oil emulsions tend to have higher reflectance at night than fresh and emulsified oil. And this is what I was talking about. So a model for oil thickness quantification using thermal images should include measurements of uplocking thermal radiation, air temperature, and water temperature. And with these thoughts, about 2 weeks ago, I had the opportunity to go to New Hampshire, and we did a full new experiment, super cold conditions. We were at noon, I believe, at 18 Fahrenheit degrees, and we were looking at a similar array of toads, and now we were more prepared. We were having an uplocking thermal sensor, and then all the other measurements for. We had sensors on the water of the toads, and we have sensors that measure the air temperature. We're going to try to come up with a model that will help us to have a better understanding quantitatively of the oil thicknesses. I think that's it for that presentation. Annie, you tell me what to do. Should I stop here or should I go to the other one?
Let's see, you've got about 10 minutes. So if you wanna,
I have 10 minutes total. I can just go. Go very quickly through this and then ask for questions if you want.
Yeah, I only have a couple questions so far. So yeah, if you want to.
Okay, go ahead.
Brush over it, or do you?
It's the same. You tell me.
Why don't I ask you these questions? We'll see how long that takes.
All right.
Let's see. So first one's in the chat here. Does the oil seep or infiltrate into the ice chunks after the chunks are added? What happens to the oil itself with reducing temperatures? Does it clump together?
I don't think I understand the question. Sorry, could you repeat?
It's like the effect of oil. What is the effect on oil when you're adding the ice chunks?
What is the effect of the oil on the ice? Well, that's a good question. Actually, oil tends to hit the ice as the ice cools the oil. So ice melts faster as oil is thicker. I'm not sure if that was the question, but we observed that on the experiment that we did 2 months ago, two weeks ago, where we had all these toads and we tried to introduce the same amount of ice on each of the toads, and we really had to work much faster on the toads that had thicker oil, because the oil warms up the ice much more quickly. I'm not sure if that was the question or if that answers the question, but that's the effect of the oil on the ice.
Okay, well, hopefully that answers, that was Ben Holt's question. And the other one is, I'm not sure if I understand this one. Ben, do you want to ask your question out loud? You can unmute yourself.
Sure. Oscar, the first question, I was just wondering if the oil went into the ice, got absorbed within the ice.
Yeah. So what we did is we set the ice, and then we add the oil, making sure that we capture the oil on the surface without having oil going under the ice. That's how we've been setting up these experiments, and every time we had to repopulate the squares with more ice, we will clean everything with absorbent pads and remove as much as possible, and then we add the new amount, making sure that the ice gets isolated. Sometimes when we had the effect of getting the ice coated a little bit on the surface with the ice, with the oil.
Okay, so does the oil, when the temperatures are reduced, when you add more ice, does the oils tend to change its properties and clump together? Or?
Yeah, so what does, it just melts, and you see on the surface that you are losing cover surface of ice so more rapidly than when you have thinner oils. And so what we did last couple of weeks, we tried to preserve between 40 and 50%. So when the ice will melt up to 40%, we will add more ice to try to keep them on that range. The problem we had is at night when everything was so cold, the whole tote froze. And so it was very interesting to observe the process being reversed. So in this case, ice being melted and then ice being formed around the oil. So it just adds another level of complication here, but well, that's why it is
complicated. So I have this other question mostly for Lisa, I think, if she's available. So there's a lot of studies looking at oil by placing it on the ice and watching it filter into the ice, and also with the oil below the ice. So, and then so the question is there a sense from the responding agencies that a spill would more likely occur within an ice regime, should it occur, will be related to the platforms, to offshore platforms and drilling, or related to shipping, because the shipping is the transport of oil and natural gas is increasing across, and
Hey,
shipping
Ben?
is increasing across the Arctic as well.
Hey, Ben, this is Greg McGowan. The risk assessment stuff, Oscar's only got 5 minutes left for the remaining presentation.
Okay,
So why don't we take that up in the chat side, and Oscar, you've got 5 minutes.
That's fine.
all right. Ben will have the chance to talk more about that for sure. So this other presentation is about a system we developed to quickly produce maps. And this is the process of many years of work. I remember it was 2014 when the first time I flew a drone over the Taylor Spill MC-20. It was 2016 when we flew it at onset. So if we take really 6 years of research, that's it. And if you see how time goes quickly, I'm so excited to see what the future holds for UAS technology, because I mean, 6 years ago, it was the first time we flew it. Now we are talking about having semi-automated methods to do mapping of oil thicknesses. That's really cool. It's been complicated. It's not easy. It's very different to generate maps of oil on the ocean than mapping land. And there is a lot of complex situations here with the geoprocessing of the data. But we have processed that. We have worked through a process where we calculate the altitude, calculate the tiltness of the camera, and we project the stills and we stitch them all together. And we have tested that technique with multiple sensors. And these are the sensors. I'm just going very quickly through all of these. These tools that we have developed are developed basically using ArcGIS and MATLAB, but we have used them in many different occasions with the Coast Guard, with other situations. Here, what I'm showing is the most common technique we use to deploy the drones, and these are examples of how the data looks once we generate those maps. Here is from the most recent campaigns we had in Santa Barbara for the NASA ROSES work, and I'm just going to stop here. Let me see if I can pull this up just to show the level of detail that we gain from this. Oh, I can't see here. How can I zoom in here? It's just that I can't see my controls. How can I close these? No, I can't see my control. Okay, maybe. Okay, so just to show a little bit of the level of detail on this imagery, but so that's the boat, that's the Coast Guard boat, and I like this example because at the beginning we were only working on straight lines, but the problem is that oil doesn't move on straight lines. So something that we managed to do well now is to generate this projection of imagery, even if we don't have a straight flight path. And this is just an example, but I'm gonna go back here. I didn't have an acknowledgement slide, but I want to thank all of my colleagues. I mean, Frank Monaldo is in here with me, next to me, Ben Holt, and all the people from the Coast Guard, Blackfin. It's been an amazing experience, and obviously all the people from NOAA and Coast Guard and the University of New Hampshire that has been involved. So I'm just going to show a few examples quickly. So the way it works, I deploy the drone and we fly. First, we do a monitoring flight where we observe what's the distribution of the oil. Most of the times, I tend to fly towards where the thickest oil is, and sometimes I will ask the boat to move towards where the thick oil is, and then I perform some flights. But these are examples of how the flight lines can be done in straight lines, for example, and that's the rapid classification. I had a video I wanted to show, but that's not going to be possible. But that video shows, where is it? Well, I'm going to have to share this video through the chat. It's in YouTube, but it shows an example of how we process data on near real time. So that shows the deployment of the drone, and then normally I go up to the bridge with my screen. So anyway, this video shows the whole process of how we operate the drones on the ocean, doing tactical positioning of the vessel to do sampling, and also once we retrieve the drone, what we do for process data on near real time. So I'll share that with anyone that could be interested. But yeah, so this system that we have developed, it works. We have put it in action not only for the NASA ROSES, also for the Huntington Beach spill, which I don't think I can talk much about it, but I'm just gonna go to the conclusions. So near real-time mapping has been developed, tested, and used. I think the TRL for this system is as high as I think could be, because it's been used, and I think it's going to be continue to be used. And as I say, yeah, we use these, we generate maps, and they were used in the Huntington Beach spill, shared with the incident command in near real time, or within 20 minutes after being collected. And then obviously the NASA ROSES project, which we are coming back, I believe in June again. We're going to keep using it. So I'm going to stop here and see if there is any more questions. I don't know how much time I have left.
Thank you, Oscar. I don't see any more questions, but good job on getting through that in 6 minutes.
Maybe everyone is asleep.
Yeah. No. Okay, getting some positive comments in the chat. Thank you so much, Oscar. That was
Absolutely, thank you.
And we have one more before lunch, and I'd like to introduce that speaker now. It's Alessandro Vagata. He is Director of Operations for Phototerra Aerial Survey. So, Alessandro, if you are able to share your screen, why don't you go ahead and
Yeah, sure.
over.
Good morning. Can you
Good
hear
morning.
me? Yes,
Yep.
good morning to everybody. It's a pleasure to be virtually with you. And let's see, let's share my screen. Okay, could you see the screen?
Looks good.
All right. So thank you again. And today I'd like to share with you the progresses that we are having with our Poseidon platform, starting from actually 2015 when we started this idea, this project, looking at the needs. The needs of the industry, of the responders, of the operator, of the agency. So what needs from airborne remote system? So one of the needs actually was the expansion of the operating window to low light bad weather conditions. And so we focus on that, like we focus on the other, starting from multiple sensor for complementary redundancy of the information, classification of the pollutants, no false positive, identification of oil target as recoverable or not recoverable, georeferencing of the information, real-time information for the incident command center, a data suitable for the common operating picture for the decision makers. So quickly in 2016, we entered in service with Poseidon. Since late 2018, Poseidon is fully operational. We've flown already about 3,000 hours. We are flying daily, and Poseidon 2 is in progress. Should enter in service in late this year. Poseidon 3 will enter in service in next year, actually, in 2023. So for who's not familiar with Poseidon, what's Poseidon? Poseidon is a mission system based on 3 main blocks: sensors, onboard data processing, and communication. Sensors include far-range detection sensor, specifically the SLAR, side-looking airborne radar, and near-range sensor for the analysis of the spill, including the AOIR for high-definition imaging and thermal imaging, MWR, microwave radiometer, for absolute thickness or spot detection, laser fluorescence for oil type classification, visual light scanner for to support the bond agreement or NOAA code for the oil appearance, and the IRUV for mapping for relative thickness. We have on board the plane a multifunction operator console for real-time processing of all the data coming from the sensors. We have communication system based on a maritime broadband radio, wireless microwave radio, and a satellite link to share the information in real time to the responders. So let's go through quickly to this little boring table, but is needed to understand a little bit more the technology of Poseidon. So Poseidon is an integrated multi-sensor platform. We have 8 different sensors: SLAR, infrared, ultraviolet, laser fluorescence, microwave radiometer, VIS, visual lens scanner, IOIR, and direction finder. We for the far range sensing, so for the synoptic overview of the spill, we use the SLAR, the side-looking airborne radar. The SLAR has a SWOT of 50 nautical miles, 25 nautical miles per side, and just to give an idea, we can scan 7,500 square nautical miles per hour. So we can provide georeference data, and the SLAR is the main tool for the detection, for the first assessment of the position and the structure of the oil spill. So we cannot do anything with a near range sensor if we don't know where we should send the plane. So especially at night or in bad weather condition, if you don't have an instrument like the SLAR, you are completely lost. So the SLAR gives a point of reference where we should start the analysis of the spill. In fact, it allows to determine the strategy, how approach the spill with a near range sensor, give a precise reference for the navigation for the successive overpasses of the aircraft above the spill. And this is one of the sensor that is all weather. So used for night and all weather operations. So also all the sensors actually they have a very high area coverage. As I said, the SLAR is about 50 nautical miles, but the near range sensors, they have a SWOT of about 2,000 feet, flying 1,000 feet altitude. We can go, usually we fly the analysis at 1,000 feet, so the SWOT is about 2,000 feet. Absolute oil thickness, quantitative volume estimation capabilities. The absolute thickness, we have the microradiometer that measures the absolute thickness in the range of the 50 micron 3 millimeter range. The laser fluorosensor measures absolute thickness in the range of 0.1 20 micron range. This is absolute thickness. So then the absolute thickness measurement are supported by the relative thickness mapping with the UV very sensitive, starting from 0.01 micron, and the IR sensitive from 2 micron. So overall, the system allows the quantification of allow the estimate of the thickness and the volume of the oil, and the visualization of the hotspots to allow for the determination of recoverable and not recoverable oil in real time. So being a sensor, we have the redundancy of the measurement. So for example, at night or in bad weather condition, where obviously the V's and the UV are out of the picture, the IR is so and so is very important to have a solid sensor like the SLAR, like the laser, like the microwave that give first of all the mapping, and then a first quantification of the thickness and volume. So oil type identification and classification, the laser fluorosensor allows the identification and classification of the pollutant. So this is, for example, we can identify crude oils or refined oils, diesel instead of algae, chlorophyll, and so on. We have already a database that can be expanded. And this is especially important. Not much when you have a specific spill from a platform, but for example, when you are spill or suspect spill from vessel for ships and so on, because you don't know what it is, where the oil come from. Can come from a platform, come from a ship, especially in the Gulf of Mexico, where there are hundreds of infrastructure, and the shipping is really busy, the traffic. So the laser fluorescence provides as well information on the weathering to support decision on dispersant application or in situ burning or mechanical recovery and so on. So the complete onboard processing on the information. So all the data from the sensor are processed on board on our console. We have one person dedicated. Mostly the process is automatic, but there is still some human intervention, especially to highlight what is the important information to transmit. So the process is automatic, but it's the person to decide, yes, this is the right information send right now to the responder for this specific frame of the response. All the data from Poseidon are georeferenced and can be exported in all the standard GIS formats, shapefile, GeoTIFF, and so on, directly from the aircraft to the common operating picture platform of the Incident Command Center. So, for example, all the hotspots and all the significant targets can be reported immediately on the maps, so the responder they are in their laptop, in their pads in real time. So communication system includes high speed, high capacity microwave data transmission, dedicated, as well as a satellite link used as a backup. So the band that we have with the microwave antenna is quite big, also to transmit video and picture in real time. Low light, all weather condition operation. Again, the redundancy and the complementarity of the sensor allow to extend the operation in low light and all weather condition. Every responders know how important is don't waste, okay, the hours at night. So if at night we keep flying, we keep monitoring the trend of the oil, the drift of the oil, the spreading of the oil. That is extremely important, because early in the morning when the vessel can start to operate, they know already their target, the position of their target. False positive prevention, again, the redundancy and complementarity of the information allow to minimize the false positive and prevent as much as possible false positive. Readiness, the system is ready 24/7. System ready doesn't mean only sensors, only processing, but means also people. So having a system ready means to have a plane ready, a crew ready, the mechanics ready, the operators ready, and especially dedicated pilots and operators specialized for this kind of activity. So we don't improvise putting a sensor in a plane of of opportunity, but our philosophy is to grow pilots, to grow operators together for the specific missions. So the time of location is critical as well. The dispatch of the plane is in general less than 1 hour. Is the time to be location is this dispatch time plus the ferry, but the cruise speed is pretty high. So we can be in location in very short time, 2 or 3 hours from the accident, from the call. We can be in location. Finally, search and rescue capabilities. So Poseidon platform includes also direction finder, FLIR sensor, and the AIS system to support search and rescue mission when necessary. So this a little bit was the boring table, but just to go a little bit more in depth of the capability of the plane, of the feature of the plane. Now let's see what's the typical mission profile for the plane. So the first step for us is the far range detection. So we fly at 3,000 feet, and we identify a target with a SLAR, with a side-looking airborne radar. We define once the target is defined. The operator gives the navigation reference for the pilots, and we start to define the pattern and overfly the spill and analyze the spill with the near range analysis. During this time, we start the onboard data processing after the near range analysis, and we transmit the data we process the data, and we transmit the information still in flight to the incident command. So these are the 3 steps, 1, 2, 3, and go a little bit more in depth. So the SLAR is a cloud penetrating X-band 9.3 gigahertz real aperture radar, and we can have on the imaging the fusion of IIS data for the vessel and platform position, satellite imagery, SLAR data, all in a GIS environment. So the near range analysis, so we have the near range sensor for the accurate analysis of the spill. Each of the sensor detects specific feature of the spill. For example, the visual line scanner that you see on the left side supports the oil appearance codes, the Bond Agreement code or the NOAA or the NOAA code. Ultraviolet, infrared, there are support for mapping, for the area position, the coverage, the relative thickness, drift, spreading, to have a first estimate of the volume. They're sensitive above 0.01 microns, the ultraviolet, 2 microns, the IR. Then we have the microwave radiometer that we use for the absolute thickness measurement. We can measure from 50 microns up to 3 millimeters. So this is for a very thick oil for the hot spots. Finally, we have the laser fluorescence sensor that we use for both absolute thickness measurement from 0.1 microns to 20 microns, plus for the oil classification and weathering. So third step, as you remember, is the onboard data processing. What does it mean, onboard data processing? We want to send to the incident command center science. We want to send to the incident command center information, intelligence. So simple, simple information. Where is the oil? What type of oil is actionable or not? How much oil? How is moving? And the map. So from all the nice sensor images, just we collect all of them in just probably one that to me is the most important. That is the process thickness map. That is a georeference thickness map, color coded, that give us the location of the oil, of the thick oil, of the hotspot, and so on. So what we send to the incident command center is intelligence. How we send with maritime radio, microwave radio, high speed and high capacity. We have a radio link of 15 megabit with a range, optimal range of 70 nautical miles or 3,000 feet. That is the main that is the main instrument. And then as a backup, we have a satellite link, also an LTE connectivity and maritime radio just for verbal communication from the plane. And what we deliver is what you see on this picture. This is an exercise, but anyway, is an incident command center, and so in the middle of the monitor of everybody there is the thickness map. Is the georeference thickness map sent in near real time from the plane to the incident command center for the decision maker to act, to recover, to take their the decision on the specific incident. So this is the type of information that we deliver. Again, this is another example, a little bit more detail of the thickness map, geolocated. This is another image. You can see on the left side a picture from our FLIR camera, HD camera, and on the right side you see the same platform, but surrounded by the map of the oil with the thickness map. So you see on one side you can see visually, because still our feeling is very visual, especially for the responder. But on the other side you have the science. You have exactly the position. Okay, where I need to send the vessel. I give you the coordinate. Where is the black spot? 100 microns. Okay, send the vessel right there. Is an information that you cannot have with the picture on the left side. So when we deliver this information during the flight, we deliver tactical information. So we provide direction to the responding asset, especially location, mapping, oil, no oil, location of the actionable oil, input on the type and number of assets to mobilize for the specific response, support dispersant application or in situ burning, depending on all the factors, thickness and so on, monitor marine mammals and marine wildlife, and search and rescue, scene monitoring support. This during the flight. Then we have strategic information within a few hours, let's say for sure within 8 hours from the overflight. we have the location, the complete mapping, the formal mapping of the spill tracking for the forecast modeling, the spill quantitative analysis with the thickness distribution, more precise volume, oil type, and so on, and the in-situ mapping of all the responding assets. And then we have, for example, the long-term information, like documentation for natural resource damage assessment, the document to document the spill characteristic and evolution, documentation for legal purposes, and so on. So these are the three steps when we deliver the information. So what's about our system? So our system is like is the youngest brother, let's say, of system already existing. For example, in Canada operates already a surveillance program with about 4,000 hours flown every year. The Bonn Agreement probably started this process of aerial remote sensing, airborne remote sensing. They fly as well about 4,000 hours every year. And Spain and other countries in Europe, they started their own program of surveillance. And the outcome is that there is, over the year, has been noticed a consistent reduction of the number and consequence of the spill over the year. It is because the early stage detection is a factor, the readiness of a plane, of a vessel for the response is a factor, and is also because area remote sensing is a deterrent for illegal discharge. So specifically, the system that we use, the Optimare Medusa system, is the latest evolution of a system that has about now is very mature, has about 90,000 hours of operation globally. So from space, mainly from Europe. In our case, since December 2018 up to December 2021, we've flown about 1,140 days, 1,100 missions, about the same inspection flight with 850 oil spill confirmed, documented, 54 emergency mission with 45 oil spill confirmed, and fishing boat also in the area in Brazil. We do also fishing control. So 900 fishing boat located around the 500 meter radius from platform. And so total, we since December we accumulated about 3,859 flight hours. We are right now about 4,300, and up with about 2,876 monitoring hours. So the system. So we started with this crazy dream in 2015. Now just we are mature. We are maturing really a very consistent experience. Even because we are let's say the only commercial entity operating this kind of this system. So yeah, there is some case study. I see Annie. Probably she tell me that the time is expiring. So if there is some question, I will be pleased to answer.
Are you ready for questions?
Yes.
Okay, so let's see. I have two came in that are very closely related. So I'm sorry if you already answered some of these, but the Poseidon is located in the Gulf, correct? Is that...
Right now Poseidon is located in Brazil because yeah, right now it's located in Brazil. We've flown a couple of times in the Gulf, but our client in Brazil, we asked our client in Brazil that to release. They did, because for emergency they release. So Poseidon 2 will be located in the Gulf. So now Poseidon 1 is fully booked in Brazil.
Oh, got it.
Except for emergency, where we can move the plane. Yes.
So and I know you talked about like being able to deploy it within an hour or so. What would your best guess be for an arrival in California if we had a spill? Like, how long would it take?
Yeah. So if so, the idea is to deploy Poseidon 2 in Houma, in Louisiana. So the flight from let's say within 10 hours from Houma, we can be in California.
Within 10 hours.
Yes.
Let's see. I think that might be all the questions I see. Oh, is there any plan in possibly ever staging one of these in California?
If there is a business case, absolutely. Yeah. Absolutely, it will be extremely beneficial because there is the cost, all the cost of California, the cost Oregon, Washington, and then Canada. Canada, they already operate, so it would be a continuity of what Canada already do. And then there is Alaska. And there are no more maybe offshore infrastructure. I mean, in California, yes, but there are not so many offshore infrastructure like the Gulf. But there is a lot of shipping. Traffic, shipping also oil and everything else. So it would be extremely beneficial.
I agree. Well, I don't see any more questions, Oscar. You're like almost perfectly on time. We got 1 more minute till lunch. So unless somebody wants to shoot their hand up, I think we'll go ahead and break for an hour. Thank you again. That was a great talk. And when we come back, we have 5 more presentations with no break scheduled. So hopefully we can power through those and be done at 3:30. If not, you know, if we get a little ahead of ourselves, maybe we'll throw a break in there. But hope everybody comes back at 1 o'clock. All right, looks like 1 o'clock to me.
Just about.
Let's stop sharing this timer. Right, hopefully everybody had a nice lunch and is tuning back in for our second half. And if there's anybody new chiming in this afternoon, I just wanted to mention that if you have a question for any of our speakers, we prefer that you use the Q&A feature of Zoom, and the chat also is open in case you'd like to give kudos or make other types of comments. You can use the chat for that, but we'll try to track questions with the Q&A. I think that's all I wanted to announce. Other than our next speaker, which is Ira Liefer. He is the CEO and Chief Scientist of Bubbleology Research International, and he's got some cool research projects to talk about today. So welcome, Ira.
Okay, thank you. So I'm going to give a talk on the work that I've done over the last 7 years and do it in 20 minutes. So apologies for anything I miss, guaranteed. Stuff will be skipped to stay on schedule. So just to kind of set the stage, I was a happy Seep scientist until Deepwater Horizon occurred, which pulled me into oil spill science, which is slightly higher pressure. Here's a visible MODIS image of the spill, which if we look in the thermal infrared, which is hot, so oil that's thick enough to get hot, we can see there is some overlap, but not great. This false color image, 4 is reflected, and so green or white are indicative of oil.
Hey, Ira.
Yeah.
We're seeing platform sister is rebuilt as sister 2. An image.
Weird. Okay, so it picked, let's see, I think this one.
Picked the wrong screen. There you go.
Okay, yes. We'll get back to Sister 2 in a second. So green is thermal, and I wanted to show this just to indicate how much thermal structure there is in the ocean, which is clearly unrelated to oil spills. Okay, there we go. Okay, so moving from the Gulf to my backyard, which is the Coal Point Marine Hydrocarbon Seep Field, a natural lab for oil spill science. And so the numbers are a few 100,000 cubic meters of gas per day, and several hundred barrels per day of oil, and they are thick. And to just tell an interesting anecdote that I'm going to come back to, relevant to some things said early in this meeting, when I was doing Seep science at UCSB, I used to joke, I love the smell of petroleum in the morning. It smells like science. Later, perhaps not the most healthy thing to have chosen as a way to go about it, even if it's not pollution. Okay. The Coal Point Marine Seep Field covers about, in a box, 18 square kilometers. It's about 3 square kilometers of seabed. It produces oil slicks. Here, what we're looking at is a MACO, which is an airborne hyperspectral imager by Aerospace Corporation, mosaic, and retrieval that picks up on the oil slicks. And one of the, so there are two characteristics that are obvious here. One is that the slicks are aggregating as they go downwind. And secondly, the thick oil components of the slick, which is what is being picked up on in this retrieval, is very thin and narrow. It's not kind of broad features, and that's a characteristic. The spatial resolution of this, I think, is about 20 centimeters. And normally what they use it for is trace gas detection. We work a lot with aerospace. Okay, our experiment, the Seep assessment study, it's SAS. And the goal of this was to provide an in-scene calibration of the remote sensing. So the idea was collect some oil, do it gently, and image it with remote sensing, and use that to calibrate what we saw when we did a survey along the slick. So here's this video, and I'm just going to describe some of the things. So we have two boats. With a boat, we initially deploy the boom in a J configuration. The skimmer, a wear skimmer modified, is offset from the apex. We collapse the boom while the airplane flies overhead, and used a combination of a pump and pool skimmers to remove the oil. We put it in buckets and we weighed it. And for one of the days, which I'm going to show, we actually collected a barrel of oil in 100 meters. That wasn't what I wanted to do. I want to go to the next slide. Here's another. So as I mentioned, one of the things we do is we collapse the boom. So let me start over. J configuration, modified wear skimmer, door closed to the side, sneak up on the oil, pretend it's hostile, and go very gently into it. Once you've captured it, then even the boom, this moves the skimmer to the apex. Don't open the door yet. At this point, we collapse the boom while gently easing it forward. This rolls air into the oil, preventing it from sinking. Sinking oil is what Coal Point Seep oil does after a few hours of weathering. Once it's had air rolled into it in the back and the boom is collapsed, we then open it, open the wear, and offload. And here we can see the other thing, our approach was actually successful at collecting oil up to 8 meters a second wind speed and 5-foot waves. So we had active white capping, very small, inside the boom. We still managed to collect the oil, and it included some of our data set. Right, here we're using a pump to offload the skimmer. which I'll note was custom modified so that when the boom was pulling on it, it didn't pull it apart. Okay, here's a view from the airplane of the oil slick that day. And you can see the white capping oil coming by platform Holly, but not from the platform. Okay, let's go next. This slide was just to show that if the movies didn't play, you can see us sneaking up in the oil. And basically the operators had to very gently go in and out of gear to not go too fast. If you went too fast, then the oil would, you know, jiggered it, one of the captains jiggered it a little too much, the oil would escape from the back and we'd have to start over. Okay, we then took these images and we photo mosaic them. Our resolution is about 20 centimeters on the thermal. Our georectification is to 20 centimeters. We stopped at that point. We could have done better. There is no image stitching. This is a straight georectification. And when we looked at the slicks, the visible had a wider field of view than the thermal. We noticed this cool oil, which at the time confused us. Well, we weren't really sure how to treat it. And so we then, well, went to the lab. And in the lab, we wanted to look at what was going on with this cool oil or oil in general. So the simple way of thinking about it is we have three media: air, oil, water. The oil is black, it absorbs sunlight, but it gets hot, so it radiates and it heat transfers. So it seemed like looking at this, well, how could oil even be cool? But you know, water is cool because of evaporation. So we didn't want to make any sort of assumption. So we went into the lab to do extremely high resolution thermal profiles of oil. You can see the setup here. We're looking at 10 micron vertical spatial resolution. So really precise. We set the surface based on the video camera, high resolution video camera. So we knew where the air oil interface was, but we didn't really know where the oil water interface was. So we ended up modeling things to get that. We did these experiments on two different types of crude, emulsified and unemulsified. Here are two example profiles. So thin oil, pretty straightforward. You basically have a decrease. It's hard to see here, and it's certainly not in our data model, but there's a very thin layer we can actually see. I'll go back here, there, the subinterfacial layer. So we actually resolved this. Thermal infrared energy penetrates a few wavelengths. And so as a result, we actually characterize the emissions and cooling of the oil in that layer that's about 30 microns thick. What was really interesting and fascinating was that thick oil had an internal peak. Now, I got zinged by a reviewer, so I'll be very straightforward up front. Thick and thin refer to optical thickness and heat transfer, not the bond agreement. Interestingly, thick oil is oil that you can do something about, is not sheen, amenable to burning, to skimming, etc. So there is an operational definition of thick and thin oil that matches the physics-based optical definition that I'm using here. Okay. You also can see there's turbulence in the air. We don't simulate turbulence, so we model the data which removes the effect of turbulence. We find the oil-water interface by the discontinuity between the two structures, which is where the transition is. It turned out to be extremely accurate within about 5 or 10 microns. We also had some problems with dealing with what was happening at this lower interface, because you get weird turbulence in our tank, a little bit unnatural, and we really didn't want to model it. But the characteristics are the same. There's a cooling of the air to the oil surface, which is warmer than the water underneath in thin oil, but in thick oil, it actually warms the air above. Okay, putting all these together, we find there's an asymptotic behavior between thermal contrast, capital delta T is in the lateral, and oil thickness. We also find an asymptotic behavior between vertical thermal contrast and oil thickness. Both of these make sense to me. At some point, the oil is so thick that any thicker doesn't absorb any more energy. If there's no more energy to absorb into the system, how can the temperature change? Similarly, in the vertical, as the oil gets thick, it starts becoming an insulator. Well, this is all very interesting, but could it be a laboratory artifact? And besides, I really don't look that great under fluorescent lighting. I got to get out into the field on a boat. So we then did the same experiments at sea. So this time we weren't able to get, because of capillary waves and their velocity, the same level of resolution. So here we're aiming for 70 micron resolution, which we achieved, which is the thickness of a human hair. So we developed this raft profiler, which very smoothly moves thermocouples into the water. It has distance sensors, so we know very precisely how far to the water it is. And we achieved measuring the thermal profile with the resolution of a human hair at sea from a rocking boat, okay? We also imaged the system with C-Spires, which is our science package. On an airplane, it's cameras. On a boat, it also includes meteorology and spectral information. We've used it on 2 different boats. One, a shrimper, where it was up 30 feet, looking down at a raft that was moving the raft, and one off of a smaller boat where we could control it. Now, one of the challenges was what I called cross georegistration. The 2 cameras are not precisely aligned, close, but not precisely. We are not pointing because we're not up high, we're low, we're on a rocking boat. So we're pointing at some angle at a sea surface that has its own curvature and slant due to waves. And it turned out that this was really hard to achieve the 2 millimeter co-registration that we needed. We did do it, but it ended up having a lot of manual work to do. We weren't able to automate it. These are also extremely high resolution images. So 2 millimeters in the thermal and 0.5 millimeter in the visible. But it wasn't just stopped there. We also had another challenge, which is if you're doing thermal measurements, then the heat radiated from hot or cold objects. Okay, not cold, that was a joke. Cold things don't radiate. Hot things radiate. Park yourself near the fire in the winter. Well, this raft was a hot fire and it contaminated the sea surface and within about 15 centimeters of the raft with a reflected radiation that the microbolometer observes, and we couldn't counter for that, unlike sky radiation, which we did counter for. And so what we needed to do was back trace the sea surface, that little patch of oil we had profiled, to get it away to where it was not near the raft. We did that using image flow. Here is an example of thick oil profiles, and we see the same characteristics, a oil thickness peak, a peak in the middle of the oil. Additionally, in this one, we did 3 profiles simultaneously so we could pick the best of 2. Something weird happened in profile C. It was considered an outlier. Specifically, we think there was a micro turbulence event. So we did 3. Putting them all together, the same asymptotic behavior in the field. And if you look at that exponential, it goes as, now this is vertical contrast because we're doing this from profiles. as H to the 0.88, that would suggest a 1.2 millimeter optical depth for the oil. Just kind of keep that in mind. Well, okay, it is the same, but why? Well, back to the fluorescent lit lab and the computer. Let's build a numerical heat model. Okay, so we got 3 media, we got convection, we got diffusion, we got absorption, we got emission. It's complicated. Does it work? Yes. We specifically tested it or validated against laboratory collected data. So it captures, number one, the 2 interfacial temperatures to within better than 10%, sometimes better than 3%. It captured the structure. Thick oil, again, optically thick, not bond agreement thick. Thick oil's got an internal peak, thin oil does not. It's also flexible. The one on the left is for the night, okay? It does not capture turbulence, not a surprise. So we compare it against a data model that also ignored turbulence. It did a poor job in the water side boundary layer of the oil. Again, this is because the turbulence from some mixing pumps doesn't follow the normal pattern you would expect turbulence in the ocean to follow. Since it didn't affect our interest, interfacial temperatures, we didn't care and we didn't bother to try to do a good job on that. It also had a little trouble on the location of the peak and the slope of the peak, internal peak. And that we believe is due to an internal circulation or overturning within the oil that could be added to future models, but wasn't at this point. Here's when you run the model for many different cases. The model lets us simulate oil that would be infeasible to run experiments on the lab, either due to it being too thin and therefore very difficult to get truly homogeneous, or too thick and having too long equilibration times. And what the data shows, or rather the simulation shows, is that exponent is 1 over the extinction length or optical depth of the oil. And you could go, we got it. It's the optical depth that's controlling things. Back to the field experiment, the Seep assessment study, now that we know what thin oil is. So I'm now going to show our application of this for thick oil, which doesn't have an emissivity problem. Why? Because where we do include this is still under litigation review. Okay. We need to know thermal contrast relative to the sea surface temperature in the area, because that's how much the oil has been heated up. That's our capital delta T in our model and our experiments. And we do this by probability distribution function modeling of the scene or texture analysis, and use that to identify wake, oil, thick oil, and background sea surface temperature. Well, that worked well for the collects because they were just a single scene and there weren't gradients in it that were significant. It didn't work for the survey where there were all sorts of gradients. So in this case, we modeled the sea surface temperature cross slick. So we basically used, created a map, if you will, of the temperature structure of the ocean if there was no oil there, which you can see in panel C on the lower left. There are two things. There are hot pools and there are cool pools. And there was a discontinuity. The inner water was cooler, the outer water was warmer. In the Mako map, you can see at the right, you can see the gyre that is formed by Colol Point. There's another gyre, or not really gyre, but shear instability due to Campus Point. These propagate around the point and control the location of the oil. If you're able to see it on the screen, you can see the red is where oil was detected in the remote sensing analysis, and it follows right along the current shears. So these current shears which are due to instabilities in the flow due to the different temperature waters, are forcing the location and the meanders and the thermal structure of the water upon which we need to evaluate what is delta T, what is the water temperature. Moving forward, it's straightforward. Now you apply our in-scene calibration, top left, which relates the amount of oil we collected to the average temperature of that oil, thermal contrast in the collects. And then you just apply that to the oil. And these are on 2 different days. And so here we have a map of the amount of oil presented on the lower plots as linear, kilograms per meter, showing a lot of structure. And we've compared this structure in the paper with the sea surface structure. And this is due primarily to emissions variability, not due to transport heterogeneity or variability or unsteadiness. So bottom line, on May 23rd, we found in our 2.2 kilometer slick, 310, 2 barrels of oil. And on the 25th, we found 17. The uncertainty is from Monte Carlo simulations of the variability in our calibration. Now, we have not, at this point, attempted to improve the calibration by using the model to correct for changes in the solar insolation. We could do that and improve our error, I think, probably another down by another third. So, okay, gonna change gears. And I saw I had presented my T-Mog last time. Is now sister. I now have a full-size pickup truck with a built-in generator to run everything. The package can go on a boat. It can go on a trailer. We're making Meteo trailers. And it measures a lot of parameters. You can see them listed here. The gases, all better than 100 part per trillion, somewhere down at the 25 part per trillion. We use the real-time data to determine where to collect sample canisters. And the analysis of that by the UC Irvine lab is 4 parts per trillion. They can see things out to undecane, the aromatics, branched aromatics. We also do very comprehensive aerosol measurements, both size distributions and aerosol profile. On the right, you can see when wildfire smoke came over my lab in our aerosol profiler. We also do meteorology and we have solar spectroscopy. And what this means is that we're actually able to characterize the health implications of exposure to harmful hydrocarbon gases, such as those ones I breathed from the Seeps when I was a postdoc. Here is some recent data we collected in Maricopa. This is the southwest San Joaquin Valley, where some drilling operations were going on. And we were able to nicely see the plume of methane, the plume of ethane. We even can see how the isotopic composition of the methane is different or more thermogenic in the plume. So we're doing some really nice work. And this is part of a project for NASA to look at the emissions from an abandoned oil field. So in the top left is our real-time display, and black are all the wells that are abandoned, not idled, abandoned. Yes, it goes on a boat too, and here's some data we collected offshore and the canisters which were collected to try to look at the emissions from the oil slick and the Seep field as well. So it's certainly we have the potential, and so we can pretty much in about 45 minutes get on the road and go make measurements. It's designed for response. So I mentioned C-Spires. It's a physics-based remote sensing, oil thickness quantification that we've developed. The numerical model allows us to extend it to other oils, to other settings, taking account of illumination, the environment, and such other measurements. The numerical model gives us uncertainty and sensitivity values and we're currently in the status of raising capital for commercialization. It's pitch ready. Thank you.
Awesome, good timing, Ira. So we have a few minutes if anybody has questions. I don't see anything in the Q&A, but I do see a raised hand. Oscar, you can go ahead and.
Thank you. I have very cool presentation. Thank you so much. I enjoy it. I have a question for you. So we have seen similar effect on other locations and also on the Seeps where the thermal shows that colder oil or interpretation is that obviously is indicative of thicker oil, but we haven't seen a way to measure how thick when you have the other way, you know, when you have the warmer oil that you can sort of relate to thickness. Do you have a sense of how to interpret the thickness of that colder oil?
It's an illusion that is cooler in brightness temperature. So what you need to know is the emissivity of the oil.
Right.
And so we measured the emissivity of the oil and also derived it from our field data. It was 0.967. And so you then use the visible imagery to make sure you only classify oil as oil, not sea surface as oil, because when delta T goes to 0, it's the same as the sea surface. And then if you apply an emissivity correction, you get the true delta T, what we measure with the thermocouples. And then you can apply the calibration constant. That particular work is still under litigation review.
So you're saying that it's not thicker oil? Is that what you're saying?
Cool oil is thinner because basically with increasing thickness, the oil gets hotter. But with decreasing thickness, the emissivity rises to that of water. And this kind of makes it look cooler,
yeah,
but it isn't.
Yeah. Yeah, it was our interpretation that so it's in thermal balance with the surrounding water, and it's just because of that emissivity change that you see it cooler. But I was hoping you could tell something about thickness.
It's never in balance with the surrounding water, not even at nighttime, because there's an energy balance. The only way it could be in balance with the water is if the air and the water are isothermal. Otherwise, there's always, let me go, I want the model. Yeah, that's it. Yeah, so this one here on the left is, catch up computer. So this is nighttime, and you can see the air's warmer, and the oil is warmer because it's transferring heat between the oil, the air and the water through the oil. And so it's warmer. It could be reversed, and that's something that we want to look at with the model if you have cool air over hot water. But it's never going to be in equilibrium. Now, when you start getting down to microns, it probably can't be easily measured, you know, unless you have extremely accurate sensors.
Mm-hmm.
But like Ryerson report, saw a thermal contrast for 5-micron oil with an extremely good 1998, a very good thermal sensor they used. So it's really just a detection level and a noise issue to see that.
All right, thank you.
Okay. So one thing I just want to add, if there was any sponsorship, we would be happy to support June activities out here in the Coal Oil Point Seep Field, our backyard with our setup. But I'm just going to put that out there. People know how to get in touch with me by email for further discussions.
Great, thank you, Ira. Fun backyard of yours.
It's nice having an oil spill every day, 40-minute boat ride away, go home for dinner.
So much science. Thanks again.
You're welcome.
Okay, we're at 1:32. I'm gonna just jump right into our next presenter, which is Sure We. And I see you on camera there. Thanks for being on time. He's the Director of Business Development for Metas, and I'll let him tell you more about himself. Welcome.
Yes, it looks like I'm the only engineer among all the PhDs and scientists here today. I have a degree in electrical engineering from the University of Bergen in Norway. I am originally from Norway. I've been in Texas since 2004. I worked in the oil and gas industry for nearly 40 years, and that's probably what has given me all my gray hair. But I'm here to talk about subsea environmental monitoring and leak detection systems. So Metas was founded in Bergen, Norway back in 2009 as a spin-off company from the Institute of Marine Research. So marine research and basically finding fish and marine life is our background. And we base our technology on sonar. And what I'm going to talk about today is using active sonar to detect leaks of hydrocarbons and CO2 on the seabed. So today we have been hearing all about all these systems that is detecting sheen and oil on the surface. Metas is actually doing this subsea on the seabed in close proximity to the actual oil production systems and to the potential leaks. So the subsea industry challenge is that we really don't have situational awareness or risk management below the water surface, which is outside of the pipe or production systems. We know what's going on inside of the pipes and inside of the production systems based on pressures and flows and all these measurements, but outside of the pipe, we have pretty much no idea. So it's difficult to identify risks so that it can be mitigated before a catastrophe occurs. So obviously, this is what we want to avoid, right? We see here to the left, it's a ruptured jumper. This is in the Gulf of Mexico a couple of years ago. And obviously, this is something that we want to avoid, and we want to avoid it before we even can see it on the surface. So today we have surface solutions, which we have been talking about most of the day today. And that is a lot depending on visibility, weather, and to a certain degree also daylight. And with detecting an oil leak on the surface, we really don't have an exact idea where the leak originated. Below the surface, we have limited visibility and no idea what's actually happening in the water column around and above oil production systems. And also traditional leak technology has been prone to false alarm and failure. And one of the things that is becoming also a requirement is that we have to be able to verify these systems in situ, which I will come back to. So today, leak detection is limited to more or less catastrophic events where you can actually see things on the surface. We also have regulatory and industrial requirements, and leak detection is becoming mandatory. BSEE, which I believe is present here today, are working on this. API 17V will amend leak detection requirements as a recommended practice. And in Norway, where I'm coming from, which probably has the strictest rules, this is leak detection is mandatory. I mean, you can't not have it. I'm also working a lot with Brazil and Brazilian government and ANP, and they are also in the process of having subsea leak detection becoming mandatory. So there are several leak detection technologies that actually are placed on the seabed. You have point sensors, which basically are capacitance and sniffers. They have to be where the actual leak or the leak is spreading. So if the point sensor is away or down or upstream of the leak, they won't see it. And then you have passive acoustic. So if you have a leak, that leak would create the noise. But you can figure out what direction the leak is coming from, but you don't really know if it's close or far away. It could be a small leak close, or it could be a big leak far away that would create the same amount of noise. And then you have active acoustics, which we have demonstrated we can have up to 1,250 meter radius detection, and for pipelines up to 8 kilometers, a little different use of it, but we can monitor using a system for up to 8 kilometers on pipelines. 360 degrees direction identification, and we can quantify leakage and rate, liter per minute, and very low risks on false alarms and installations. And most importantly, we are able to validate and test these systems when they are installed on the seabed, releasing gas, and which is basically air we're using, and green oil. So you see my minions here. This is this yellow little thing. It's about 1 meter high and maybe 30-40 centimeter in diameter. This is the wide area acoustic monitor, and the sonar transceiver sits in that little dome on the top, and it rotates and it goes up and down, so it can actually do 360 degrees horizontal and 0 to 70 degrees vertical. So we can also see up above the infrastructure. So it identifies basically anything that moves in the ocean and the water column. So that could be ROVs, remote operated vehicle, autonomous underwater vehicles, dropped objects, trawls, and anchors. I mean, this leak that you had in California last year was a dropped anchor. We would have seen that anchor, and we would see that anchor coming down in the water. We would see where it hit, and when the leak starts, we would detect the leak. And not only that, based on the IIS systems on the ships, we could also tell what ship it was. So that's pretty interesting. And of course, submarines, Russian submarines these days, maybe, you know, with the tension in Ukraine and all that, it's also could have military purposes. And of course, we detect actual leaks. And we cover a large area, up to 1,250 meters, which is 3/4 of a mile radius, and for pipelines up to 8 kilometers. We're also using machine learning software to avoid false alarms, because we can see everything that moves. We see fish, we see marine mammals, we see ROVs and all that. And you don't want an alarm every time you see something moving in the ocean. And the software is learning the behavior of all these different objects and what is actually hydrocarbon oil and gas leaks and what is not. So it only reports targets of interest. So that is very useful. And this can also be used if you want to monitor marine life or fish, or document that subsea infrastructure can act as artificial reefs. We can do that too. So it has a lot of different purposes, but for today, we are talking about subsea leaks. This is a typical example. You can place your system somewhere in the vicinity of a subsea production system. There you can see trees, flow lines, manifolds, and risers. And we can see all this and monitor all this. So what we actually would like to do is, even before drilling is started, if you can identify natural seeps and environmental risks before you even start the drilling, that would have big value for later operation. And of course, during the drilling, we all remember the Deepwater Horizon and Macondo disaster. We can monitor well integrity, and even if we might not have prevented the failure that happened on the Deepwater Horizon, we would have been able to detect it way ahead of when the disaster happened, and probably saved the 11 lives that were lost on that disaster. So production systems, early production systems, and not to mention aging infrastructure. We know that a lot of these platforms and pipelines and subsea infrastructure is way beyond their original design life. And as they age, would pose a potential threat of leakage. That is something that we have to be aware of. And then you have abandoned wells. We are working with Petrobras in Brazil on monitoring of abandoned wells. And they have had leaks, small and big leaks from abandoned wells. And that is, of course, something that you absolutely want to avoid. So this would enable operator to detect, stop, and limit the consequences of a subsea hydrocarbon leak. And continuous monitoring is maximizing safety of environment and marine life. And intermittent monitoring could maximize battery life on remote systems. I will come back to that. We also have systems that can operate on subsea batteries. We can map the position within 1% accuracy of the distance. So if you have 100 meters, it's plus minus 1 meter position accuracy. If you have 1 kilometer, it's about 10 meters accurate on position of the leak. We can quantify the volume of the leak in liters per minute and the total volume. And we can also identify the properties of the leaked hydrocarbons, whether it's oil or gas. The leak detection is, of course, independent of visibility, light and weather conditions. And it can be detected in minutes, depending on the swept area. So you can choose 360 degrees, but if you have a subsea field that doesn't require 360 degrees, you can choose how much of that area you want to sweep. And of course, you reduce risk by early identification. And since we're covering a very large area, it's very cost effective because you would need just a few units to cover a really large area, or maybe just one. Machine learning is no false alarms and no deferred production. You don't want to shut down your production based on false alarms. I mean, if you have a real situation, you can shut down your production system, whether that is a single well that is leaking, or it's a manifold that is leaking, or it's a pipeline that is leaking. So you would know exactly what equipment that is leaking. And of course, we don't want anything on the surface like this. We also have subsea communication. So for systems that are remote or doesn't have existing infrastructure, we can have battery operated systems and subsea modems, and we can daisy chain these subsea systems, and they can communicate to a surface buoy that could send the data to either to satellite or to 4G on the cell phone networks. Regulatory requirements. We know that every country has different rules and regulations on subsea activities and leak detection. And here in the US, it's, compared to several other countries, it's fairly relaxed. BSEE is recommending or advising, but they doesn't seem to have really strict rules. And this is a safety alert letter from BSEE from 2 years ago, based on a leak. You saw this picture earlier. This was a leak on a platform in the Gulf of Mexico. It went undetected for 24 hours. They were leaking 16,000 barrels of oil before they could see the sheen on the surface. And their measurement technology wasn't good enough to detect it. And also the pressure low setting in the pipeline was set below the hydrostatic pressure on the ocean. So when they had this rupture in the line, the pressure low alarm didn't go off. So one of the points here from Bessie is to improve subsea leak detection methods by employing a conditional rate of change, which is basically multi-phase measurements, or advanced monitoring technologies. And that is exactly what Metas is providing and offering, advanced monitoring technologies on the seabed, directly detecting oil and gas leaks. So together with Equinor, the Norwegian oil company Equinor, that used to be Statoil in the old days, we did a pilot project in the North Sea on the Troll B platform. So here is the Troll B platform and the two vessels that we used for deploying and for testing this system. So this was done in November 2019, and it has been in operation since. Equinor is very happy with it. If there is interest, I have reference people in Equinor that can talk about the system and how it's working. So here is the system installed on the seabed. And you can see the similarity with the Minion, right? I mean, you have this little yellow figure that is kind of looking at you. So on this installation on the Troll B platform, we had two systems, one long-range sonar and one short-range sonar. I will talk about the long-range one because that is the most challenging one and probably the most interesting one. So we were having Equinor to do leaks, or we had a template that we put on the seabed with compressed air, and that was placed in 5 different distances: 350, 650, 850, 950, and 1,050 meters from the sonar system. And then between each test, the leakage frame was lifted back on deck and recharged. This is the sonar picture of the seabed. You can see on the left side here is the wide area acoustic monitoring system. You have a manifold here in the middle. You have several wells, and you have flow lines that you can see on this picture. This is the sonar image of the existing infrastructure. So when we install the system, we will map and store the image that the sonar will give us on all the fixed items, all the fixed infrastructure. And basically in the software, those fixed structures will be ignored. What we are looking for are things that move in the water column. And here we have those 5 release points. This is the 350 meters, 650 meters, 850 meters, 950 meters, and 1,050 meters from the base. So this test was a blind test for Metas. So Equinor did this, and Metas was not supposed to know when or where or how this leak occurred. So they started out at 350 meters from the wide area acoustic monitoring system. So they placed the leak frame on the seabed, 350 meters away, and started to release. Here you can see the green. Here, this is the gas plume racing in the ocean. So you can see this is moving up, which means it's moving from south to north, and it's moving with the current. And here you can see the plume is rising and it's spreading, and it changes color as it changes volume and pressure. Obviously, this is gas. So with when it raises in the water column, the pressure will be decreased. And here it's further. You can see that the plume is really spreading, and based on the size and the volume we can detect, we can also determine the actual leak volume in liters per minute, and of course the total leak volume. And here it spreads further up in the water column. So this is one of the many images that we have. We can also have, this is a 2D image. We can also have 3D images and other images that you can see in real time in the platform control room, or in this case, the control room is actually onshore. Further spreading of the plume in the water column. One of the things that, at least in Norway, is a requirement is that you need to be able to validate these leak detection systems in situ, which means that they have to be able to test it as they are installed on the seabed in or around the infrastructure, the subsea production systems. And also this field validation is independent of the process. So you can actually, you have full production while you do this field validation and testing. And so we can demonstrate and verify sensitivity. We can verify alarm performance and how and where you should set your alarms. We can verify the rate measurements, and we can verify the plume visualization. And we are using green fluid. So obviously for the gas release, we're using air, compressed air. And for oil release, we're using a green oil. And typically for these tests, it took around 10 hours for each validation test. The thing is, so oil and gas, obviously, they behave different when they're released in the ocean. Gas obviously is much lighter than water. It rises quickly to the surface, and it creates a big plume that is very easy to see on the sonar. Oil, however, has specific gravity that is closer to water, so it will rise much slower, and it will follow the current for a much longer distance. And that's another thing with surface detection, is that you really don't know where the leak is coming from. And depending on water depth and current and weather, what you see on the surface could be tens, if not hundreds, of kilometers away from the actual leak point.
Hey, sure.
So, yes.
You've got a few minutes left, and you have some questions, so just letting you know.
Okay. This is just how it looks like when we release gas on the seabed. You can see there are fish and krill and marine life in the background. And this, yeah, I'll go quickly through this. So Statoil or Equinor agreed that the test was successful. We met their test criteria. So my point here is, with this technology commercially available, operators of subsea oil and gas productions should not have the opportunity to choose ignorance about what's going on in the water column around and above drilling and production systems. So just a comparison, smoke detectors have become mandatory everywhere. So do you think your house will burn down? You probably don't. But in case of a fire, you want to detect it, put it out, and prevent or limit the damage. And that is what this thing is. It's basically like a subsea smoke detector. So that was my presentation, and I understand there were some questions.
Yeah, thank you very much for that. It's very useful technology. I have a couple questions in the chat and one other. So it says your system could have detected the blowout at Macondo before it happened. Can you, are you saying that this system would detect anomalies inside the well before the oil and gas reached the rig and exploded?
So what happened in Macondo was that there was a collapse of the well integrity. So gas started to leak outside of the pipe and was escaping around the pipe and on the seabed before this was detected or before people reacted on the platform. So yes, we would have seen this happening. I mean, we couldn't, of course, see that, predict that the platform would blow up, but we would have been able to see the leak on the seabed.
Okay, second question, what if the release was high energy and produced droplets and or bubbles that were in the order of only 100 microns in diameter? Would the sonar see these small oil droplets and bubbles?
That depends on the distance. So if we have the near, we have a system that we can place inside of infrastructure on 15, 20 meters, we can see down to milliliters. Obviously, if you are a kilometer away, we would need a bigger volume. So if this is like a jet stream with very fine or small bubbles, it depends on how much it would be. I mean, we would see it if it's big enough. Typically on a kilometer's distance, the sensitivity is around 40 liters per minute.
Okay, hopefully that answered that question. I have one more. Is the 5-mile leak detection range for pipeline monitoring for a straight run of pipe only, or will it work for 5 linear miles of pipeline with turns?
That is for straight line only. So based on the angle of the sonar and the frequency, we can see 4 kilometers one way. So if we place a system where we're looking both ways, we can do up to 8 kilometers or 5 miles. That is in a straight line.
Awesome. All right. Thank you. Well, that's all the questions I see. Thanks again for that great presentation and for sticking to your time limit. It's great having you on board today.
Okay. Thank you very much.
And so since it's 2 o'clock, we're going to move on to our next presentation, which is Kevin Hoskins. And Kevin is Vice President of Telecom and Information Systems for the Marine Spill Response Corporation, or MSRC, as we all call it. So welcome, Kevin.
Thank you very much. Can you see my screen?
Yep, looks good.
And you can hear me, so okay. The technology's working, that's good. Well, good afternoon, everyone. Today I want to talk to you about oil spill detection and tracking, but a multi-tiered approach. And I think there's been a common theme through a lot of the presentations today where, you know, one sensor just doesn't give you the entire picture. It takes several sensors to give you that characterization that you're looking for. And then I'd like to, you know, my company obviously is focused on cleaning up oil spills, and I'm focused on being able to detect oil on the water. But we found that these sensors do have alternate applications, and so I'll give you a few examples of those, as well as I'll intersperse some of the real world case studies that we've been involved with over the years. All right, so as I said, no one technology or sensor can provide all the answers. Each sensor type has its pros and cons. And it's very important to understand the capabilities of the sensor, how they react to different oil types, different oil thicknesses, emulsifications, etc. And there's many factors that can impact the effectiveness of the sensor, and a lot of that have been highlighted today. And I know the focus of this workshop is in low light or in conditions where the environmental low light and clouds and rain and humidity can have an impact. So I'm not going to spend a lot of time on the satellite just because I couldn't do any better than Gordon and David, or I'm sorry, Benjamin did this morning. But I will just highlight the sensors that are available to us in the SAR, the thermal, and the optical. We also have a proprietary app that we developed in-house that utilizes the Apple devices, the iOS devices, the iPhone or the iPad. It utilizes the GPS and the camera in the devices to allow us to go out and get get that first look at what's going on and map the spill, create a workbox, characterize it, take pictures, make notes, and then export this into a PDF document that we can readily email down to a command center or a vessel. Aerial sensors, and the aerial sensors that I'm going to focus on today are small and portable. There's a lot of sensors out there, but a lot of them also are pretty big and require dedicated aircraft, and I'll talk more about our Aircraft of Opportunity program. But so the sensor we're using is small, compact, portable. It has near wave and long wave infrared, and also multispectral sensors. And then for those of you who have been in, participated in this workshop before, I know I've talked about our aerostat in the past. Basically a big balloon, right, with helium. And on the front of the balloon, and hopefully you can see my cursor, on the front of the balloon is the gimbal with the high definition and infrared sensors. And on the back is the tail of the kite, which it's a little hard to see, but that's where the battery goes because we do not provide power through the tether. And so, and then on the top is basically the strobe light, just to alert the aircraft. And then drones, there's a lot of sensors, 4K and thermal being the most prominent. And then finally, the vessel mounted sensors. On our particular oil spill response vessels, we do have oil detection systems that incorporate X-band and FLIR technologies. All right, so again, I'm going to cruise through the satellite because a lot of this is replicated from the earlier presentations, but obviously that's the sensors that are available, SAR being probably the most applicable. They can obviously cover a large area. They're effective. Thermal and SAR can be effective day or night, and they can provide relative thickness information, and they've been widely used for decades. Some of the cons, obviously visual sensors are only good for daylight hours. False positives are always a concern no matter what sensor you're using. Thermal cameras typically cannot detect thin oil sheens. Very calm or rough sea states can impact the SAR effectiveness. The interpretation to discern oil is complex and requires a skilled analyst. I think Gordon highlighted that this morning. And there could be long delays between the satellite or aircraft tasking and the final delivery. Again, if the incident happens in an area where the satellite is not and you have to wait for it to come overhead, that can delay you getting the product. All right, again, aerial sensor. The sensor that we utilize has a 12 megapixel color sensor and long wave infrared and near wave infrared. And it has a step, stair, roll, pitch, automated stabilizing gimbal. I can hardly say that once. Try saying that 3 times in a row. And I'll give you an example of what that looks like on the next slide. But this sensor allows us to get real-time imagery on a map in all bands. We can create quick mosaics in the aircraft and readily send those down to on-water assets or a command center. And then automatic detection of objects or changes of interest is also possible. We could fly the same flight path and have the software detect changes. So this is a quick video of the sensor in motion, and this is kind of giving you that side-to-side stair-step motion, if you will. It basically is programmable from 1 frame to 5. And it repeats. So it goes from 1 to 5 and then goes back to 1. And that's what gives you this sort of stair-step imaging. So that's kind of unique, and it is modified. The operator can modify the number of frames, but obviously if you lessen the number of frames, you're minimizing your swath width, right? So this is what some of that imagery would look like. The bottom is the multispectral, and the top is the thermal. And in this particular case, there are 3 passes were made, and you can see that 3 passes and five frames per pass, right? And then this is all stitched together. And again, the operator can choose which spectral band they want to observe, and they can toggle back and forth if they're trying to vet out false positives or get a better look. And again, the operator can adjust the number of frames for the swath width. Here's another example of an exercise we did off the Santa Barbara coast at about 2,500 feet. And you can see the areas that were captured. And then the exploded views are the areas of interest where we actually saw oil. And again, when we can see it in the thermal camera, we consider that to be actionable. So these here would be actionable oil, and that's where we would focus our attention. Here's another of platform Holly, again, using the thermal camera. And the key advantages, again, to this sensor is it differentiates thick from thin oil or recoverable versus sheen. We can cover a large area, flying anywhere from 4,000 to 10,000 feet. We're able to track oil movement. Again, multispectral and thermal infrared overlay help us to expose false positives. A very fundamental example of that in this image would be for someone who wasn't really experienced to look at this thermal image and see what one could mistake as something, you know, that could be oil because it's much darker than the surrounding water. But what that really is a boat wake, and the prop churns up the colder water. You get a temperature differentiation, and it shows up in the thermal camera. You can easily flip over to the multispectral camera, and obviously there would be nothing there, and you would know then that that was a false positive. The actual oil is depicted down here. Again, dark, thick streamers that we consider would be actionable. The deployment strategy, again, is a contracted aircraft of opportunity. These are aircraft that we have pre-vetted to meet our safety standards, but also they must have a downward-looking observation port or some type of a pod, a belly pod that the sensor can fit into. Very tactical in use, direct resources to the thickest oil, and we have low light and daytime operations. Weather conditions, obviously a low cloud ceiling can be a problem. Thick fog is a problem for us, obviously. Humidity can also impact thermal on occasion. So if we are able to fly in what I would consider to be, you know, light fog conditions or light rain, it might impact the range and resolution of the sensors. So this is depicts an actual response, and the left-hand side of the screen is basically the flight path that the aircraft flew. And you can see the areas of interest are highlighted in the red rectangles. And once we deliver that raw data to an analyst, within a couple of hours, typically, they can put together a classification map like you see on the right-hand side of your screen. And I don't know if you can see, but it's basically 3 classifications here, one being actionable, and that's the yellowish color. Red is the actionable emulsification, and black is the actionable thick emulsification. And so this is the type of products that this sensor can deliver. All right, so the next, I'll give a little more detail on the aerostat. Again, basically it's a big balloon with helium, The gimbal goes on the front. In the tail is the battery. And on the right-hand side, you can see that it's deployed from one of our vessels off the helo deck. I think, like they say, as they say, a picture paints 1,000 words. The top picture is from oil on water exercise in Norway, and it's the Aerostat's optical camera. And you can see in front of the vessel that there's a lot of sheen, and it'd be very difficult to try to determine where you would want to focus your on-water assets. But when you flip over to the thermal camera, which is the bottom picture, it becomes very evident where you want to focus. The darker patches here are the thicker or actionable oil. So again, in this case, the key advantages differentiate thick from thin oil, recoverable versus sheen. Medium range, by medium range, I mean that we can detect oil. Typically we will fly this aerostat at 300 to 400 feet, and we can detect oil at maybe 3 to 4 miles and classify. And what I mean by classify is determine whether it's actionable or not, usually 3,000 to 4,000 feet. The more nadir the look angle, the more accurate the sensor is. Lower cost as compared to aircraft imaging options. Like I said earlier, it has a 12-hour hang time. We bring it down, swap out the battery, top it off with helium, and then send it right back up. There's no FAA restrictions at night. There are some precursors to that, and the fact that we obviously have to have the strobe operating on the top of the aerostat, and for every 50 feet above 150 feet, the tether must also be lighted with a strobe. Additionally, we have to have the capability to hit the self-destruct button, if you will, if for some reason, and I hope this never happens, the tether broke and the balloon started to take off on its own. We do have a self-destruct button that is radio activated by the operator via radio, and basically it completes a circuit that there's a bare wire that lays on the balloon, and that's one end's to ground and the other end goes through a switch and then through the positive of the battery. So once that switch is activated, you complete the circuit, that wire gets hot and it burns a hole in the balloon, and then the helium escapes and it comes down. So like I said, hopefully we never have to deal with that one. There's no certification required, unlike drones with the Part 107 pilot certification. Part 101 does not require that. And again, our goal here is to track the moving oil and keep our on-water assets in that oil. I mentioned earlier, we can tether it up to any platform, up to 500 feet, day or nighttime operations. And I have a scenario that I'll show you here shortly where we did utilize this tool for almost 4 or 5 days straight, 24 hours a day. We have the ability to take screenshots of what the operator is seeing and transfer that to a vessel or command center. Weather conditions that can cancel flights, winds greater than 30 knots, we probably would not launch. We have launched the balloon sustained winds of 22 knots with gusts at 28. It seems to do well. The manufacturer says 34 knots is the cap. We always have to maintain 500 feet below cloud ceiling. So if we have a really low cloud ceiling, that could be a problem. And hard rain or snow, it's probably a non-starter. I can tell you that we did a job off the coast of Newfoundland a couple of years back, and it was cold, wintertime. We were monitoring a pipeline repair offshore, and they were using the aerostat to help facilitate that, especially at night. And it was snowing, and it was snowing hard enough, and it was kind of that wet snow that would stick to things, and it stuck to the top of the aerostat. Of course, that's a big 9-foot by 15-foot surface area that gained a lot of weight in a big hurry. And so it started to slowly come down on its own, and the operators brought it down and realized that it had at least an inch of snow over the entire top of the aerostat. So it was had to obviously brush that off and send it back up, but so it was kind of a unique experience for the guys. This is what I was mentioning earlier. This was a response where a barge incident was a light blending product. It was very difficult to see for our guys on the water. But the thermal camera on the aerostat saw it very, very well. You can see it's depicted by these dark streamers. And so, like I said, we flew the balloon 4 or 5 days, 24/7, directing the on-water assets to the thickest oil. So real world application. All right, drones. I mentioned earlier the Part 107 certification is required. So there's some concerns with FAA restrictions with lithium ion batteries. Depending upon the size of the battery, you either can or cannot take that with you on a commercial aircraft. So it's something that needs to be considered. Again, airspace restrictions, maximum altitude at 400 feet. A couple of applications that are very useful to pilots, and anyone who is a drone pilot knows these. The before you fly and the Lance application, which can get you near real-time authorizations in restricted airspace. So two important tools. And as always, deconfliction concerns are paramount. You need to always coordinate with your air operations branch because you probably won't be the only aircraft in the area. Weather conditions, I think typical light rain is not a problem, but heavy rain or snow will be impactful and probably would not fly. And then always important with no matter what sensor you're collecting the data is to make sure that you have a chain of custody established who should have access to that data. And this is some imagery that we took, compliments of Dr. Garcia during an experiment that we were doing off the Santa Barbara Seeps again. And this gives you an example. I think that we've seen a couple examples of Oscar's work throughout the day today. So this gives you an idea of what you can get from the drone. All right, I think I talked about this last year in looking at tethered drones as a possible replacement for aerostats down the road. And at that particular point in time, I'd only tested a couple vendors, but we've had an opportunity to test a few more with pretty good success. So what I thought I'd do is just show you, it's about a 60-second clip of a deployment that we did off of New Jersey on our New Jersey responder. And again, the tethered drone is mounted on the helo deck. Weather conditions were breezy, but you can see the sea state's pretty calm. But what we did do once we got the drone up to altitude is we tried to put it through its paces as best we could. We had the vessel going as fast as it could, which is about 10 knots. And then we were doing a lot of S-turns and circles to make sure that the drone could handle that. So I'll quickly play this video. Okay, as you can see, it basically stayed overhead. I think it uses what they call a follow me function, and so it worked very well. All right, I mentioned at the beginning that there are alternate applications for a lot of these sensors, and the same sensor that we use to detect oil on water can also be used to image forest fires. And so we got involved in that last year, flying almost 100 sorties for CAL FIRE and the federal government Forest Service, most of it in the state of California, and imaging the maps. And so this particular product that you see is something that we delivered to the Forest Service. And the mission looked, the mission usually started at 10 o'clock at night. We would go fly 1 or 2 fires and then offload the raw data to an analyst on the ground that would take a look at the imagery and create these perimeter maps and highlight the intense heat areas, scattered heat areas, and isolated heat sources. And then we had to have that into the Forest Service by 0400 every morning. For CAL FIRE, we fly a little different mission. It was during the day, very tactical. We'd fly an area, create a mosaic in the aircraft, and get that down to the ground as quick as possible. But again, same sensor that we use to image oil on water, we were using to image forest fires. A couple other case studies that are outside of the norm of what again, my norm being detecting oil on water. In the top, you can see, this was after Hurricane Harvey, a tank farm where a lot of the floating roofs had failed. And we used the aerostat to monitor the pumping operations. And then the bottom was a few years back, the bottom picture was a tank farm on a river at a flood stage. And the concern was that the river would breach its banks and perhaps get into the tank farm and cause havoc. So we used the aerostat to monitor the tank farm at night. And you can see the clarity. It's so clear that we could see the level of the products in the tanks. And thankfully, the river behaved itself. It wasn't a problem, but we did fly a couple nights monitoring that tank farm. All right, this next one has to do with drones and another alternative application. It was for a ship fire, and we were originally called out just to boom off the ship to make sure that if there were any leaks that we would contain it. But we were able to, we were flying our drone, but we were able to utilize the thermal camera to help the firefighters know where to focus their attention. So in the visual side, the visual sensor, you can see, you really can't see, there's no open flames, it's hard to tell where you should be focusing your attention. But when you flip over to the thermal camera, it becomes very evident very quickly where the firefighters need to focus the water. So a pretty unique application of the thermal camera on the sensor, or on the drone, sorry. And his face popped up, and I said, "Oh my God, I got to hurry up and finish." So another application for the drones, there was a monitoring a pipeline repair, and they were using a helicopter to provide that overhead visual observation. And as we all know, helicopters are pretty pricey. So we were able to utilize drones instead of the helicopter, and we were had a drone in the air from dusk till dawn, I'm sorry, dawn to dusk, and always had a drone. So we had 2 drones and 2 pilots, and basically monitoring that repair to make sure there was no leaks. And that's it. So hopefully you can see that, there's a lot of tools. They all kind of complement each other, and they all have some unique applications outside of just looking at oil on water. And with that, I'll take some questions.
Yeah, I think that's a huge takeaway from all of this, is that sometimes it takes a combination. There's no like magic pill for these things. I do have one question in the Q&A from Jordan. Are the classified oil imagery from the aircraft mounted sensor generated in a shapefile or another format that NOAA trajectory modelers can automatically ingest into their WebGNOME?
Yes, we can export that into almost any format you would like. Shapefile, GeoTIFF, GIS friendly formats, absolutely.
Also, and then the second part of the question is, can those classified imagery products be provided directly to NOAA quickly during an active response, or would that first require approval by your industry client?
It requires approval by the industry client. Yep, that was when I was talking about the confidentiality and, you know, and chain of custody. So typically we would provide the imagery to our customer, and then the customer disseminates that to who they would like to have that information. Yep.
Okay, let's see, is there one more here? Which of those, can you just kind of highlight the ones of those technology you talked about that work at night?
Certainly the thermal camera, I think on all the sensors has the capability of working at night, right? The last aerostat photo I showed you of the light and blending product, those images were at night. So that was a thermal camera at night, taking that imagery and depicting where the oil was. So.
And then one more question, is the Apple app free, and what is the name of it?
This is an app that was developed by one of my guys. So it's an MSRC proprietary app that we haven't really ever thought about marketing. So something that we use internally. However, I do know that there are some apps on the App Store. One I think that's over in the UK for sure that is available. So
do some app hunting.
Yes. All right, is that it?
Okay. Anybody else have a question? If not,
yeah, this is Lisa DiPinto. I can't type the questions in. Hey, Kevin, great presentation. Can I ask a quick question?
Sure.
Along the lines of where Jordan was going, and we're both NOAA, of course, I was curious how long it takes to deliver the oil classification maps that you talked about. So you collect the data. How long does it take to produce one of those maps? And how long would you anticipate it would take to get into a NOAA system? Maybe it depends on the responsible party approving it. Maybe leave that step in for one answer and then take that step out for another answer.
I can tell you that the guy who's doing the analysis for us is the one and only Oscar Garcia. And so I think, Oscar, you can pipe in if you're on, but for the response that I showed, typically once he got the raw data, he could interpret it and develop that within a couple hours, I believe. So, which is pretty quick. A lot of times the longest part of it is if you have a slow internet, is trying to get that data offloaded from the sensor down. Now, we usually try to start that process in the air if we have good cellular connectivity and get that down as quickly as possible while we're going back to the airport. My experience, Lisa, again, I think the second part of your question was, how does NOAA get access to it? The few responses that we have been on, or we've done the aerial imagery, it's been at NOAA's request, and then NOAA has gone to the customer, the responsible party, and said, this is the type of information that we would like, and then that customer went and got, activated us. So I'm not sure if that answered your question, but.
No, thank you very much. I appreciate it.
You're welcome.
Like a train going by.
I know, I wasn't me though.
All right, thanks so much, Kevin.
Thank you, everybody. Appreciate the opportunity.
And on deck, we have Tim Nedwed, ExxonMobil's oil spill response principal advisor. So Tim, if you're ready to share your screen, go right ahead.
Oops. All right, there you go. Can you see my screen? Hold on.
Looks good.
You don't see. I see other things. Okay. All right, you can see my screen and you can hear me. Okay. All right, I'll get started. Hey, so I wanted to Well, first off, move the slide. Hold on, I'm sorry. First off, I want to recognize Lisa because I changed the name of my presentation here to Uncrewed Jet Ski. I used to say Unmanned Jet Ski, and I think uncrewed is a gender non-specific way of describing what the jet ski is. And it's a very elegant way of doing that because it doesn't change the acronym. We have an uncrewed jet ski with a tethered uncrewed aerial vehicle, and it provides a fast and flexible remote sensing capability. So I'm going to describe the research that we've done and the status of that system because it's still in development. But I'm going to say up front, I think it provides kind of the charter of this workshop as well as anything, because it provides detection, mapping, and I'll add tracking. And if we change recovering to responding to oil at night in the fog, I think this system does that. I hope to explain to you, and you agree with me as we go through this presentation. So before I start, this is a collaborative project, and I want to recognize some of the participants in this project. And Scott Begal is the first one because Alaska Oil Spill Recovery Institute is the coordinator of this joint effort that we have with both industry and government entities. And he's provided some funding and also kind of his own internal expertise that's helped move this project along. We have Bessie is supporting the project, but not just that, they're providing expertise that helps guide this project through Jay Cho and Karen Stone. Paul Schuler with Clean Caribbean Associates has provided some research funding, and he's provided his kind of real world understanding of how oil spill response happens to help with the project. And lastly, I'll mention the kind of innovative person that's really pushed us towards this jet ski system that I'll describe, and his name's Tim Thornton, and he's the vendor that's been developing it. He's the one that had the idea to advance to this jet ski platform, and he's with Tactical Electronics in Tulsa, Oklahoma. So this jet ski system that we have is that the development of this thing really tells you the importance of kind of stick-to-itiveness with research, because we went down a path and we ended up trying to solve a problem down that path with a whole new platform that allows us to do a lot more than we had expected to be able to do in the beginning. And I think as the title says, this is a fast and flexible platform really for both remote sensing, and as I'll describe on a slide, if I don't run out of time, it also provides an active response tool for using if we use in situ burning. Okay. So this is conceptual drawing of the jet ski and some of our deployment methods that we want to use, right? So it is a jet ski, and I'll show you on the next slide, but it's an off-the-shelf jet ski where we've taken the top sides off. It's a clamshell design, and you just have to unbolt the top sides, and then we built our own top sides to fit over it that has the capabilities and the ability to add additional capabilities to it. And it includes a tethered UAV, right, that we can put whatever system the UAV can handle on it, and one option is an IR, visible cameras. So it provides the eyes in the skies that are really absolutely vital for remote detection and characterization of oil slicks. And it's a tethered UAV that this is an electric power line, so it is not carrying its own battery. It is getting power from the jet ski platform, which allows it to stay in the air as long as the jet ski has fuel, and we've outfitted the jet ski with additional fuel capabilities, so it can stay in the air for multiple days, possibly. And then let me just show. So we have a couple of visions. Not sure why I can't get my multiple visions for how we would trying to get my laser pointer for how we would deploy the jet ski. I guess I'm stuck with the mouse. Okay, we have multiple visions for how we would deploy the jet ski. We're actively working towards these first two right now through this joint effort that I mentioned. One is deploying it off of a boat, which is relatively easy. The jet ski is not a heavy thing. It's probably around 400 pounds fully loaded. So it can use hooks or cranes that are available on many vessels to get it over the side and to recover it. But we're also building it with a built-in winch that allows it to be pulled up under the belly of most helicopters that have a hook underneath, and some of those helicopters may not have their own winch. So we can deploy it really quickly with a helicopter. And then eventually we hope to build a system that allows it to be deployed out of an airplane, a fixed wing airplane that has opening, like a C-130 would have, an opening large enough to allow it to be jettisoned out of the airplane. And this little drawing here shows it with like a dragster parachute to keep it from falling at its terminal velocity. into the sea. So that's where the fast comes in. All right, so I mentioned we have an off-the-shelf system. The system is called the Sea-Doo Spark, the one that we used, because it's a very advanced jet ski, and it has the most efficient motor available on the market. For just off the shelf, it has many hours of operation. I think they say they can have 12 hours of operation with the fuel capacity that comes with it off the shelf. As I said, we took, I'll show you on the next slide or two what the prototype looks like right now, which you can see the bolts along the side of this. This top side comes off, and we molded and built our own top sides. The motor it's a 90 horsepower, it's a gasoline motor. The jet ski is a three crew member jet ski that allows 450 pounds of cargo limit off the shelf, and we've actually been able to add some additional buoyancy to it. It is built, we've added the ability to have autonomous operation. We can use a GPS system to put waypoints in to send the jet ski to where we want it to be and actually do a circuit on the way there. But it also has remote capability. There's a 360-degree camera on the jet ski that allows a remote operator to operate the system in basically any place on the planet if we go all the way to satellite communications. And that's important because it allows the operator to not necessarily be in the theater where the spill is, but he can be an expert that might be it might be more effective for that person to be at some other location, but he still gets the same information as if he was in the theater. Off the shelf, the system, has a fuel capacity, I think about a third of this, 15 gallons maybe, but when we open up the clamshell and looked inside the hole, there's lots of space, and we added additional fuel capacity. So we think it now has speeds of up to 50 miles an hour, depending on sea state. Certainly in 3-foot seas, it may not be going that fast. It has a range of 1,200 miles before needing to be refueled, and has 30 plus hours of operation, depending on how fast you're going and how much fuel you're using. And I mentioned it is also a active response system, and I'll describe that on a slide. It has a herder application, and then it is and my teenage son's like this, it is a flame throwing jet ski because it can spray gelled gasoline, ignited gelled gasoline 10, 15 feet off of the jet ski to ignite a slick and initiate in situ burning. I'll show you it as a radar system built into it to allow collision avoidance. And I mentioned the tethered UAV that allows eyes in the sky. It has these lipstick cameras that are on above the waterline and below the waterline, so we can have visuals in every direction, but also has a 360-degree virtual reality camera. And in fact, we could use virtual reality goggles, I believe, to allow an operator to operate as if he was on the back of the jet ski. And it's being outfitted with underwater lighting. So that's kind of what it has, the prototype has now. We're working towards a project to add additional sensors to it, and the sky is kind of the limit on what sensors because of its capacity. We can't put something greater than its load capacity on the back of it, or we'd be challenged. But we're adding a VOC monitoring system to it. We're looking at different methods of detecting and mapping slick thickness. There's the potential for put an oil slick sampling system on it, and we could put some off the tethered UAV, a smoke plume sensing system to characterize smoke plume. And as I put here, there's potential for it to do other things. And we are looking for suggestions on what other things that might be useful on the system. Okay, so this is the system as it existed. When was this? In January. And this is the system, right? This is the jet ski. I mentioned the top sides are pulled off. Top sides right now are this aluminum system because it's easy to fabricate and modify. This is the radar system, an off-the-shelf radar system. Garmin claims that it can detect, and the way it's positioned on this boom up above the surface, it's 5 or so feet off the water at least. It can see a floating tire 2 miles down the road, and then it can either have an algorithm. We're building an algorithm that allows it to automatically avoid that, or the remote operator can avoid something that it sees that far down the road. And this system is built with the herder delivery and the flame throwing gelled gasoline system built into it. And this is just a picture with the top sides cut off. We built a frame to make it more stable, and you can see there's still quite a bit of capacity for additional fuel. And here's the jet ski, the prototype we had in 2019 operating. This is a couple interesting things. It's 10% throttle right now, so it could certainly go a lot faster. And you can see it go nose down right there. This jet ski has a capability to reverse thrusters, so it can actually have its own braking system, which is great if you actually have a recreational version of this. And because you don't think of these kinds of vessels having brakes, but this one actually does have brakes. And the other thing I'll mention about the jet ski is it's made out of this polymer. And it's not made out of fiberglass. When I was a kid, jet skis were made out of fiberglass. And if you ran into a rock or something else, you cracked the fiberglass and you were in deep trouble. This is made out of a very durable polymer. In fact, it's the same type of polymer that like modern trash cans are used. Like the trash can I have that we put outside, I can run over it with my SUV and it will pop right back into shape and it's not destroyed. This jet ski can do the same thing. It will not be destroyed very easily. In fact, there's videos online of guys going across rivers or going up rivers where there's broken ice flows, and they actually take the jet ski, speed it up in the water portion between the leads, and then hit the front of the jet ski onto these ice flows and skid across the surface. And then the jet ski comes off the ice flow onto the other side, and they give it gas again and get speed and do it as they move up a river that's covered with ice. Okay, so we are in the process. This year, we started a project with our consortia to increase the remote sensing capabilities beyond the tether system and the camera systems that we have built into it. The system's going to have these desired capabilities when we're done: long-range communications with either satellite, a cellular network, or radios, but the satellite system will be the longest range. It'll have the virtual reality operations that we're building into it. As I mentioned. So we think it can apply rapid detection, characterization, and mapping of offshore oil slicks. It's got eyes in the skies with the UAV. And then we hope to put a slick thickness mapping system into it. So we can map, by running transects through a slick, we can map the oil thickness in real time and provide real-time heat maps of an oil slick. We also, as I mentioned, we want to put an air monitoring system. And so the unmanned system can go into places where you don't want to put personnel. And in fact, we think that the VOC monitoring system will allow the jet ski to be an overnight tracking system, because we can develop an algorithm so that the jet ski stays in the middle of an oil slick or in an oil slick when overnight by just staying where the high VOC signals are. So it's not just a detection system, it is this autonomous tracking system for overnight and even in storms possibly. And I mentioned the radar system has this autonomous collision avoidance system. So we're putting the radar system and checking it out now. We are checking through these systems. Onboard satellite, cellular, and radio communication systems are in the prototype now. The GPS system is in the prototype now. We are mounting, you see this conceptual drawing of the articulating arm. We want to use it to test a range of different CIS detectors. And so we're going to use this arm to put detectors above the water surface, on the water surface, or even below the water surface to do various things. Slick stick detection is one of them. At the eyes in the sky. I'll mention the tethered UAV is both a UAV, the one we're using is both a UAV and an AUV because it can go underwater, right? It can actually be a submarine. And that's important because of the way we want to use this system. Being on this small platform, there's not a helideck like you saw in Kevin's video to land or take off from. So the idea here is we have a hangar on the back of the jet ski, and you jettison the UAV into the water and it actually floats on the water. We deploy a certain length of the tether, and then the jet ski takes off in the air, and then to retrieve it, it would be pulled, come back down. It actually flies on its own, and the tether would reel as it's flying. The tether, the UAV is not pulled by the tether. It is programmed to fly based on the positioning of the jet ski at whatever height you tell it should fly at. So the tether is just there to supply the power to the system, which makes it fail safe also. And then when to retract it, the jet ski or the UAV would land back on the water, and then it would be pulled back into its hangar. Right, and I mentioned the VOC instrument for tracking, and then the onboard camera. So we are looking at ways of doing slick thickness detection. And I used to talk about how this camera system that we have that measures, that actually sits at the interface in the water. So it sits halfway submerged. This image on the right is a picture of the interface between the air and the oil in the water. And we simply use the system to count pixels. But we found in a blind test that we did, a double blind study, I guess, that we did at the University of New Hampshire earlier this year and late last year, that there's some challenges with the oil meniscusing up against the plexiglass window that we have to put the camera through, because the camera sits in an airtight compartment. And so it was obscuring the actual thickness and actually giving us thicknesses that were great. They were greater than what the actual oil thickness was. It did give us thick versus thin, so it gave us relative thickness, but actually absolute thickness. It wasn't very good at giving us absolute thickness. And I want to mention, and I don't want to call anyone out, but I think it's important. And when I look through the talks that we had today, I think it's fantastic in the last 5 or 10 years, the capability of these remote detection systems that we've been tinkering with for a long time in the oil spill response research field, and they've come a long way. And their ability to define actionable oil from oil that isn't actionable, or where there isn't oil, is I think great. And there's a lot of different systems for doing that. I think we need to be careful if we try to extrapolate these systems into an ability to determine absolute thickness, because I think there's just way too many degrees of freedom for an oil spill. And what I mean is there's too many unknowns. The oil chemistry is not known unless you've already collected a sample and characterized it. Oil slicks are very heterogeneous, and they weather differently. And the amount of water in different parts of the same oil spill can be different. Photooxidation can be different across an oil slick, and the amount of photooxidation is unknown, and evaporation is unknown. All these things make it very challenging to remotely detect an absolute slick thickness. I'm not saying it can't happen, but I think the researchers are really handicapped in their ability to validate systems and prove that they actually can do it. I'm not saying they can't do it. I'm saying right now it's basically impossible to validate these systems. And I believe they need to be validated with real world spills, or demonstrations where we put oil on the water on purpose in the field. And then we have characterized those oil spills as far as their thickness with some other tool that we know is accurate. And so without that field testing, I think it's tough to, I grew up near Missouri, and in Missouri for at least part of my time, and it's the show me state. So until some of these tools are proven with actual data from a field release, proving them in a wave tank like OMSAT is a good thing, but it's not completely sufficient to proving how these things are going to work in the field. So we've had the same challenge with this system here, and we are actually kind of scratching our heads on what system we might use instead of the camera system to more closely determine an absolute thickness, or even better, doing relative thick and thin, or actionable and unactionable oil. Okay, so I mentioned the system is capable of an active response, and the active response is with herders. So there is a capability for the system to have a stockpile of herders and to spray herders around the perimeter of an oil slick. Herders act as kind of a chemical boom that force oil was too thin to ignite. It forces it into a smaller area, and therefore it's thicker. And then the system has this is the prototype. This is Tim Thornton, the guy who came up with this system and developed this flame throwing system, and a lot of other innovative things that are on the jet ski. And so this system is now put into the prototype jet ski to allow it to both herd, thicken, and then ignite the thickened slick to allow in situ burning to be done with a uncrewed system, allowing it to be rapid and safe. So I think it's an important step, and I believe if we can get over the hurdle of advocacy for in situ burning and herder use, that it could be a tool that allows in situ burning to be a much more commonly used tool for offshore oil spill response, at least. All right, so we're getting to close to the commercial stage, and I'd say we could probably have prototypes that are ready for at least testing by some of the oil spill response organizations sometime early next year, if we were pressed. The system by the vendor is being called Nomad. It goes out and does its thing on its own, and it comes back. This is the trailer that has been built for. The trailer includes 3 flat, I don't have good pictures of inside the trailer right now, but it includes 3 flat screen TVs and actually a control desk. And it includes the tools and a maintenance area for the jet skis. And it also allows 2 jet skis to be loaded into the back of it. There's a special dolly that it stacks, one stacks on top of the other. So this allows the jet ski system to be pulled down the road. And then this system could be put on the deck of a vessel and strapped down and be the command and control center, and also the maintenance center for the jet ski. There's other methods of operating the jet ski. This is the computer controlled system from a laptop that's carried in a Pelican case. And then there's this handheld joystick system that also can be used to control the jet ski. So I mentioned we have a core consortia developing the jet ski right now. It allows, I think, a robust platform for remote sensing and meets the goals of this workshop, I believe, by allowing things to be done at night, and I think even into fog with the right sensors. And it also allows active response. Because it's will be capable of being deployed from a helicopter, but it also can come off the bow of a ship and move quickly, likely much faster than a large oil spill response vessel. It allows a rapid response system and a remote sensing system that keeps personnel safely off the water. And our plans for this year is we hope to take it in June of this year up to Alaska. There's a 100 meter by 100 meter basin that allows in situ burning. So we hope to do a demonstration of the capability of the system to apply herder and to ignite herded slicks in 2022. There will be a visitors day on that, and if someone is interested in coming up to the visitors day, it'll be on June 16th. Send me an email if you're interested in that, and we can see there's going to be limitations on how many people that the facility can accept, but it might be first come, first serve. And then we are also working with the Canadian Multispectral Research Initiative project, and we hope to demonstrate the jet ski during their planned June through, or potentially June, July, or August field demonstration that is planned as a part of that project. And the remote sensing cables, the focus for the last 2 years on the jet ski has been putting the herder delivery and slick ignition systems into it, and the equipment and sensing systems that are needed for that. At the end of last year, we started a project to look more closely at expanding the capabilities and expanding the remote sensing capabilities of that system, and that's an ongoing project right now. So with that, Annie, I'll stop and turn it back to you. Thanks.
Exciting stuff, Tim. Thank you. I want to come to Alaska for Visitor Day. Let me see here. Another question here about just, can you quickly just highlight again what jet ski capabilities it currently has that can detect oil at night?
Yes, so we work closely with Dave Chenault, so I think we could put the polarized camera on it. I think that's probably one of the most effective methods for, and it's such a small system, it's one of the most effective methods. So that's one of the systems that we're considering, because it doesn't care about day or night, it's the emissivity of the oil and the difference in emissivity between the oil and the water surface. And it can look through dawn and dusk when oil and water might be the same temperature. But IR systems are also the VOC system that we're planning on putting on it will detect oil. It doesn't care if it's night or day as well. So those are some of the systems that we're considering for our nighttime and potentially even detection in heavy fog.
Great. And then I don't know if you touched on it, but the second part of their question was, at least one system uses VOCs to detect oil. What is the level of VOC detection compared to weathering?
Yeah, so I'll say that the VOC, we are in the process of speccing out what VOC system we actually put on it, and I can't say right now what that's a question about detection limit of the system, and I can't say what the detection limit is of whatever VOC system we look at, but certainly if the slick is so highly weathered that it's not putting out VOCs above the detection limit of the detector, we have a problem.
The next question is, well, amazing vehicle. Thanks for presenting. First question, how much do you estimate a production model would cost?
Yeah, so the off-the-shelf jet ski is pretty cheap, right? I mean, I could almost afford it, right, on my salary. It's about $10,000. But I'm guessing, and so I don't. The answer is I don't know. I'm guessing that something like the radar system is several tens of thousands of dollars on its own, and so I'm guessing that the raw, all of the off-the-shelf tools that we're putting into it approach the $100,000 cost to the vendor. So. I'm guessing a cost, my hope is the cost is cheaper than some of the uncrewed vessels that have been used by some of the oil spill response organizations. I've heard numbers up to $700,000 for those systems. So I hope that we can keep, and it depends on what kind of, we hope to have kind of a spec sheet, and you check off what you want to be on the system, right? And that will determine the cost. But we hope to have a system that does what the capabilities that we want for a fraction of the cost of some of these larger uncrewed vessels that we've seen in the past.
Great. The second part of their question, how do you think the radar will work in rough seas and swell typical of offshore environments in the Pacific?
So I'm not an expert on that. My guess is that the radar will stick its head up over the top of a swell as the vessel is on a swell and be able to look over into the distance to some extent and collect an image to see things. But I could be wrong because I'm not a radar expert. It makes sense to me. So I do think the way we have it built to put it up as high off the water as we can will allow it to do some of that without a challenge. And look, it doesn't need to look 2 miles down ahead of it, right? It needs to look 100 yards ahead of it and make sure it doesn't hit a marine mammal that's in the, or some other sensitive thing that's in the water. And I think these things are highly agile and they can turn very easily. And I think it can maneuver around things without having to look 2 miles ahead and make a decision. It could look 50 yards ahead and make a decision, or shut down and hit the brakes even.
And that kind of leads into the last question I see here. Chris Weiss says, I snorkel a bit and dodging jet skis is a common issue. Glad you have underwater cameras. How will this work in lagoons versus offshore with swells and waves to obstruct view?
Well, I mean, it's really not designed to work in a lagoon, right? Remote sensing of an oil slick in a lagoon may not be as important because there may be other ways to do that. But putting it making sure that a spill of whatever volatile compound in a lagoon is safe to put personnel in it could certainly do that. And I'm not sure snorkeling should be happening in that kind of event in the first place, but I could envision that we could put a smart system into it that's looking at, taking signals from all its cameras, including the radar system, and doing an autonomous response to whatever it sees to avoid hitting something above, below, or on the water even.
Yeah, I think that's one of its greatest assets is taking people out of the water, and it just enhances safety of response, being able to do some of the things we usually do on the water. Thanks so much. Did anybody else have any questions? We're right on time still. That's all I see. Appreciate the presentation, Tim. Thank you.
Thanks, Annie.
And last but not least, today we have Ed Owens presenting next. He is from Owens Coastal Consultants, and he's going to talk to us about some canine projects related to spill response.
It's Paul Bunker. Ed unfortunately can't be in a position to present, although he might be on the call and able to answer questions, but he asked me to go ahead and present if I could. So
okay. Thank you, Paul. Welcome.
All right. Can you see the screen okay?
Looks good to me.
Great. Well, thank you, everyone. And I think I'm the last talker today, and I'm conscious of the time. So I'm going to try and keep on time. As I said, Ed can't unfortunately join us on the call. So he's asked me to give his part of the presentation, and then I will go over the canine side. My name is Paul Bunker, and I'm the principal of Chiron Canine, a consultancy and training company that focuses on detection. So I'm going to go over a bit of a background of how we got to where we are now in the canine SCAT community, and lead that on to canine detection underwater and also in night or fog, low visibility type SCAT conditions. So Ed and team, or his team, conducted a review on behalf of the API back in 2013, looking at subsurface oil detection delineation in shoreline sediments. And that led to both a field guide and a final report, and the final report being published in 2014, in October 2014. And actually, that was when I first met Ed at a conference and started to discuss canines, although Ed had already been exposed to canines in Norway, and it included that in his final report. And he was looking at the best practices for subsurface oil detection. And a lot of this was based on, obviously, the experience at Deepwater Horizon. But he was comparing the different current practices available in 2013. And clearly, you know, canines brought something to the field potentially that would bridge the gaps. And I think it's important to understand that canines are a tool in the toolbox, just like a lot of other tools, and they are not the final solution. And, you know, we don't ever want to pitch they are the final solution. But if we understand the capabilities and limitations of any tools in the toolbox, in our case, the canines can obviously offer potentially a bridge in the limitations of some of the methods and protocols and techniques being employed compared to others. And when you fulfill that toolbox to all green, then obviously you're conducting surveys in depth, and that just makes it more productive and more effective. So the Ed had the kind of vision of bringing canines into the SCAT community and bringing it up to date, particularly here in the United States, because that's where we're both based. I'm in San Antonio, Texas, although at the time I was in North Carolina. And the first opportunity we had, again, was an API-funded trial up in North Carolina in 2015. And this is really where a proof of concept was conducted just to demonstrate the capability of canines to detect oil within, it was sand actually, the sediment being used, oil, the oil in sand, and it was down to 3 feet. And it was a very simple exercise. Can dogs firstly detect and respond on oils? And in this case, we used it was a Texas crude, and I'm sorry, I can't remember the other oil, but it was another crude oil. And that was successful. You know, we got something like out of 706 targets, if I remember, the dogs detected 99.9%. It missed one, or the dogs, because we had a couple of dogs in the whole project. In 2016, then, there was an opportunity to go up to Nova Scotia and conduct shoreline surveys on what had been an actual spill response. The original spill was in the 70s, the TV Arrow, and there'd been a burp of the tank in 2015, later 2015. It overwintered, and then I traveled up there with a canine team, and we conducted some surveys. And again, you know, the dog was very successful, but one of the interesting things was not only did it detect the burp, so the 6-month-old or thereabouts oil that had washed up and overwintered, but actually the dog was responding on the original 1970s hard standing type oil that was still present within the environment. And, you know, the team put the dog on to areas where there was no known oil, as well as known oil, although it was blind to both myself and the canine team as to what was present and what shorelines were being searched. Well, actually, not long after that, in 2016, there was a spill up in Saskatchewan in Canada, In 2016, 2 canine teams went up and supported the initial response. It was late in the season, unfortunately, so I think there was only there like 2 months. But they went back again in 2017. 4 teams went up for 4 months, and then 2018, there was some more follow-up searches. And really, this was the first operational deployment of the canine teams and was a real test, baptism of fire, if you like, a test. The dogs had to deploy on boats. It was the only way to get out there. It was arduous terrain. It went from the winter months, I want to say in March, so freezing cold, and there was snow at times, all the way through the heat of summer, which actually does get hot and humid up there, and again to the end of season. And in 2017, the canine teams had something like 8,000 confirmed finds. So it was a great learning experience. And some of this presentation is based on what I learned, particularly because I was one of the canine teams, both as the team lead and the dog handler there, of what I observed of my dog and its capabilities within real life. 2017 then, as well, we went up to Prince William Sound, conducted some search on the sequestered oil out in Prince William Sound on some of the islands. Again, the dog had some really good successful finds of that oil, even though it would weathered. It was under the gravel, under the boulders and the rocks. So it was very difficult to confirm a number of her, it was a female dog, a number of her responses, just because it took so long to try and dig up wherever she responded. But where they did dig, they did find oil. In 2020, there was another API-funded trial, and this looked at both of the detection capability of 3 canines to detect weathered oil targets. There was Macondos, there was some tarball, and some other oils. But also in a separate phase, it was looking at targets that were down to 15 feet this time. And again, the canines were very successful, something like a 98% success in that one dog missed one of the targets in the whole of the trial. Again, the canines were double blind during those trials. So we demonstrated the capability of dogs to find things at depth. In 2021 then, and this is kind of moving to where we are in this presentation or the focus, Bessie and Naval Research Lab. So Bessie funded the project and Naval Research Lab undertook the work, but we supported that. Sharon Canine supported that with Ed as well, looking at underwater oil detection. And I'm going to talk about that a bit more in a little bit, and I'll actually show some video of the dog working on the results of that trial. And currently we have an ongoing project where we're looking at canines which are trained to find specific oils and ignore background oil conditions on the Gulf Coast here in Texas. The dogs have gone through research with Texas Tech University at the Canine Olfaction Lab, and that went really well. I have 2 of the dogs at the moment, and we're just waiting to start the field deployment area. The field deployment phase, and then that's ongoing research funded by Texas General Land Office, TGLO, in partnership with Texas A&M University. So why oil detection dogs? Well, in the controlled trials, as I said, there has been 99% accuracy down to something like in Prince William Sound, I want to say it was 68% or something, because the dog responded and we wasn't able to confirm where the dog responded. You can see that photo bottom right. That was the terrain that we're trying to dig through, or the support team were trying to dig through to confirm where dog responded. And it simply wasn't feasible to do that for all her responses. But when you're looking at around 98% actually in the controlled environments, in Saskatchewan, 4 teams, something like I said, 8,000 finds, the dogs were around 90% accurate, and that's in the field. Remembering that, one of the issues, not an issue, but one of the capabilities of the dog is to find even minute traces of oil, but actually in verification purposes, you can't verify something that we can't see. And, in the terrain of Saskatchewan, it made it very difficult at times for us to even see what the dog had responded on or find it, because of the amount of vegetation and the difficult terrain we were working in. But so we're looking at around 80% actually over that period of time with that amount of 8,000 confirmed finds. Most SCAT surveys have around 60 or 70% of no observed oil. And this is where, you know, the dogs have really a great advantage, because you can use the canines to reduce areas by saying there's nothing here, rather than actually telling you there's lots of things here. You know, so the dogs can cover a large amount of area very quickly, very effectively, with high confidence that they're not missing anything, and say to you, there's nothing here. And again, you know, when you're going on a lot of these SCAT surveys and you're manually having to dig pits just to tell you there's nothing there, that's labor intensive, manpower intensive, whereas a canine team with maybe a SCAT assistant can actually cover a lot of area. And then when it does have an alert, a response to a target, you can prioritize your resources to specifically investigate those locations, and the canine team just moves along and keeps on with the surveys. The trial in 2021 I spoke about, 15 feet. This is some images of the actual trial. The field on the left is here in Somerset, Texas at Global Training Academy, which is the facility that I have my company on. And basically there was boreholes which were cased with PVC, and then inner pipes, and you can see there in the right-hand photo, inner pipes were loaded into the actual casing at 15 feet in depth. And the bottom, depending on the actual target, but in the middle photo, you can see some of the targets being placed into the pipe. There is a plug of native soil there. And then it was capped and sealed with a waterproof seal. And then when the pipe was moved into the actual casing, it was filled with native soil, so that the whole pipe was filled with soil up to the ground level. And that was the 2021 trial where the dogs were, and there was like 10 of these pits, as you can see on the left-hand side. A number of them were just native soil, and a number of them was native soil with the target in, the 5 different types of targets. And then the dog handlers, myself and another handler, worked the 3 dogs blind to what was in which pit. And then we recorded whenever the dog actually responded. And the data set was actually analyzed for dog's response versus the actual location of targets. So currently in 2022, the techniques typical are slow and require verification. So there's only a few good options for sunken oil detection that exist at this point. And if we talk about USCAT, here's a graphic that Ed provided from the USCAT technical reference manual. And you can see, because the surface coverage area is high for a canine, the speed of search, and also the resolution is that they can find very low concentrations. And we know that they've actually responded on below 1 part per million because during the 2021 trial, a PFD was actually used to analyze where the dog had responded. And although the dog actually picked up in one case from around 90 feet from the source and go to the source, the airspace was analyzed 1 inch from the surface, and it was at like 6 parts per million. So we know the dogs are going well below 1 part per million detection rate or capability. So potentially it fills the top left corner of that graphic, but clearly there's more work to be done. And that leads me into the underwater oil detection capability, which was the BESI funded I spoke about. And this, and there is a little video in a moment, came from my experience in Saskatchewan and Nova Scotia, where I observed the dogs, different dogs, detecting sequestered oil underwater, even though they hadn't specifically been trained to do it. And I believe, just like there's cadaver detection dogs, and up in Seattle area, there's whale scat detection dogs, I believe that canines could detect hydrocarbons sequestered underwater. both based on prior experience with cadaver dogs and also my experience on the ground of my dog responding on actually sequestered oil underwater. So the issue was actually training a dog that a body of water is a productive place to look for oil, because we train the dogs by associating the smell of the oil with its toy or a treat. And if we go out into a lake and tell the dog to look for something, but we're not able to use targets in training because we would contaminate the environment, obviously, if we put oil in water to train the dog with, then we're going to just frustrate the dog. It's not going to understand what we're trying to achieve. So I actually had an idea for this device. Bessie, thankfully, funded a research trial again with Naval Research Lab to develop this device. And basically what we've got is a compressor on the left-hand side. This is just the type of compressor you use from Home Depot or something. There are two types. This is a battery-driven compressor, and then there's a passive air tank. The passive air tank is totally silent in operation, where obviously this compressor buzzes. But the compressor gives us, because it's portable, it gives, and battery powered, it gives me a lot more training time while I'm actually training the dog in the process. Once the dog is trained, then I switch to the passive tank, which has zero noise, and there's a valve on it which allows you to control the bubbling a lot easier. You can drip feed the bubbles. You'll see video of the actual compressor bubbling in a moment, but you can drip feed the bubbles and it's silent operation. So it kind of transfers the dog to the next stage in training. The tank in the middle, that's a paint spray can tank. I've adapted it slightly. I have some different valves on there, a pressure gauge, etc. And there is about 1 liter of Texas crude oil held in the base of that tank. But the pipe going in and the pipe coming out, which is the tube on the right-hand side, only attaches to the top. So then it's just pushing out headspace. And the tube, you can see, then goes underwater and is laid on the bottom of the lake or the river, whatever you're using for training. And then the bubbles coming up smell of hydrocarbon. Now, in this case, they're just the headspace. In real sequestered oil, my expectation is, and I am no expert at this, but I believe there will be more odor available for the dog to smell just because of the dilution of the oil that's held there coming to the surface, as well as if there's any particles actually raising to the surface. But until we continue this project into field deployment phase, it's difficult to say. So here's a video. This is my dog Poppy on the front of my boat. If you look on the bank, there is the assistant, and she's controlling the actual device. Here's the pipe, and there's the bubbles. And I've left this on so you can actually see what we're talking about. The wind is coming from left to right. So the dog picks up on the plume smell of oil. And then she starts to, I see a change in behavior, and then she starts to move her body towards the plume. And if you notice, what I'm doing is moving the boat from left to right, and the dog will move its body position to the opposite side of the boat to try and keep its nose in the plume. This allows the dog to steer me towards the source of the smell. I'm moving out the plume, she moves to the left to stay in it. I move the boat towards her direction. She moves slightly right, I move slightly left. And what I'm aiming to do is have the boat on the dog on the front of the boat, because that means I'm pointing straight towards the plume or the source. Again, we've left the bubbles on here so you can see. And in the early parts of training, this is how we do it anyway. But later on, there would be no bubbles showing because they're very intermittent. And she's doing this for the toy. See there, I throw a ball. And that's purely why she does this. She's associated the smell that's held within the water with her toy. So she wants to get to her toy, and she just knows that the actual odor of hydrocarbons is how it's going to get there. So nighttime scat then surveys as much as possible are planned for daylight and low tides. But what happens if there's none, and we're talking about anything north of 60 degrees, obviously in winter. And this is a graphic from Anchorage. And you can see here, there was a double high tide. The only low tide existed during darkness. And actually in the upper intertidal zone, the most it was ever exposed for was 2 hours, the middle was less, and then the lower it was not at all. So actually, the capability to actually search effectively or survey effectively during daylight hours might not exist because of the environment we're working in. And there's more examples. It's not just up in Alaska, there was California as well. And obviously this means that potentially you have times when you're not able to survey the full intertidal zone because of that. So this is my dog in Saskatchewan, and this is one of the times that she actually detected sequestered oil under the water. She'd never been trained to do this. The behavior she just did there was called a check pace, and now she's sniffing the water. Lapping the water is actually pretty common when you're looking for cadavers, or as we've found, oil underwater. We believe that, well, there is a sensory organ called the Jacobson organ at the back of the mouth. And it is a odor sensory organ predominantly used for pheromones, but there is a understanding that dogs will use it to confirm an odor, particularly when it's wet like this, underwater like a cadaver. So in this case, I realized there was some unusual behavior in the way my dog was working the water. It had never been trained to do that. It clearly can't respond by sitting in that water type environment. And I asked the SCAT team lead, or I pointed out the team lead, I think something is going on here. He actually weighed it out, stirred the sediment, and a sheen came up to the surface. Here's another example. This is the same dog, again, up in Canada. She's searching the sediment, again, not under so much water. And where she actually held there and then stands and looks at me, again, disturbed the sediment, and there was a sheen that raised to the surface. And there was an example from Nova Scotia as well, and this is where I believed that dogs could find sequestered oil underwater. So working a canine in limited visibility, such as at night, we already do it. We do it down here in Texas because of heat. We might do it operationally when I was doing counterterrorism searches, etc., because of obviously the threat environment we're working in. So actually working dogs is not uncommon whatsoever. We have several options that exist to us in a non-combat role. If we're working them off lead, we'll use white lights such as flashlights or headlights on the handler, headlamps on the handler, sorry. Also in a picture here is my dog Poppy. She has a chem light, which is fitted on either side of her harness, but the harness can actually hold chem lights. Or on the strap on the top, I can attach a beacon light, a battery operated. I like the chem lights that generally last for the full survey 12 hours. And that's visible enough for me to see her. There's glowing lit collars, etc. So there's ways of actually seeing the dog as well as using white light. Or you can use night vision devices, which we clearly do in combat type missions, but they do exist. The other option is if you don't want to put the dog off lead because of the environment you're working in, you can just work the dog on the long lead on a 50-foot, 30-foot, 50-foot long line, but also you can use the white lights, etc. at the same time, particularly headlamps and the chem lights on the harness to increase visibility. The other thing we can use is the GPS, because the GPS system that I use, it actually tells me which direction the dog is away from me and the distance that she's away. And actually this version will tell me if she's passive. By passive, I mean sitting. And that tells me, even if I can't see her, if she's giving a response, because her response on target is to sit. And one of the advantages at night is that a canine's senses are enhanced. So they actually work a lot better at night than during the daylight, because there's a lot less distractions, a lot less environmental noise, as in noise pollution, etc. Because the warm air from the ground rising into the cool air of night actually increases the amount of odor available to the dog. So rule of thumb then, a canine can tell us if oil is present in shallow water on the shoreline or deeper from the front of a boat. And if it's safe for a human, then it's safe for a canine. Potential applications there are nighttime scat, fog scat, exactly the same techniques, and then U-scat. And I'm just about right on time, so I've got time for questions if there are any.
Great. Thank you for that, Paul. Thanks for pinch hitting today for Ed. Very interesting topic. I don't see any questions in the Q&A. Does anybody want to raise their hand if they have a question? I know I was going to ask you, you talked about if it's safe for humans, it's safe for dogs. That's something I've heard some others have concerns about, is that you're exposing dogs to something that could be potentially harmful to them. How do you answer that question when that comes up?
Yeah, so, you know, it does come up a lot, obviously, and clearly we have concerns about that ourselves. However, there are several prior experiences which demonstrate actually canines do not have adverse effects to sniffing and of hydrocarbons. And some of these are that we've had arson detection dogs, you know, the fire service, etc. There's thousands in the world, and there's over 600, as I understand it, operational at any one time in the US and Canada, etc. Australia use them, the UK. And in the decades they've been used, and they search for very volatile hydrocarbons, more volatile than potentially crude oil, etc. There's never been any reports of any detrimental effects to canines. And I do know one canine was studied for a whole of its career, and the vet said there was nothing detrimental in sniffing. What we have to remember as well is dogs don't breathe in. You know, they're not in a cloud of hydrocarbon headspace and just breathe it in. When they're searching, they sniff. And once they've, so they separate the air between their lungs and their nose. They have that ability. Once they sniff a target, in this case, they don't just keep sniffing and sucking in all that air. They've done it. You know, that part of the job is done. And if you notice, the dogs actually, they lift their head up and then they just sit, you know, they're not putting their nose in and smelling it. Now, if the environment is assessed, and obviously we do safety surveys before humans or dogs go in. If it's not safe for a human, then a dog wouldn't go, and we wouldn't send a dog into that environment. They can also carry monitors on their collars. But, you know, honestly, I wouldn't put my dog into any environment. And I know the SCAT teams we work with wouldn't ask us to if there was any risk that we thought there was any sort of risk in breathing. So while there's no specific research, that funny enough, there's never been research done on the dogs sniffing explosives or drugs. I mean, they've done it for, you know, however many decades, but there's never been any research done, and there's never been any anecdotal talking that it's detrimental to a dog, even though to us they can be carcinogenic, etc. So yeah, I think, you know, unless someone wants to fund that, it's not research to be done, because at the minute there's no observed issues in the long term. Remember that dogs, you know, generally, as unfortunate it is, only live 8 years or so. So their lifetime, you know, what they're saying as well, potentially their lifetime just doesn't allow it, even if it was something that potentially, if we was exposed, would harm us.
Right. Thanks. There's one more question that popped up here. How much does it cost to lease your dog services, and what is your range of operation?
So yeah, I'm not the only team that's out there. I'm in South Texas, as I said, San Antonio, Texas, and I've been up to Canada a lot. Well, I've been up with a team that deployed up to Alaska. We've been all over. COVID, unfortunately, has caused some issues with flights, because it's not just us, they're just not flying dogs much now. So I ended up driving up to Canada. So range-wise, you know, within the United States, both OCONUS and CONUS is possible, and even into Canada. There are other teams, as I said, available. It's not just me. So there are canine teams out there that exist. We do have a daily rate, and then it'd be plus expenses. Now, what I do is the daily rate includes the dog, and it includes all veterinary, etc. So you're not going to get suddenly, well, my dog's sick, I'm going to add a vet bill or anything. You know, the daily rate covers all of that, is food, etc. The only thing to consider is really when you deploy a dog, firstly, the accommodation, we share the accommodation with the dog. So a hotel or something has to be pet friendly or working dog friendly, because we have had dispensations in the past for a working dog. Flight, obviously, for the dog. Sometimes they have to go cargo, which can be pricey, but sometimes they'll fly them on a plane, which isn't so. And then the dog has to have a specific veterinary inspection before and after, but that's only like $90 an inspection. So they're not, hugely expensive in that respect. It's going to depend on the length of task, etc., and where it is.
Well, and you answered the first part of the second question, but the second part of it is there some type of certification process for oil sniffing dogs?
Yeah, so myself, Ed Owens, and actually a gentleman called Dwayne Ferris, he actually does pipeline detection, leak detection. We formed an association called the International Canine Spill and Leak Detection Association, and we do certifications through that with an aim that there is a certification process and that clients can actually have some confidence in what they're receiving as a working dog team actually has demonstrated some sort of capability. So yes, the certification does exist, and either Ed or myself or Dwayne would actually independently observe the dog. So Dwayne or Ed come and they certify me, I don't certify myself, although I'll certify other teams that I haven't trained, etc. But yes, there is a certification process that is available.
Very cool. Well, thanks so much for sharing that with us today, Paul. That brings us to the end of our workshop. I just wanted to throw a few thanks out there for the team who helped put this together. Greg McGowan, Ellen Fro-Daniels, and Elliot Frodall, who has helped us with IT and getting this Zoom meeting put together. I also wanted to thank all of our wonderful speakers for taking the time to put those presentations together for us. And I think we got a pretty good range of different types of tools that address some of the challenges of responding to spills and low visibility. It's not a simple, there's no miracle tool out there for it, but it's good to see all the research and all the projects that are happening to help us get better at it. And thanks for everyone who attended as well. Did you want to say anything, Greg?
I was just going to wave and say thank you, and thank you again to Annie. Tom, do you want to close us out here?
I would just echo what you're saying, Greg. It's been a great, very productive day. Lots of things for us to think about and reach out to some of our interagency state partners, our OSROs, to bounce some ideas. And again, I'm really looking forward to next year's Spill Technology Workshop in its regular cycle. Thanks so much to the presenters.
Thanks all.
Yep, I just threw up hopefully you can see that, a link to our science page on the OSPR website. It's where all of you probably found the agenda, and that is where we will be putting up information about the 2023 broader technology workshop that we're putting on. And I also wanted to mention Washington State is planning one for this fall. So stay tuned for that. Check in with Sonia Larson or Department of Ecology's website to find out when that gets scheduled. So on that note, thanks everybody for chiming in, and enjoy the rest of your spring break. If it's spring break for you, I would say have a great drive home, but you're probably all at home. All right, signing off.